Hey, do you feel like you've learned quite a lot of Unity, but still feel a little unsure about your grasp on it? In this case, this lesson is exactly for you. By the end of it, you'll have an understanding about a couple of advanced algorithms, will be able to perform advanced actions in the editor of Unity, will build an Octree data structure. You will learn to turn the time during the game backwards, work with the editor windows, will understand how to manipulate and edit mesh directly in the Unity's editor. We will apply a waveform function to a simple mesh, we'll cover the time complexity concept and the balanced binary search tree data structures. As well as that, you will learn about recursions and how to transform them into stack-recursion form, taking load from the memory stack and putting the entire workflow onto the heap of the computer's memory, avoiding any kind of stack overflow errors. My name is Igor Aherne, and you are watching an advanced lesson on game programming in Unity. This part is a logical continuation of How to Make a Horror Game Part 8, the link to which you can see on the screen. And by the way, I saw Brecky's and Etiski tutorials being subscribed to me, so big ups to you guys. Finally, I want to thank all of my subscribers that are following me, and I really appreciate your effort. Keep studying with me, because computer games development is an amazing subject. I absolutely love it because it's so vast, there is so much to study, and there is always something new which you can learn. Even though we're specializing on Unity directly as being our main game engine, with additional information that we're discussing, it's very possible that you might make your own and understand everything tied with the programming even more deeply. Currently, in 2016, I've successfully graduated with the first class honors from University of Kent, and at the moment I'm in the University of Newcastle, studying Masters in Computer Games Engineering. The amount of content conveyed in my 9 lessons is close to the staggering 40 hours, and if you want to support me, please do so at my website, igoraherne.com. The front page has a button, by clicking which you can thank me with any sum which you feel like. Oh yeah, and after doing so, you'll be able to add me on Facebook. The link will be on the page which follows. So turn on the annotations of the video, and you can also click on the video settings and watch it at 1.25 speed, if you're up for a hardcore flow of information. With that said, let's get down to upgrading your skills. One of the most important topics in game creation in Unity is how you write an editor script. Such scripts can run at the background during the editing process, while you're creating your scenes and design your objects, position them within the scene, so that you can cut down on the number of operations that you have to perform. One of examples where such things could be used, if you have a scene, big terrain, and you've got to detailize it with many objects, let's say stones, maybe bushes or grass. Well, in Unity you can use standard terrain, but if you're using your own meshes, that means that you have to position by hand every single rock and rotate it a little bit, scale it up, scale it down, so that it looks random and doesn't look symmetrical. Just scatter objects across the scene. Well, if you do it by hand, it will take ages. However, if you got a script that you've written yourself, you can code it such that just by clicking on the ground, it's going to instantiate the required object with the random rotation and scale. You can use editor scripts to quickly navigate through the files where each unique object in your game scene view, right here, is tied with some sort of file in your hierarchy. So by selecting, let's say, camera, you are going to pick some binary file in here, or maybe some sort of scriptable object file, which we'll talk about in a second. And by picking light, into the memory you're going to load some different file from your hierarchy of folders, and then perform some sort of operations on them, maybe store settings from over here into the file, so that later on you can access this data from the file and maybe apply it to this object or some different one. So editor scripting is one strategy. Another way, which you can also interleave and interweave with the editor scripting, are static classes that can run at the background while you are working on your scene as well. So the first way to work with the editor is to create an editor script. Let's make a task for ourselves to have a cube selected, and once we have it, as we press the button, let's say button G, we'll be creating other cubes, similar ones, around the selected cube. For example, we can create a 3D object, a cube, and let's remove the box collider because we won't need it. The plan is that when we have this object selected by pressing G, we can clone the cube around the original one within some sort of radius limit. To do this, we have to have an editor script, which will kick in as soon as we have this cube object selected. On top of this cube, let's attach a newly created script, which we'll call cube behavior. Pay attention to the casing of the letters. And inside of the same folder in the assets, let's create a prefab called cube and drag our cube from the hierarchy of the scene into our prefab. Now, as we drag and drop the cube prefab, it will have everything, including the script as well. Now let's create our editor script. Let's right click and create a C# script, cube behavior editor. Now, it's not really regarded as an editor script until you've placed it into the editor folder. The folder should have the first letter as capital and should be under the assets folder. Not editor, but editor. So drag and drop the cube behavior editor into its appropriate folder, the editor one. If we look at cube behavior, which was attached to our cube, we can then see that it's just a normal usual script with a start and update function, which we won't actually require, so let's get rid of them. As we open our editor script, we have to modify a few things before it can be considered as a real editor script. We won't require system.collections namespace, we will need Unity Engine, and we will need a Unity editor. The class itself should extend from the editor, and this class is available because we've included Unity editor namespace. Once we've inherited from it, let's get rid of those functions. And there is one more line of code that should be placed above the class definition, inside of the square brackets. A custom editor, open the round brackets, and in there declare a type for which this custom editor is created. Let's say type of game object. So this script will kick in as soon as we have a game object selected. Because we're inheriting from editor, we can make use of the function called onEnable. This is like an equivalent of start function in mono behavior, the kind of script which would be thrown on different game objects. Here we have onEnable, and it's ran only once as soon as this script kicks in. There are a couple of keywords which we can use. For example, target. We would like to establish the reference to our cube object as soon as we have it selected, and for that we can declare a variable of type gameObject and call it selectedCube. Inside of onEnable function, we can make our selected cube be equal to the target. The target is the keyword supplied by the editor class, and it means the selection. Just pointing the selected cube towards the target is not going to be correct, because at the moment target is of type object. It is more ambiguous than the game object. Therefore, we have to cast it down to game object. And remember that this is going to be always right. We are not going to be able to run this piece of code and force something that's not a game object. For example, if target would be something different, we would be forcing it as a game object, but it's not even going to be executed, because this piece of code ensures that this script is only ran when we have a game object selected. Therefore, we're safe to make this cast in here and force the target of type object to be cast down to game object and assigned to cube. Now, if we'd like to access the cube behavior on that selection, we can create a variable of type cube behavior. And after we've established the reference to the game object, we can point our selected cube behavior towards selected cube dot get component, and of course type in cube behavior. As we're selecting a cube, our editor script notices this because we've selected a game object, and we've immediately drawn two references to the game object itself as well as to its behavior. This happened only once upon the selection, during onEnable function. There are several methods which we can use, for instance on inspector GUI. This method was declared in the editor class, and if we would like to override it, meaning that we can provide our own code instead of the one specified in the editor class, to extend it or override it, we first of all have to make sure that this is a public function and type in override keyword in front of it. This method is ran several times a frame as soon as there is a change in the scene. For instance, we drag some sort of slider inside of the inspector or change the object's position. Then this function is run several times a frame, and during it we can debug the selected cube's name. Let's go into Unity and check that this is working. Jump into the console, clear the messages, and as soon as we select our cube, the message is displayed several times. Once we change a position and triggering this function, we get messages several times a frame. Same thing happens if we turn off the mesh renderer or turn it back on. Any change in the inspector is going to trigger this function message. Now there is an interesting thing, because we can select a camera and we'll still have a message displayed. Of course with a different name, because we've selected a game object and we've forced our editor script to kick in, and we're debugging the name of that game object. This is not totally right, because we don't restrict ourselves to selecting just the cubes. It is gonna work as soon as we have a game object selected. But for now this is not a problem for us. We can restrict it later on to just trigger only if we have a cube selected. If we don't want to make use of onInspector GUI function, but would like to make use of our own function, which is ran for every update of editor, we can create our own method and call it custom update, for example. The name doesn't matter, you can name it anything. But apart from creating this function, it has to be registered. We have to tell Unity's editor that this function has to be treated as such and be called every frame of the editor. Therefore we have to go into editor application and add our function to a delegate, which is a fancy word for a function pointer. This delegate gets used by the editor application and calls all the functions that have been added to it, including our custom update. So drop it like this. And just to check that it works, let's debug a message. Custom update has been tied to the editor's application update delegate. Clear our messages, and as soon as we have our script working, meaning that we have to select some sort of game object, as soon as we have it, we got our messages displayed here. Once we've checked that it works, we can comment out this message and return back to our task. Remember about the task that we've put before ourselves. As we select this cube, when we press some button, let's say G, we would want to populate other cubes around the selected one. To be specific, the prefabs that we've created here, the cube ones. For that, we have to somehow register the input that is coming from user. And it is slightly different from the one that we are using as the game is running. We're not able to use the input class like we did in the previous tutorial. Here we have to be sneakier, and if we come back to our code, you can see that currently our custom update, and let me comment out our debug message because we don't need it, but you can see that the custom update was added to the update delegate of editor application. Yes, this way it can be ran every single frame inside of the editor, but this way prevents it from receiving inputs from a user or a designer. Functions added to this callback are really good to display your own messages or to perform something at the background. But you shouldn't be adding anything to this callback that has to receive an input from the user. Instead, we're going to use another callback, the one that belongs to the SceneView class. And it is called onSceneGUI delegate. It's quite famous, so you might have met it before in other lessons of other people. But adding our function to this delegate instead of the previous one will allow us to use the event class, which is the key in receiving the input from the user in Unity's editor classes. But there is one important thing, because the functions that are added to this delegate have to have a very specific signature, meaning that even though the name doesn't matter, they should receive a parameter of type SceneView, and the parameter can be referred to as, I don't know, CV. We're not going to be using it, however it's a thing required by Unity's internal core. I suspect that it carries information about the events and serves as a link between Unity's viewport and users' inputs. Having added this argument to our signature of our function, when we jump back to Unity, you can see that the function is ran, even if we don't select any kind of object in our scene. We will get a new message as soon as something happens on the screen, meaning that even if we move our mouse into the scene view, right here, into the big window, we're gonna get extra messages popped into our console, which is very nice because now we can code our inputs, and this function will be able to process them, unlike the way we did it previously. So, as the user selects the cube and presses the G button, we would want to create and instantiate our cube prefab somewhere around it, but not further than a given radius, let's say 4 units. That's why, in our script, we will declare a variable, the float type one, and call it radius. By default, I'll set it to 4 units. To signify the event, that means that something happened in the scene, we have to supply a variable of type event inside of our custom update function. So every time it's ran, we're creating a new variable of type event, let's call it E, which will be corresponding to the current event. So event.current. It can be anything: button press, nothing, mouse movement, etc. And during our function, we can check if our current event was a key. So we're going to type isKey. And if it's true, then we check for another thing. If event was a character, which exactly equals to G. So two conditions in our if statement. First of all, it has to be a key, and then we check if this key has a character corresponding to the one G. If that's the case, that means that we've received the input from the user, and we can proceed with instantiating our prefabs next to our cube. Well, right now we'll create a prefab slightly to the right of the cube, and then later on we'll think about how we can randomize the position of new cubes which are stuck around the currently selected one. To instantiate an object, we have to make use of the class called prefabUtility. From there, we would want to make use of the function called instantiatePrefab. When I open the brackets, notice the requirements of the function. It requires an object, an ambiguous thing. Object can be anything. It's hierarchically higher than the game object, than the string, than the character, than the integer. It's the biggest possible thing, the object, the most ambiguous one. But that's what's required by the function's input. And we will tell it how to get our cube prefab. We will put a string saying cube, which has exactly the name corresponding to our cube prefab in here, in the assets folder, with a big capital C. But that's full of errors, because first of all, the function requires an object, and we've supplied it a string. That's incorrect. Instead, we should modify our argument such that this string is being used by the class resources and its function load. This might seem complicated, but it's really not. Resources is just a class for the folder which is called resources. And at the moment we don't have such folder, so we should create it. Resources is really a folder which is regarded by Unity in the same way as the editor folder. That is, it has a special meaning. Not many folders are so important that they have their own class, but resources does have its own class, and it has several functions associated with it. We should drag our cube prefab into the resources folder, into here, and because our cube is right inside of the resources folder, meaning that it's not hidden in any other inner folders, it's just straight away inside of resources, we can just put its name like this. Otherwise, we'd have to use slashes, put the name of the folders, and reach our cube from there. Here we go, resources.load, we made use of our string, and if I open up quickly the brackets for resources.load, you can see that it has three overload methods, and we are interested in the second one. The second one requires a string path, the one relative to the resources folder, which is correct. Our cube does lie straight away inside of the resources folder, but this function will return an object, and this object is then going to be used by the instantiatePrefab function, which indeed requires an object as its argument. So this now is perfectly valid. However, because this function prefabUtility.instantiatePrefab, which envelops everything, returns something, we cannot just call it like this. We should assign the result to some variable. And for that, let's create a variable of type gameObject and call it instantiateDCube. Let's then assign the result of this function, what it returns, to our variable. Try to figure out what else is there remaining on this line that we should do. It is important to make sure that the object that is returned here is cast down into the game object. Object on its own is way too ambiguous. We have to make sure that it's being cast down to game object so that it can be received by the variable instantiateDCube, just like this. We've been talking about casts in the previous lesson, so make sure to check it out. It's very important. Once we've removed this kind of ambiguity and made sure that our result on the right is a game object, we can stick it to the instantiateDCube variable. Now we have an object in our scene view that we've created. It's just important to reposition it properly and give it a correct coordinates in space. Let's quickly do this. InstantiateDCube, its transform, its position, becomes equal to, and let's put it slightly to the right of the selected cube, the one which is pointing to our main selection. So selected cube dot transform dot position plus a newly created vector which will translate our instantiated cube slightly to the right from the selected cube. So let's say 2 in x, 0 in vertical axis, and 0 in forward axis. Of course, floats everywhere. putting like this is correct, and it would be just as correct as saying vector3 dot right and times 2. Vector3 dot right is an already created variable, so we don't have to bother about instantiating new structs and wasting our memory. We can just make use of the one which was already made by Unity, multiplying it by 2, because vector.right, just as any other Unity's supplied vectors, are all of length 1. There's also one very important thing left, which I'll talk about and mention in a second, but let's first of all jump into Unity and check out how our things are working. Let's select our cube, and if we press G button, you can see that we stick a new cube to the left of our selected one. Now the problem comes in if, let's say, we select this one and press G, we create 2 cubes now. And why is that so? Let's select this one and maybe move them slightly to the side. Select this one and press G. Boom! Suddenly we create 4 cubes. What the hell is going on, Igor? Well, what we did here is our custom update was registered into the onScene GUI delegate. We added it, but we didn't remove it. And as we are pressing the button and are selecting different cubes, we keep calling the old functions. So just as we did here in void onEnable, we should make use of another function, also supplied by the editor class, which is called onDisable. It's just a single line of code where we're saying sceneview.onSceneGUIDelegate minus equals our custom update function. Now we will not have this problem, and as we create cubes, we won't be creating many cubes. It's just going to be 1 cube per press of a button. So right now we're creating a cube slightly to the right of the selection, and it's alright. But our initial idea was to populate our selection with cubes that are positioned in a radius and in a random position relative to the selection. How do we do this? We are now going to make use of the radius variable, and this task is just about modifying this line of code. Nothing too complicated. Instantiated cube's transformed up position becomes equal to the position of the selection plus something else, some sort of offset vector. And this offset vector has to be of a random length, but not longer than 4f and not shorter than, say, 0.1f. So not too close and not too far away from the selection. And also it has to be rotated, spinned around the current selection. So first of all, let's figure out how we change the length of the vector randomly. And we just do this by saying vector 3 dot to the right, or maybe the forward one, doesn't really matter, because we still will be rotating it randomly. Let's multiply it by the class random dot the function range. Let's apply for the smallest possible value 0.1 float, and for the maximum one, let's make use of our radius variable, or just type in there 4 float. If I jump back into Unity, we will be creating cubes in front of the selected one as we press G at a different varying length. The furthest away will be 4, and the closest will be 0.1. After I press buttons, you see that we create eventually many cubes that fill the range. Now let's rotate this random vector around the selection. And how do we rotate this vector? We have to supply it a special coefficient, a variable by which we multiply this vector. So I'll put times here, and in this space I'm going to supply a coefficient, just in the brackets. This variable might seem difficult, but it's not really anything complicated. We're going to make use of the class called Quaternion, which controls all the rotations and operations with the rotations, and make use of the Euler function. In there we can supply by how many degrees we would want to rotate our vector, that is, relative to the world axis. We can say 30, 35, 32.2 float, etc. But we would want a random rotation, right? So Euler takes 3 arguments, and in the first one we will put random.range from -180 to +180. And that's our first argument. For the y value, the rotation around the y-axis, we're gonna put exactly the same thing, because we want to go to the left, -180 degrees, and maybe to the right, also 180 degrees. And also for the z, that is the rotation around the z, the forward axis, we're gonna supply the exact same thing. And there you go. I'm just gonna press enter so that it's not as crowded, and maybe bring the whole line with the coefficient to the new line. So this coefficient just determines the rotation of our randomly stretched vector. And then this randomly stretched vector is added on top of the position for the main selection, just so that it's relative to this main selection. And then this whole thing is assigned to the position of our instantiated cube. Let's check out our awesome work. And as we press G, we'll be populating our selection with the cubes. And after we perform this many times, it will start to resemble a sphere. I'm just gonna press G and hold it so that it populates everything with the cubes. Because the cubes are randomly generated, it might take some time before we approach and approximate the sphere shape. Also, a task for you would be think about how you can create and resemble the shape of a cube. It is much easier than creating a sphere, and you shouldn't be using any kind of quaternion or anything. Just play around with random.range, and you should be able to achieve an approximation of a cube. As you can see, we've created many cubes, and we begin to achieve a sphere. Literally like several hundreds of cubes already. Hopefully this example showed you how you can control user input using your own editor function, and how you can speed up your process of creation of objects in the scene view. We'll still think about it and use this knowledge to create more complex tools in our following examples. With the knowledge that you've been given so far, you should be able to predict and figure out how to create such a similar thing. Try to imagine how you would do something like that. Which strategies would you use, and how would you shape out your class? My approach is just one of many. In scripting, you can achieve any task via so many different ways. Time remapping and time reversing is an interesting subject, because you can't really do it, you can't reverse time. But you can keep track of positions and rotations as the time progresses for every single item that has been moving. And then later on you can just play back those positions, stored in a list or in an array. We'll be talking about a specific data structure, which we can make use of to efficiently store the positions and retrieve them as well. To control all those rigid bodies and their behavior, we'll make use of a Singletone-like structure, and I will explain what it is in just a second. First of all, let's quickly create a player movement script. We would want to be able to move backwards and forwards, left and right, as well as rotate our camera and shoot bullets or some sort of spheres with colliders and a rigid body attached to them, so that later on we can trigger and hit those boxes, causing their shift and falling down on the ground. Speaking of which, let's quickly create a ground in front of our scene. I'll create a cube, because plane doesn't have depth really, and we need depth for this to work. 30 by 1 by 30, and because it's a height of 1, I will bring it down by its half, so the position will be minus 0.5 float. This will be our ground, with which the objects will be colliding. It will only have box collider, because it's a static physical object. It will not be moving, but it will be able to reflect objects and be sort of rigid ground, stationary one. That's why we give it collider, but don't give it rigid body. I will also create a game object, the cube, and let's call it block. So I'll right click on the name and we'll rename it to block. To create a prefab, I'll quickly drag it from the hierarchy into the assets folder. Let's create a resources folder as well. This follows the previous example shown in this lesson. Let's store everything in there. I will also create a bullet object. You can select the sphere and press F2 to quickly rename it. Now actually, I forgot to attach the rigid body to the cube. So I will go here, add component, and stick a rigid body. I'll do the same for the sphere. The mass of the ball shall be big, I'd say like 15 kilos, and the mass of the cube will be just 1. They'll be all using gravity, and they will not be kinematic. I'll explain what kinematic means later on, but we've covered this in previous lesson as well. Now if we select the block, it has the rigid body, but the block prefab doesn't have it. That's why we will select block from the hierarchy, and since it's tied with the prefab and we've inflicted a change upon it, we can either revert this change, meaning that the rigid body will be removed, so that the instantiated block is exactly equal in parameters to the block prefab, or we can apply the change, and that's exactly what we want. So we are overriding the prefab tied with this block. And now if we select the block prefab, it will have the rigid body, and all the consecutive blocks will have it as well. I will store the bullet as well, into the prefab by just dragging it here into the resources folder. In the assets, we want to create several scripts. And first of all, let's create a movement script really quickly. I will call it mover with a big M up in front. I will also centrate on my camera by pressing F, and we'll bring it slightly upwards. This is going to be our player. It's just going to be one single object. We're going to be inflicting rotation and changing position of the camera, and that's exactly what mover script will be doing. During the start, I will really quickly lock the cursor by saying cursor.lockState, which is an enum. Therefore, it has to be picked from the cursor lock mode enum variables, and we need it to be locked. So now our cursor will be locked in the middle of the screen and will not be moving. I will also set it to invisible, so cursor.visible becomes equal to false. That all happens during the start function. Now, before we do anything else, just to make it clear, let's drag our mover script onto the camera, because this script is going to be affecting the camera movement. We only need one script, so make sure that it's just one single copy of mono behavior attached to the camera. My camera doesn't need any kind of flare layers, because there won't be any flares shining into the camera. It's just an example, and it won't need audio listeners. If you want to have sounds, then you will need this component, but I don't require it. So now with this script attached to the camera, we can keep on working on it. And it's nothing difficult. We are literally replicating the script from the previous 8th part. We'll quickly transform and apply the changes in movement to this camera in a standard way. Once again, if you're not familiar with what I'm doing right now, make sure to check the ending of tutorial number 8, when we were moving our monk backwards and forwards, left and right. Every single update, we are translating our game object by some amount, perhaps 0 in all axes, but if we have any kind of input, then the 0 will be substituted with the variable provided by the input. If we're pressing the forward button, it will vary from 0 to 1, and we also multiply it by the change in frames, so that we are not dependent upon frames. We're also stretching this movement by some factor, a factor of 10, so that we move quickly, and we're doing this relative to ourselves. Later on, when we will be rotating the camera with the mouse, we want to be moving forwards relative to our camera. So if we tilt our camera downwards with the rotation, by pressing forward, we'll be moving kind of downwards because we're moving towards ourselves. We would also want to rotate our camera every single frame depending on the input that we get. First of all, if we're moving our mouse horizontally, we would want to rotate around the vertical axis. That's why we supply this argument as a second argument, the Y argument. We don't want to rotate currently around the Z-axis, which would be clockwise and counterclockwise rotation relative to the screen or the camera. And right now, I don't want to rotate up and down as well. This will be done on the next line. This rotation, leftwards and rightwards one, is performed relative to the world space. That means no matter how much our camera is tilted downwards, we are still going to be rotating around the vertical world's axis, preventing our camera from being tilted and getting lost in space. This problem was discussed in the previous lesson once again when we were moving our character. We also would want to rotate via the axis which sticks to the right from our camera, that is our local right. That's why we're rotating in a cell space relative to the camera, to the object that this script is attached to. And our first argument corresponding to the rotation around the x-axis, our right axis, the local one, is depending on the mouse Y input. We want to be looking up and down, rotating around the rightwards axis, as we're getting input, the vertical one of the mouse. And here obviously we don't put any changes since it has been taken care of in the previous line. We also need to, of course, multiply it by the change in time it took to render the previous frame, so that we're not frame dependent. And having this, we can check for any errors in the console and actually run our game and see how it's working. So yeah, we're getting movement, and we can move relative to our camera. We are not tilting over because we are rotating leftwards and rightwards around the vertical world's axis. Now we'll implement shooting and maybe time reversing later on. Also notice the coefficients, the minus in front of our x variable. If I wouldn't have it, then we would have inverse controls. As promised earlier, let's add a functionality to shoot our spheres forward from us. We'll be doing this if we're receiving an input with the button R, and only when it's being pressed down. That means that if it's being held, it's still going to be regarded as only one single press. As we're pressing button E, we'll be creating a bullet. And for that, I'm quickly gonna prepare the object where the reference to this newly created game object will be stored. It's obviously going to be of type GameObject, so I'm quickly doing the cast, since the GameObject.instantiate function will create an object, but it will be just of type object, which is more general than GameObject. Hence the cast prior to this line. And similar to the previous example, we are using the resources.load function, since we need to receive an argument for the GameObject.instantiate function of type object, which is exactly what resources.load will do. We are asking it to load the bullet, similar to the previous example, from the folder called resources, and resources.load once again returns an object. Here, the second overloaded method requests a string path relative to the resources folder and returns an object. We can stick it here, since this returned object is exactly what's required by the GameObject.instantiate function, this overloaded method. I'm scrolling through the overloaded methods by pressing up and down arrows on my keyboard. So, as asked, we are supplying the object argument into the function, and we are then being returned the object as the result of this whole function. Since we want to store this result in the GameObject type variable, we need to perform the cast, which will shrink down this object into the GameObject type. Now when we have this bullet, let's quickly reposition it towards our camera so that it's created right under us. We will change its position to be exactly the position of the camera, since this is where the script is attached to. All of this was once again done in the previous tutorial. Because we know that our bullet has the component of rigid body attached to it, we can safely refer to it. But first of all, as we create the object, let's create the reference, establish the reference towards this rigid body by quickly searching for the component on the created bullet. So get component, and since this is a generic type function, we need to supply it in the angle brackets the type for which we're searching, which is a rigid body. And we've established the reference towards the rigid body component on our new bullet object. Now, when we want to perform any operation on this specific component, specifically on that newly created bullet, we just have to type RB. There is no need to say created bullet.getComponent over and over again. As we created this object, we want to add a force straight away to it. rigidbody.addForce, and add force is really how you're moving objects with rigid bodies attached to them. It's fine to perform this quick teleportation that we did here, but after that, if you want it to collide properly with objects, you want to really add forces to it. So we'll be adding force, but it requires a vector, and since we're shooting our bullet forward from ourselves, we want to supply a vector that is pointing directly forward from our currently attached GameObject's transform. So from the camera, we would want to grab the transform.forward vector, perhaps multiplied by some big amount, like 4200, float of course. Once again, if you are lost on this line, we're just adding the force to our newly created bullet's rigid body, which will be moving this bullet forward in a physically correct manner. But the direction of this force is exactly the forward direction relative to our camera. That is, where we're looking, it's exactly perpendicular to our screen. That's where we'll be sending our bullet. And we are multiplying it by this amount so that the vector of force is long enough, meaning that the force is quite big. Since our rigid body weighs something like 20 kilos, this force should be enough, maybe not, we'll see in a second. And also, let's say, during the update function at the very end, if we are getting an input with a key code escape, then we should terminate our application. That is application, which is the class available to us since we made use of the Unity engine namespace, .quit, and this will terminate our game. This function is disabled during the editor mode for well-known reasons, but it's going to be available to you once you build the game. And that way you don't have to really freak out that your game is not closing, press Ctrl-Shift-Escape and try to terminate the process from there. just press escape and it will quit the game. Let's quickly test our game and see if we get any errors. Try to remember how I fixed them, so that they are simple for you to fix after that as well. So the best overloaded method match for input.getButtonDown string has some invalid arguments. Because I didn't want to get the getButtonDown, I just want to make use of the getKeyDown. If we make using of getButtonDown, we shouldn't be supplying the enum value here. We should be saying just e like this. But I don't prefer this, and I like really the getKeyDown function, which indeed requires the enum of type keyCode, which we're supplying to it in this form. Save the script, jump into here, and see that there are no errors left. Now, as we are rotating our camera, we can press button E, and this will throw out a sphere. As you can see, it's kind of slow, so we'll increase the speed later on at which it's being thrown out by just, I don't know, adding maybe another 0 here. So 42,000 is the length of our vector. So finally, let's think about how we can create this cube structure and replicate the time remap of our game. Recall that we have block objects in our resources, and maybe let's quickly create a whole thing with blocks. I mean, create a wall or maybe a cube out of those objects. Don't position them too high from the ground, so that they kind of rest on it. If you put it inside of the ground, then as you play the game they will jump out vigorously from the ground. So make sure that there are no collisions prior to the game start. You can always test the game and see how it looks like. Boom, they're being dropped to the ground, meaning that they are kind of correctly positioned, maybe slightly closer to the ground as well. I'll press Ctrl V, Ctrl C, and make sure that you don't press Ctrl V, for example here, without moving them away from their original parents, from the cubes where they have been copied from, since if you forget to move them, when you start the game, they'll be colliding with each other, pushing each other to the sides. So once you've copied, make sure to move it aside so that there are no intersecting objects at all prior to the game start. Now when we've built ourselves a wall, we can really think about creating ourselves a singleton. And a singleton is just a class entity which can only exist in one replica, in one instance. Recall how we've imagined the classes to be some sort of blueprints, that is, instructions on paper of how objects should look like. The operations performed by singleton are similar to static class. That means it's like a core, some sort of entity which should only be in one instance, so that it doesn't duplicate the operations. To create such singleton, we just have to shape out our script that we didn't create yet. So let's right click in here and create a script which we'll be calling block control. Also make sure that the naming is correct, so I'll rename this here into the small o. I'm getting some bug behavior, so I'm just gonna recreate this stubborn script. So once again, the correct casing, block control. This will be our singleton class, which will take care of all the cubes, all their positions, recording and remapping of the time. Right now I'll introduce you to several data structures which can be used for storing the data. First of all, we would like to get hold of all the cube objects, our block objects, that are present in the scene. That's why, in this class, which extends from monoBehavior, we're gonna declare a variable of type GameObjectArray, and actually we'll do it in the start function. So, void start. This function with the proper casing is accessible to us and is recognized by the monoBehavior, since we're extending from monoBehavior class, which described how this function should behave. So during the start function we're going to create blocks and quickly point it towards the GameObject.find, and actually maybe find objects with tag. If I open up the brackets, notice that it will return us an array of game objects. That's why we've prepared it here, and no cast will be necessary. And it requires a tag by which it will be searching the objects, trying to extract the array of correct ones. Well, let's say block item is going to be our tag by which we're going to search the objects. Selecting our block, one of the blocks, which is tied to the prefab, we can create a tag, add a tag, just call it block item. Pay attention to the casing as well of the letters. Press enter, come back to one of the cubes and just tag it as a block item. Make sure that you apply the changes to the prefab so that this change is inflicted on all the remaining cubes that have been derived from this prefab. So click apply, and now if we pick any other different cube, it will have the tag block item applied to it. Let's jump back to our script, and upon the start of the game, we already have an array of our cubes. That is, we've extracted those objects from the whole pile of other game objects. Now we got the access to all the cubes, and we have to arrange this data into some sort of handy structure. If you never heard about dictionaries before, don't worry, because I'm gonna explain to you, since this is our core data structure. A dictionary is nothing complicated. It acts exactly like a normal dictionary would. It has a list of keys, for each of which it has a variable. Assume that we have a data structure called dictionary, which will have two parts. One will be the key, and another column will receive a value. You can think of the key as some sort of ID. And let's say this dictionary will be receiving a string as a key, comma, and for the values it will be receiving humans. As we run our program, let's say we want to throw some different people into the dictionary to store the references to them. In here, the first object will say, okay, we're gonna supply it an Igor, and for the key we're putting Igor as a string, the name, and for the value we receive a reference to the human, and also giving it the reference to the Alex person, also Bob. Bob will be of a green color, just to show that they are different people. Let's say later on that I want to point towards the blue person, and I know that his name is Alex. I will just do the following thing. I'll say dictionary, and in the square brackets I will put the string, the key. I will say Alex. If I will put Igor in here, the result of this line will be the red person, since we've supplied it the key of Igor. And if we want to index, I don't know, Bob, we're putting Bob in here, and this is going to return us the green person. We can also erase or add other items into our dictionary as long as their IDs are different. If we're supplying another Alex, and let's say his color will be yellow, then we're gonna erase the blue person from memory and put a yellow person on top of him. But this is really how dictionary works. And in our mono behavior script, we would want to create a data structure of type dictionary, obviously, which will be holding several keys and several references. To work with dictionaries, we should make use of the namespace located in systems.collections.generic. Now we can make use of the generic types and dictionaries which can hold various types. They are not bound to some sort of fixed type. We can specify our own types of keys and variables that should be stored in the dictionaries. And this script once again will have a variable of type dictionary, and the dictionary itself will be called blocks dictionary. For the key of this dictionary, we'll be supplying the game objects, and for the value, we'll be supplying some arbitrary class that we are yet to make. This class we will call rigid body rotation and trace stack, and we are yet to make this class, so don't panic. I'll explain everything in a second, don't worry. So as we've declared our dictionary like this, we named it, now we need to create it really quickly. So it becomes equal to the newly created dictionary with a key of type game object and the values of type rigid body rotation and trace stack class, which we are yet to make. Now we have this data structure initialized and it's ready to receive the appropriate keys and appropriate variables. In this mono behavior class, I will create another class, inner one, which will be a private class, meaning that it's only accessible within this mono behavior. And guess what? I'm gonna call it rigid body rotation and trace stack. In it, I will have several variables, specifically 3, each one of which will have an accessor modifier of type public, meaning that we are able to access the following variable not only inside of this class, but from the outer class, which is the mono behavior one, and it's of type rigid body, and I'll call it RB. I will also have a public variable of type stack, which will be holding vector3 objects. Stack is also a new data structure that you shouldn't be familiar with, so don't panic. I'll go over this once I complete this class, when we are nearly done anyways. So it will be holding vector3s, and we will call it trace. Just as we did with the dictionary, we've declared it, but we haven't created it. So let's quickly make it available for us to use by saying that new stack of type vector3 like this. And also a stack for rotation of type quaternion, that is not the vector which is used by the position, but the type which is used by the rotation. And this is our class. As you can see, this class is used as a variable in our dictionary. And as we populate our dictionary, for every game object key, we will have a class containing additional information about the position, about its rotation, and about its rigid body. We are yet to populate this dictionary, but it's available for us to use. And it's important that you understand that for every game object that will be placed in there, there will be a class containing all additional information about that game object. Later on, when we want to access this information about this game object, all we'll have to do is to supply this game object as a key to the dictionary. We've just done the most hard part, so trust me, if you understood it, then it's a piece of cake. Now, for every game object, we'll have an instance of this class stored in our dictionary, right? As a variable. And this instance of class will have nothing but 3 variables. First of all, it will have the link to the rigid body of that game object for which this class is held. It will also have a variable with several positions recorded and stored inside, in a data structure called stack. Stack is slightly different to dictionary, and we're also using it for storing different rotations of that game object. Stack is a pretty simple concept. Imagine that you have several papers lying on the desk. You can take out the first one and put it to your right on the table. You can take out the next piece of paper and put it on top of the previous paper. You are then taking this paper and putting it also on top of this stack of papers. Also, you do the same thing with the last paper. Put it on top of the stack. The stack data structure contains elements, and in this case, the first stack of ours doesn't contain papers, but it contains vector objects. Another stack will contain quaternion, but it's working in exactly the same principle. We are using vector 3 objects and we are placing them on top of each other, making our stack grow in size. The stack structure has many functions. One of its most pleasant things that it can provide is the pop function. Once you call this function, you remove the top element from the stack, that is this one, and you receive reference towards it. As you keep calling pop over and over again, you'll be removing other additional elements, getting reference to them in the same manner. The operation of us putting the paper on top of the stack, like this, was called push. As you can see, the stack data structure is quite simple, meaning that whatever you put last on top of the stack with a push function will be the first thing to come out when you use the pop on the stack. That's why the stack is referred to as a data structure of the order last in, first out, LIFO. Whatever you put last on top of the stack will be the first thing to come out from the stack. Just because we're talking about the stack, let's also maybe mention another type, similar type of the data structure, which is called the queue. First in, first out order data structure. As you put objects into the data structure and keep putting them, as you would want to retrieve them, you'll be doing this from the bottom. Coming back to our lovely stack of vector 3s, you can see that for every single game object we'll have this class, which will have rigid body reference of that game object, and it will also have a stack of vector 3 positions, right? And we called it trace. We could have called it, I don't know, maybe position. So that's what we'll do. And we also have a stack of rotations. Why do we want to have many vector 3 positions stored for a game object, you might ask? Imagine the following scenario. You are firing a sphere at your structure of cubes, the wall that we've built here. As the sphere collides with the rigid bodies, they are being awakened and they start to fall down on the ground. At every given increment of time as they are falling, they have their new position and they have a new rotation. We should store this rotation and position as they're falling until they've reached a rest on the ground, so that later on we can scrub backwards through those positions and rotations. So it's nothing really complicated, as you can see. Make sure that you don't confuse the stack data structure with the memory stack. Memory stack is working in exactly the same principle as the stack data structure, and it's literally what our program is working on. You might have heard about the terms stack overflow and memory overflow. You can research about the memory stack, and you'll see that it's different from this data structure completely. It's from different area. So make sure you don't confuse them. And if you don't know about memory stack, don't even bother right now. Also, check this out. We got the start function for our block control singleton class that we are working on, but start function won't work since this is a mono behavior which should be attached to a game object in our scene by hand. But what if we don't want to bother about this silly attaching of this mono behavior block control, let's say to the floor or somewhere else? We just don't want to do it because it takes our time. Well, we can tell Unity to run a specific method specified in this class to make sure that this class instantiates itself on some sort of game object within our scene without us having to do it. And how do we do this? Well, we can quickly create a function. Let's call it void init, standing for initialization. It will not be returning anything, but it will be doing something to the system, hence the void keyword in its signature. We want to grab this script, which is not materialized yet, and stick it on some game object in the scene. But we don't want to stick it on any game object. We want to materialize this script on its own, specifically created for that purpose game object. So we'll quickly allocate the variable of type game object and call it instance game object, which will be holding an instance of this singleton class mono behavior. And immediately we can create a new game object. We don't really care where it's positioned, but for the sake of it, maybe let's bring it to the center of the world. It becomes equal to the newly created vector 0, 0, 0, or maybe just make use of the Unity's prepared vector. Just as in the previous example, we made use of the forward vector. Here we're making use of the vector 3.0, which is the 0th position relative to the world of Unity. Now it's positioned right in the center of the world, and immediately let's give it the name that is how it's called in the hierarchy. Let's change its name to the string which says block control dash singleton game object. And yes, this presumably will create an object, but it will not have this component attached to it. That's why we will say that, okay, instance game object dot add component, and in those angle brackets, which are actually of a generic nature, but in there we can supply a type which we want to stick onto this game object. We want to stick block control, that is this script, on top of this game object. The singleton nature is quite tricky to understand, so I will go over this once again. We got a blueprint, the class block control, which is inheriting from mono behavior, meaning that the script cannot actually perform anything as we start the game until we've attached it to the game object. But how do we make use of this function then? Since this script is not attached to the game object, it cannot do anything until it's being attached to it. And this function is what actually attaches it to the game object. So it's kind of like a recursive, strange anomaly. How do we actually call this function without instantiating this class so that it gets instantiated on the game object? We have to make use of the keyword which was introduced in Unity 5 in the square brackets. Runtime initialize on load method. This function will be called no matter if this class is instantiated or not as soon as the game starts. And for that, the function signature should not only have the void keyword, but it should also be static, meaning that this function can be called from the class without actually having to require an instance of that class. We can call this function directly from the blueprint. There is no need to create an object out of this class to call this function. But this function will be immediately called as soon as we start the game. And in fact, the static should be before the void, because the order matters. So as the game starts, we're gonna call this static function directly from the blueprint, the mono behavior class that hasn't been instantiated yet, to create a game object and create an instance of that class and stick it on that game object. After that, we'll have a game object in the scene sitting right in the middle of the world with the instance of that class. So let's go into console, see that we have no errors, and let's run the game and see if there is a game object created here. Recall that once again we didn't attach this block control to anything. It's really creating an object out of a blueprint and then sticking the instance of that class on top of that game object. Here we go. As soon as we started the game, the blueprint function was called, which created a game object and materialized this blueprint block control in form of an object, the mono behavior, onto that game object. And now it's being able to run the start function, update, fixed update, any functions specified and provided by the monoBehavior class, from which this blueprint extends the class. As the start function is run, we are finding all of the cubes, extracting this whole bunch of references as a GameObject array and storing it in the blocks array. It only persists until the start function exists, so later on we'll destroy the references to those GameObjects as soon as the start function is finished. And before it's being destroyed, let's make sure that it's being stored somewhere else, so that GameObjects themselves are not leaked into the scene, meaning that there are no references to them anymore. As we extracted the references towards those blocks, let's quickly populate our dictionary with them, right? Since that's what we require. For every single GameObject block, we would want to put it into the dictionary and also create appropriate class ready to hold information about position, rotation, etc. for that GameObject. We're going to iterate through every GameObject in our blocks. So for each GameObject in our blocks array, and we get an error here because for every GameObject, let's say B in blocks. That's the correct syntaxes. So for every GameObject in our extracted blocks into our dictionary, the blocks dictionary, we want to add the following thing. As you're adding something, notice the signature. We've specified our dictionary to hold a GameObject as a key, that's why it's here being specified as a key, and also for the value, we'll be providing the instances of this class. So for the key, the GameObject should be the GameObject B, which should be accompanied by the instance of this class, since every single object will have this class paired with it, according to our signature of the dictionary. Because it has to have an instance of that class, we have to create an instance of that class. This means that we are iterating through all the GameObject in our array, and for every GameObject in this array, we are adding this GameObject and its newly created instance of the rigid body rotation and trace stack into the dictionary. Since we've changed the variable to position in here, I'm also going to rename this class quickly to position stack, just so that it's easier to understand. And now, by the end of the start function, we've iterated through all the elements in this array, and all of those elements have been paired with their newly created instance of class, having those three variables, position, rotation, and rigid body, which can then later on be accessed whenever we want to. Because our wall consists of 12 objects, as the start function is ran on the singleton, we will have 12 entries in the dictionary by the end of this for each loop. It might seem that I'm going over the same thing again and again, but it's very important to understand, and I want to ensure that nobody's left behind in this lesson, so forgive me if I'm repeating myself. Let's also debug a message for ourselves, just to say that the singleton's start has finished and we've populated the dictionary. And let's say the dictionary's length is spacebar, close the string, and let's concatenate to it the length of the dictionary. Because dictionary is coming from a generic namespace, it's a little bit different to arrays. It doesn't have .length variable, but it has a .count one. We want to concatenate the count of the dictionary. As you can see, .count is the integer type, and since we are concatenating it, meaning that we are putting plus after the string, it's going to be immediately cast down into string and converted into string. We don't actually have to bother putting toString function at the end of it. But if this would be before the string in here, then this method would be necessary to put, since the compiler wouldn't know that we are working with a string. But if we put it after the string, it's already assumed, and it's going to perform its transformation into string by default. If you want to add two numbers, then you would have to put it in the brackets. And this is what got me some time ago, and I couldn't understand what the hell was going on. This will actually add 1 and then concatenate it to the string. But if you put it like this, at the end you'll have the string, the count of the dictionary concatenated to it, and then you'll have letter 1 stuck on top of this string. But I'm gonna get rid of this unnecessary one. And we're gonna jump into Unity, check that we have no errors, and make sure that you remember which errors are here and how I fixed them. So rigid body rotation and trace stack could not be found. Let's double click on it and see where it points us to. Oh, and yes, remember how I changed the naming of this since we changed this variable here. Well, I did change it here, but I forgot to change it here. And also, as we're creating the new dictionary, instantiating it, we should also supply it here. I'm just gonna put the comments on the new line. Jump back into Unity, no errors. Let's start the game. Notice that the game object is created. It is being placed here. And we've populated our dictionary. It has a length of 12 because we got 12 cubes. Every single one is acting as a key for the dictionary, which is tied with a value being represented by the instance of the class, rigid body rotation, and position stack. So every single game object in the dictionary has its own instance of that class. It just comes down to two more functions, and that's it. The functions will be the record and the rewind one. They'll be of type void, since they won't be returning anything, but they'll be doing something to the system. And also void rewind. The record function should be ran by default. It's going to be storing all the positions of the cubes as the time progresses. We're going to iterate through every entry in the dictionary and do something upon it. Once again, we're going to make use of the for each loop. We're going to say for each entry in this dictionary, which was called blocks dictionary, do something. But those things in the dictionary are pairs of things. They contain a key and they contain a value. This pair is considered as an item through which we can iterate in our dictionary. This item is nothing but a key value pair. The key value pair, and in the angle brackets we're going to say which key value pair. Well, our dictionary contains several key value pairs of game objects as the keys, and the values as the instances of that class, rigid body rotation and position stack. So for each key value pair, which has game object as a key and rigid body rotation and position stack as a value, KVP, that is how we're going to refer to each key value pair, we're going to refer to it as KVP, we're going to do something. Because we're recording, for every pair like this, we would want to store the current position of its game object into the rigid body's rotation and position stack positions variable. This is quite difficult, but bear with me. KVP dot value dot position dot push, and in there we want to push the position of the game object belonging to this currently inspected KVP, the key value pair. Since the game object of this KVP is the key, we're gonna say KVP is key dot transform dot position, since this is really the game object. So we are pushing the transform of the game object of this KVP into the rigid body rotation and position stack instance of that KVP. And this is performed for every single entry of this dictionary. By the end this function is finished executing, we're gonna iterate through all the entries in the dictionary, meaning that all the instances of classes will be updated with the new position of their corresponding game object. This was really the hardest part. If you understand it, then it's a piece of cake. We're gonna do the same thing because position is not enough. We wanna say KVP dot value, so we are really jumping into the instance of that class for the KVP. And now we're interested not in position, but in rotation variable, residing in this class. Because it's a stack, we can also make use of the push function, which will place the rotation, the current new rotation, on top of the older ones. And we want to grab the rotation, the current one, of the corresponding game object. I'm going to put kvp.key, just as we did previously. So we've jumped into the corresponding game object of the currently inspected kvp. .transform, and let's have a look at the rotation. The rotation variable belonging to the transform component of that game object. We want to run this function every iteration of the physics update. That's why we are also going to introduce the function called fixed update, the one we've discussed in the previous lesson. I'm really counting on you being familiar with those concepts, since we are really going into the hardcore stuff now. Make sure that you know what fixed update is prior to starting this lesson. During the fixed update, let's just run the record function. Now, as we're starting the game, let's check that we got no errors. This will fix later on. And as we start the game, we are creating the block control singletone game object. We are attaching and materializing our singletone behavior on it. The start function kicks in. It creates a dictionary which contains pairs of items. For the key of that pair, it has the game object's cubes. For the values, it has instances of the class containing positions, rotations, and other data for its own cube in that pair. As we're running the game, the fixed update is ran by the physics engine, and it's running the function called record. The record function iterates through all the pairs in the dictionary and updates, steals the position, the current position of each key, the game object in that pair, and stores it in the value of that pair. And it iterates through all the pairs. So by now we have huge stack of positions and huge stack of rotations for every single game object. Those huge stacks are growing in the instances of classes for those game objects. But we would also want to rewind the system. So for that, let's introduce another variable. It's going to be of type boolean, and it's going to be public. By default, it's going to be true, since we want to be recording initially. Let's quickly maybe say, okay, if recording is true, then run the record function. Otherwise, run the rewind function. But else if it's kind of boring, let's do the switch. We're going to be switching based on the recording variable, and we're going to have two cases. Case when it's true, break, and case when it's false. When it's true, we're going to run the record function. When it's false, the rewind one. At the moment in the recording function, let's debug a message saying that we are recording. And in the rewind one, you guessed it, we are rewinding. Even though this is public variable and we can change it in the inspector, let's change it as we press the button on the keyboard. That's why in the update function of this class, and we can use it because it derives from mono behavior, in the update we're going to check if there is an input and we are getting the key down with a key code, let's say R for record and rewind. If we're doing this, our isRecording variable going to become the opposite of what it was. Exclamation is recording. Once it's being triggered in the update function, it changes. Fixed update is gonna glance at it and run the according function during its iteration. Each function has its own message, and our record actually already performs so much information on our data, but we're just interested about the messages. Expected symbol, so probably I forgot a bracket right here. Let's run the game. Created our singleton, and as you can see, we are recording message in the console. Pressing R, we are rewinding, pressing recording, rewinding. As we are recording, once again, we are iterating through the pairs and updating the stored position, copying it over from the real position of that game object in that pair. Okay, now it's the final thing, and we can rewind our actions. Once we are rewinding, we just need to iterate through the game objects in our dictionary and plug the positions, brutally just change it from the real position into the stored one. So for every key value pair, KVP in blocks dictionary, we want to do KVP, its key, that is we're pointing towards the game object now of that pair, its transform and position becomes equal to, well, the top of that position stack in its corresponding class instance. The key value pair dot value, since now we're pointing towards the class instance, position dot pop, because this is our stack of vectors, and pop is going to return and remove the top element from the stack, allowing us to reference it. So we are pushing and squeezing out the top variable and immediately grabbing it by the position of the corresponding game object of that pair. The same thing happens for the rotation, so I'm just going to quickly grab this. I'm going to say the game object, its transform, its rotation becomes equal to the, well, the class instance, the rotation stack, and we're going to pop the top value from there. And this is going to work now, but it's very dirty. One thing that we should do is make sure that as this function is ran, that we don't run out of stuff to pop from the stack, because otherwise it's going to be null, and position cannot be null. So only if the class's instance, the position, its count, because it's a stack, is greater than 0. Otherwise don't bother. And that way we're ensuring that as we run this function via our fixed update relentlessly and iterate through the things, and pop out the positions of the objects and rotations, we won't run out of them and we won't get null in here. Now there is going to be some anomaly that's going to happen, but we're going to fix it later on. The main structure should already be working. As we fire our bullet into the scene, you can see that we are firing our cubes and they are recording their position. If we press R, you can see that they start to fly backwards into the correct position, and boom, right in the correct place. This anomaly happens at the moment because we didn't turn off the rigid body, and we're gonna fix this in a second. So I'm gonna start to record, fire the bullet, hit a couple of boxes, and then press R to rewind backwards, and they're gonna get in their initial position, erasing the stack, popping all the entries from the stack of position and rotation. As you could have seen, once we started to rewind, we got them in the correct position, almost. But then they fell down, ruining the whole thing. So as we are rewinding, the rigid body of those game objects should be put to sleep. That means that no physics calculations shall be done on that game object at that stage. So we're gonna say kvp, the instance of the class, this one, and we want to access the RB variable, the rigid body of that game object. Because we're accessing the rigid body now, we got the access to all the function, and the one of interest to us is the sleep function, meaning that it will sleep for at least one more frame. So we're sending the rigid body of this game object to sleep until the rewind is finished. But notice that the rigid body is going to be only placed to sleep if there are still things left in the stack to pop out. If we've already reversed all the cubes back into their normal position, where they started from, and there are no more additional positions to pop out, we're not going to put our rigid bodies to sleep, and this is bad. So we should really put it before the if statement. Let's run the game, fire the bullet. Every single cube gets its position recorded and rotation as well. But as we press R, we're saying that there is a null reference exception. There is no object pointing to the variable. And why is that so? Well, as you can see, by accessing the instance of the class and referring to rigid body, we're expecting to point towards the rigid body of that game object. Since this is what our class has been made to, it has been paired with a game object. But remember that very back at the start, when we were populating our dictionary with game objects and classes, we just instantiated the class. And in the class we're saying that as soon as it's initialized, yes, create the position and rotation stacks, but we don't point rigid body to anything. And this is bad. Really, there should be a constructor for this class. And now it's time to make it. So there will be a constructor, the default constructor, public constructor, which will take 3 arguments. It will take the rigid body type variable called R. It will get the vector3 position pause and the quaternion rotation. As we are creating this class, this function will ensure that the variable RB becomes equal to R, and it will ensure that the variable position becomes equal to pause. The variable rotation grabs the supplied value of rot. Because we're initializing the stacks here, you can safely assume that indeed this line of code, the initialization and declaration of variables, runs before the constructor. This is the order in C#. So first we're creating variables, and then the constructor is immediately ran, and we assign the variables. But oops, of course this is incorrect, because position cannot become equal to the vector pause. Instead we can say push, since this is a stack. Careless mistakes like this will result in several errors thrown at you. This is a rotation stack, and we can push the supplied rotation. Now we've established the reference to the rigid body of the game object, but this is not it yet. As we're creating the class, when we're populating our dictionary, it requires 3 arguments. If I open up the brackets, obviously it requires the rigid body, it requires the current position and the rotation of the game object. Since we are iterating through the game object B in our extracted blocks array, for that game object, as we are placing it into the dictionary, for that instance of the class, we want to supply the rigid body of our game object B. And rigid body is no longer accessible via the shortcut .rigidbody, but now you have to make use of get component just like you would be getting access to any other components. So rigid body. For the second argument of the construction for this class, we've said that we want to get the position of the game object, b.transform.position, and b.transform.rotation. Rotation is of type Quaternion, as you can see, rotation Quaternion, which will fit into this slot, and everything is going to be fine. Now we've populated our dictionary with pairs containing game object and containing the instance of class, which already knows about the rigid body of that game object, its current position, which is being placed into the stack on the first place, and also the rotation, which is also being pushed into the first place of the rotation stack. And now as we press the rewind button, we are indeed able to call this function, iterate through each key value pair, and put the rigid body of that game object to sleep. We won't get any null reference exception since the rigid body actually contains the link to this object. It's being established as we are populating our dictionary for the first time. We get the error here, and that's because we forgot to put obviously the round brackets here. So get component, angle brackets, type, and then round brackets is the correct syntaxes. Running into Unity, we can see that we are recording in the console. Press E. Every single cube has got its position, rotation being recorded. As we press R, we begin to extract them backwards, and the rigid bodies are sleeping, as you can see, and boom, perfect in place. As you can see, while I'm still firing, because we're still rewinding, this creates a problem. Now I can press we are recording, and obviously when I pressed it, it's now going to be our initial position of cubes because our stacks didn't have any variables left in their possession. So as we fire the objects and press R, they're going to be restored back into this kind of hectic position. To fix this, it's really simple. We want to make sure that as we're rewinding, when we run out of things to push away from rotation and position in all the game objects, and literally don't move any single game object in this iteration, then we are safe to assume that we finished rewinding. We can do it by introducing the variable of type boolean and say none moved. Initially it's going to be true, and let's say as we're iterating through items, some of them might have already no more things to pop out. We keep iterating through the pairs, and boom, some of them still have something to pop out. We perform this instruction, and then because we've moved at least one object within our dictionary collection, we should say that none moved becomes equal to false, and it's going to remain as such until the whole rewind function is over. But because it's now false, we're going to block ourselves from an instruction. But if it was indeed true, we can put it like this, or just say just that, because it's a boolean type variable. If it was false and for each didn't actually manage to move any cubes in its iterations, then we can safely put our isRecording variable to true, allowing the fixed update to pick it up later on, check it, and then since it's true, it's gonna just do record now. Rewind is no longer gonna be ran. Now, we are recording really nothing. As you can see, if we start the game and wait for like 10 seconds, recording, and then fire the bullet, inflicting the change, as we are pressing the rewind button, we are going through the stationary positions. When it has collected itself, it still has got those 10 seconds of not doing nothing in the beginning until it begins to record again, just like I did a second ago. And now we are recording. We're gonna wait even longer, let's say like maybe 12 seconds or so. Start to fire, still recording, and rewind. Okay, back in place, and still rewinding because we've been waiting for 12 seconds. Still waiting, and then stacks are depleted, and we get recording. We should not be really recording, running this function, if our rigid bodies don't move, that is, they are sleeping. So we should just introduce one minor check here. Only perform the push into the stack if the rigid body of the object is not sleeping at the moment. That is, the object was moving. So kvp.value, because we want to access this instance of class, if rb, the rigid body component of that game object, is sleeping, it's a function, and it returns true or false. So we only want to run the following two lines only if it's not sleeping. So we're going to put exclamation mark here, or just say, okay, does not equal to true, or is exactly equals to false. But I prefer shorter notation, so I'm going to put exclamation mark here. And of course, curly brackets, grab our lines of code and stick it here. So we're only going to record and only going to push stuff onto the stack if the currently inspected cube, if it's a rigid body, is not sleeping. When we run the game, notice that the cubes are going to pop downwards, finding their rest, because currently they are suspended a little bit. And this is going to mean the change in position. So our stacks will always be populated with this minor change, but that's okay. So we are recording, they came to rest. Even though the message is running, it's just running because it's inside of the function. The iteration doesn't really push any position or rotation onto the stack for each of the cubes at the moment. If we fire the bullet, we're recording, and now we're rewinding. Notice how quickly the recording will start. Boom, recording immediately. And we can fire again, recording, boom, rewinding, and back into place. It's still not perfect though, and that's because some of the rigid bodies are colliding with each other. Even though they are sleeping, they can still inflict a change on other rigid bodies. Therefore we have to set them, the rigid body, to kinematic as we are rewinding. And if none is moved, that means that no change in the cubes has been performed as we were iterating through them. We want to set them to false. However, we cannot really steal this line since it's dependent on this for each loop. We should iterate once again through the key value pairs of the dictionary, and then we can say kvp, its value, rigid body, and then say that it's not kinematic anymore. This block of code will not be executed as long as there's at least one cube that has moved within the dictionary. This is important to understand. And as soon as all of them are no longer moving, that is, we've depleted our stacks and there is nothing else to pop out, then we can safely iterate once again for the last time through the whole dictionary, just to set all the rigid bodies to be no longer kinematic, meaning that they can be pushed by other objects, the physical objects. Let's rewind. They're jumping up a little bit, and that's because we are beginning to populate and push variables into our stacks as soon as we begin the game. As you can see, when I start the game, they come to rest, and this is a change in motion. Our rigid bodies are no longer sleeping at that moment, and because they're not sleeping, we are actually recording this minor jump in the beginning when they come to rest. This can be fixed by performing the following thing. We can just delay our building up of the dictionary and everything, delay by literally a fraction of a second. Then we are guaranteed that all the rigid bodies came to the rest, and we can start to populate dictionary with the correct blocks that are already rested and are not moving. This will be done by extracting this code into a coroutine and starting it literally 2 seconds after the start function kicked in. So in there, we would establish the reference to the dictionary and everything. And meanwhile, before this delayed function would even kick in, the update would already be doing its dirty job. It would be running the record function and rewind one, which are nothing complicated. By that time, when they are already ran, even though we still haven't populated the dictionary, it's already there, and we don't have any entries in there, so we're just not going to be running this for each loop, and we'll be terminating our functions right here immediately. As soon as we populated our dictionary with variables, then this thing would be run. But we're not going to be bothered by actually delaying anything. Instead, we're going to say that as we are populating our dictionary with the rigid bodies, we're going to say before that, the game object's rigid body should actually sleep from the very start. If you want to be really, really neat, you can say, okay, rigid body R becomes equal to get component rigid body, and then just say, okay, r.sleep, so that we don't get two get component function calls. Just do it once and then reference it like this. But this is a very neat way of doing it, so we've already done so much mistakes probably that it doesn't really matter. Because our rigid bodies are sleeping from the very first second as we start the game, this means that they're not going to be actually moving. And as the update function is ran, we're not going to be populating and pushing the variables of position and rotation onto the corresponding stacks, since the rigid body is actually going to be sleeping. It's not going to be falling down to its initial rest. In addition to that, we can also say that if no objects were moved during our rewind function, not only do we set the kinematic variable to false, but we are also putting the rigid body to sleep. Doing this is not enough. Try to figure out what's going to happen in a second and why the following error will occur. I'm firing a bullet and I'm pressing rewind. All good. Back in normal position. We are recording, but we're not really pushing anything on their stacks because the cubes are sleeping. But if I fire once again and press rewind, they're not going to really come back to their original place. Now, what is happening here? Really what you've done is you've told it to sleep immediately after none was moved. And none was moved only if all the cubes have exactly the count of their stacks at 0. If it's at 0, then you're sleeping. And since you're gonna go into record function now, because well, is recording is true now, since none was moved, record is gonna check and see that, well, the rigid bodies are sleeping, so I should not do anything, and I'm not gonna push anything on the stack. And this first frame, the initial frame, is lost forever. In order for us not to push, we first of all have to be sleeping, or the position or rotation stack, doesn't matter because they're all of the same size, has to have the count exactly equal to 0. So if we're not sleeping, or if we are sleeping, but the instance of our class, its position stack has a count at 0, then we should push one entry. And now it's gonna be fine. No more silly popping, and all the variables are being returned back to their normal place. This is really cool. And if you understood this lesson, my sincere congratulations, because this is quite an advanced level. And if you understand it, you're going to be able to understand other important concepts like Quadtrees, binary search trees, which we are about to start building. One final thing you might be interested in doing is when you're firing the bullets and they are all splattered, you press rewind and press R again, and they hang in space. You might like this effect, but if you want them to drop down and begin recording again, you just need to add a line of code here, just setting it to no longer be kinematic. As you fire your game, check this out. They start to fall down. And then if you press R, they're going to be brought upwards and then back into the original place. Boom. Epic. When we're talking about working in Unity, we're thinking about manipulating objects, spreading them in the scene view, renaming them, scaling, moving, rotating, putting scripts on them. But most of this is done manually, by us literally going and dragging the objects into the scene and sticking all the required components on top of them. If you want to automate this process, you are highly welcomed. The way Unity was constructed allows us to build extra tools on top of its main core. It provides us opportunity to incorporate our own extension methods into it. They are called editor scripts. There are two ways to experience Unity's power. It's either when you play the game or when you work in the editor mode. As a designer, you'll spend most of the time obviously in the second option, in the editor mode. So you want to add extra functionality to it. Editor scripts allow us to modify the look of the items in just one click of a button or a key on the keyboard. And it also allows us to modify the inspector view or open our own windows with our own custom layout and buttons. Because creating a window is much more handy, I will explain to you the basics of it, so that later on you can learn on your own how to expand it further, but I'll give you a nice basis. To create a window, which you can dock around into your layout, you have to create a C# script in the assets folder, or any folder that you desire. You can call it whatever you want. I will name mine tutorial 9 window. Of course, remember that there shouldn't be any spaces in the name. Just use the camel case notation. You don't have to place this script, even though it's from the editor nature, into the editor folder, like I told you in the previous tutorial. If you are interested in what folders are reserved by Unity, you can go into this address and read about specific folder names as of Unity 5.0. Those are pretty much all the folders that you shouldn't be using as your own custom folders, because they have a special meaning behind them. Usually if you'd be writing the editor scripts, you'll be placing them in this folder. However, in our case, when we're designing the Windows script, we can place it anywhere we want. So let's open it in order to improve it. Just by default we get this layout, which we can get rid of, because we're going to be creating not a mono behavior, but a different class. Since we want to make an editor window, we have to make use of Unity Editor namespace. Because we've included it, now we will be able to inherit from the editor window class. I highly advise you to go into Unity's API and check on all of the available functions provided with the new class. In our case, editor window, so I'm gonna search for it. Here's the way it's working, and if you're interested in the real API, just type in Google editor window API Unity. There you go. You have a nice example and also the list of all the variables and functions which you can invoke, and we'll be talking about some of them so that you get the idea of how it's working. Pretty much when you're describing this class, you are explaining what any particular window should perform if it's being called, hovered over, you name it. It should have several functions, and especially the init one, initialization. Let's go into the documentation and search for the init function. We can in fact copy it from the example as it is, and I'll explain to you what each line means. So we got a comment here, and the following function will be invoked as soon as we will choose the appropriate option from the menu item in our Unity layout. It's because we're inheriting from the editor window, and this notation, square brackets, menu item, round brackets, the name of the option, means that whatever function is after this little tag or whatever you call it, this function will be called as soon as you press this option in here. Because the name of our window is going to be tutorial 9 window, we should place the type of the window to be tutorial 9 window here in the cast and also in the type of window which should be produced. So it's already too much information. Let's go into Unity and see that indeed now we get under window tab my window option, and believe me, it wasn't there previously. So if you click on it, you get a window because we've ran the initialization function, this one. What happened here is that we're saying there should be a window of the type of our class, this particular one. We're going to make use of the editor window and either obtain a window or create it if it hasn't been yet made. It's a static function, as you can see by its signature. Hence we are making use of it by calling editor window class and getting the window. Here we have to supply it the type of the window. Notice the notation here. When you see this option, you should always make use of the type of keyword and supply the type of the object or the parameter that you have to supply. And which type should we supply it? It should be the tutorial 9 window, since we want to either find such window, the tutorial 9 window, or create it if needed. So editor window, and we can make use of the static function getWindow, which requires the type of the window that we want to get. And in itself, this is not enough. If you check Unity right now, you'll get an error message saying that you are not able to convert editor window to tutorial 9 window. This is because there should be a cast in here, because as you can see there is a undefined type here, just the same as the argument. You have to supply which kind of output you're expecting. We are waiting for tutorial 9 window reference. When we receive the reference to the window, this thing on its own is not enough. If we want to see this window, we have to highlight it, and since we called it window, we can call a function from it by saying, well, our window dot show. Show is a function provided by the editor window class, and since our created window is of type tutorial 9 window, which inherits from this class, therefore we can use this function on such windows. Anything that we specify after this is going to be the implementation and different functionality which each of our windows will expose. I almost forgot to mention that you can access the API and the scripting reference and the documentation in Unity, even in the offline mode when you got no internet, by going into Help option, then picking Scripting Reference. As you can see, this URL is pointing to your local destination on your computer. It's not the internet. And of course you can pick between which language you prefer to use, although many of the deep and hardcore subjects are at the moment written in JavaScript, so-called Unity script. But the big core is written in C# as well. Once again, we're working with the editor window, that's why we will search for it here. We've already implemented the initialization function and exposed it as the menu item, our window. Another function which is very straightforward is onGUI. Because its responsibility is to draw elements and different toggles onto our window, we can throw different GUI layout items here, such as labels, sliders, boolean ticks or buttons, and they all will be displayed in our window over here. So every window that we create will have this functionality, this method, because we're about to specify it. There are several classes from which we can retrieve the elements that we want to place into the area for our window. They are the GUI layout, editor GUI layout, or editor GUI layout utility. Many different classes, but the main difference between GUI layout and, let's say, GUI class is that GUI layout places the items one after another one, and you don't have to hard code their position most of the time. So it's more flexible. You can begin the groups, like for example begin horizontal, and then until you finish the horizontal, you can stick buttons, sliders or whatever. They are all gonna lie nicely and divide the horizontal space evenly between each other until this horizontal group is finished. So when you rescale the window, your buttons will be rescaled as well. That is the characteristic of GUI layout, or any kind of thing that finishes with layout. Different functionality that we required is scattered across several classes dedicated to GUI. We will look at them, don't worry. In this simple example, I want to demonstrate you how quickly you can create a tool for populating your scene with objects. Imagine that you got a terrain, which is not the Unity's provided default terrain, but it's just a mesh with a mesh collider. For instance, let's create a 3D object, a plane, or maybe for our sake, let's create a cube. I will scale it up to about 30 by 30 by 30. In this case, it has got a box collider, but if your mesh would be of an irregular shape, you would stick a mesh collider, of course. Now, we want to build a tool, an extension for Unity, such that we can stick around this cube elements, such as rocks or grass, whatever, by just clicking and placing them on its surface. We don't want to manually drag the items onto the scene, reposition them so that it looks like they are sticking on top of the cube. We just want to click on the screen, placing the objects exactly where they have to be. I'm thinking about sticking a button onto our window, which will have a name, for example, stick objects onto the cube. Remember that any functionality like this, creating buttons, sliders, whatever, to be shown on the window, has to go into onGUI function. For now, we're gonna make use of the toggle or the tick. So instead of picking editor GUI, I'm gonna go for GUI layout, because I don't want to be hard coding the specific positions of the items, such as buttons, sliders, whatever, on my window. I just want them to rearrange themselves automatically. And from there, I want to make use of the toggle. When I open the brackets, you will see that it has a boolean return type variable. So when we tick it, the result will be true, and when we untick it, the resulting thing that it produces will be false. It also requires the value to show and extra parameters. The function itself has 6 different overload methods, but we are just interested about the first one. This is a very interesting notation if you haven't seen it before. It might trick you into thinking what's going on here, but you have a toggle, and at every single specific frame of time, it has a value to display. For example, if I declare at the very top a variable of type boolean, call it a, make it false. Then we'll create a second one, b, and set it to true. Because this is a function, as you can see here, it requires a value and a set of optional parameters. The boolean variable that we're going to supply to it, the argument, I'll drop a into here. But since this function returns something, this something has to be assigned to another variable, which has to be to the left of this function. So b becomes equal to the result of this toggle. Because toggle received a value of a, When you read the documentation, you will see that the toggle will be displaying A all the time, assigning the resulting value to B. So immediately, as soon as we open our window, onGUI will begin running and B will become false, because the variable here holds the value of false. But if we do something tricky, for example, make B the result of the toggle which displays the value of B, then we'll be able to assign and change the value of B. We can dispose of A because it was just for demonstration. Also in the same function, let's debug the value of B so that you can see what's happening there every single frame. Because we've already got the window running, we can open the console. As you can see, when I untick it, we got some messages here which are not showing because I didn't press this button. So I'm gonna tick it, and we got now messages, many of them. Right now B is false because it's unticked. And as soon as I click in the window area, you can see that the GUI function kicks in about 100 times a second. But when I'm hovering my mouse somewhere else, in the scene view for example, working there, the GUI function is not running. It still updates the window a few times a second when I hover over the window, but its main work happens when I click on it and do something in there, like drag around or drag my mouse and click inside of the window. So when I press and make our toggle true, you can see that B is now true, now it's false, and so on. On the contrary, once again, just as in the case with A, if I was to apply a constant value of true into here, then no matter how much we try to untick or tick this box, it's always going to have a tick inside of it, and B is always going to be true. Here you go, I'm trying to untick it, but because it's displaying the value of true and immediately assigning it to B, there is no way for us to change it, unless we display B as well. Once this is out of the way, we can create a functionality which will allow us to press on a button, and as long as it's pressed, we can draw objects on our cube, placing them and instantiating them from prefabs, which is exactly what we need. We will make it very rough, and we'll do fancy stuff like changing button appearance, etc. in the very end. I will change the name of my variable B to something more sensible, not to confuse you. Place objects, for instance. And of course we'll change it here. We also want to create a slot for accepting different game objects, which we can then instantiate around our cube on its surface. This slot will be accepting game objects and will be storing them in our internal variable, which will be declared aside of the place objects in the very beginning as well. It will be the object to instantiate. Because this is a GUI layout, if we make use of this class, the toggle, the slot and everything else will be positioned aside next to each other in a nice manner. So right after this line, I'm going to assign the result of the following instruction to the object to instantiate variable. Just to be safe, because it's of a type game object, I'm going to immediately make a cast to the game object so that whatever comes out on the right side will be immediately cast down into the game object and safely assigned into this variable to store it for later. Instead of getting the toggle, this time from editor GUI layout, we're gonna access the object field. Inspect carefully the description of its function. It returns an object, and my assumption about casting down the result to game object was true, because otherwise we wouldn't be able to assign the object to our game object variable. But with this cast, it's safe. And it also requires the variable which it has to display, similar to our tick. So it will be displaying whatever is currently in the object to instantiate. That way we can modify it, similar to how we did it with our toggle. The type of objects which it will be able to accept, and notice that it's system.type, so we have to make use of our newly introduced keyword, the one that I've introduced just a second ago. Type of, and in there we're going to supply the game object type. The third argument will be whether we want to allow the user to drag the items from the hierarchy into the slot, or they have to come directly from the project window here. Why not? Let's allow him to drag it from the hierarchy into the slot, and here we can supply whatever we want to if we desire. But we're gonna leave it like this, check for any errors, and I don't think we have any. If there would be errors, they would be placed in the beginning. So instead of scrolling upwards, you could have just unticked this button to hide all the messages and just show the warnings or the errors. But we got nothing here, and right now we're able to control one Boolean variable and retrieve the object, which we can later instantiate around our scene. To update the view of this window, we can close it and reopen it. Pretty big slot, and it looks alright. If we look into the documentation of the editor window class, you can see that the functions include the one which is called update, which runs also 100 times a second. So if you would be implementing your editor GUI into onGUI function, drawing all the sliders, ticks, etc., here you just put general stuff. Notice that there is also onSelection change. That is, if you select different objects, this function will be called. It is the so-called callback. On project change, when the window loses focus, so for example you switch to a different window. On destroy, when you close it. On inspector update, or when something happens in the hierarchy. On inspector update happens when you change something inside of this panel for any object. But if you want to add your own custom callback function, which is ran also 100 times a second, you can do it in the following way. I'll quickly Control F and search for onEnable function because I know it exists here. And in here, we want to add our own function as a callback so that it's called 100 times a second. The function will be called void custom update, or for example onScene GUI, whatever you want to call it. I will call it my custom update, or just the custom update function. And inside of onEnable, just access the scene view class, which is available to us because we're using the engine, because we're using Unity engine namespace and Unity editor. And from there, go into onScene GUI delegate and attach, so plus equals to, attach our function to whatever is already there. Notice that I'm not placing the round brackets here, just this part of its signature, the custom update. However, let's say that onEnable happens quite a few times. You will suddenly notice that your custom update receives much more attention now. And let's say if you perform any kind of input check or event processing like mouse clicks, keyboard presses, you'll see that it happens twice, 3 times, 4 times. It's all because of the way you've attached this function. We're just adding it to whatever is there. But the safe way to do it is to first of all subtract it from this delegate. If you subtract a function which is not yet attached to this GUI delegate, you will not do anything bad. It will shrug its shoulders and say, well, fine, you want to subtract a function which is not attached yet to me. I'm not gonna freak out and will just ignore this function. But the good news is, if there is already a custom update attached to it, we're not gonna have a duplicate, because first of all, we'll remove the old call, and then we'll add our new one. It's a rusty way of doing it, but it's a steady and a guaranteed way to ensure that you will only have one copy of this function running at any time. So now when we've notified the scene view about its GUI delegate, anytime we do something in the scene view right here, it will be running our function dedicated to a particular copy of our tutorial 9 window. So all of this hustle with the custom update and adding it to the delegate was because we're gonna process all the events just in this function. All the GUI is gonna go here, all the events are gonna go here. If we want to record any kind of input from user, such as for example mouse press. After joining our function into the delegate, if we jump into Unity, you will see that there is an error in our console. Let's look at it closely and see what it means. A method or delegate which emerges from our tutorial 9 window class, it is called the custom update. This is the method where the problem is. Inside of it, the parameters, the things that go inside of its round brackets, do not match the delegate which emerges from Unity editor namespace, scene view class, onScene function, and the parameters which emerge from Unity editor scene view. So basically, our custom update function, as you recall, didn't receive or be intended to receive any parameters, but the delegate to which we are assigning this function requires our custom update to have a different form. The custom update should be able to receive the variables as an arguments of type scene view. To quickly fix this error, of course we're gonna make use of the scene view class, specifying the type of the argument which will be supplied into this function. We'll call it C or SV, doesn't matter. We're not gonna make use of it, but if we would be, we could. To make it slightly more clearer, as you can see, it emerges from Unity editor namespace, and even though the error disappeared, the scene view comes from Unity editor. As you can see here, editor window, scene view, just to follow the convention. Now it's perfectly valid, and we can attach this function to onEnable. We did similar stuff in the beginning of this lesson when we were cloning our cubes in the editor class. To retrieve the event of a mouse click, keyboard press, etc., we first of all have to create such event, and the variable will be of type event. We will call it e, and we'll point it to whatever is currently specified in the event static class. So event.current. We're pointing our e to reference whatever is happening at the moment. Mouse press, nothing, keyboard press, mouse drag, whatever you desire, any kind of input. And every time this function is run, we can check if event is something that we require. For example, if our event e, its type, you can see that it's of type event type. So if its type is exactly equal to event type and it's an enum, so dot, and we can pick whatever we want from the range of provided options here. If the type is mouse drag or mouse click, let's go for mouse drag. Or if the type is exactly equal to event type, just for the sake of it, let's go for mouse click. So mouse down. But this is not enough. Even if we press the middle mouse button, the right one, the left one, we're gonna trigger this check. But imagine that we wanna place objects when we left click on our mouse. So if this condition is true, if we dragged the mouse or clicked it, to follow this we have to also check with the right side of this statement if the button from our event type variable is exactly equal to 0. 1 would be the right mouse button. If you're working with keyboard presses, you could go for key down and then check the key code to be, for example, key code A, left shift, alt, etc. But we're working with mouse, so if any parts of this statement is true and the right statement is also true, then we're gonna perform something, and in particular instantiate a couple of cubes or a couple of objects on the surface of our cube. Some of you might be surprised to hear that this OR statement has a higher precedence than the AND statement. If, for example, A and B and C or D, then even if this is false, this is true for example, and this is false, as long as the right side is true, it's gonna run the code. Pay attention to the order at which you want to check your commands. If you now place, for example, a bracket here and separate this statement, if A is true and B and C is true or D is true, then it's gonna run the block of code. Pay attention, and it's very important not to mess this up. Here it doesn't matter. Once we got the input from the user, the left mouse click, let's perform a raycast. Obviously we're gonna be clicking somewhere in the scene view here, and I'm gonna centrate on my cube. We're gonna be clicking here somewhere, and we want to detect the point of our click and transform it into the world space, because right now we're clicking on the flat screen. We're going to be raycasting a ray from our screen, which is a flat plane, outwards into the perspective of our virtual world, converting this ray, which is coming out from the point of our mouse, into the three-dimensional representation, adhering it to the rules of perspective. So anything that we collide our ray with is going to be stored into the raycast hit variable. I will call it hit. Now we can perform any kind of raycasts, and just as I explained to you in the beginning of this entire lesson, we're going to be making use of our out keyword, so that even though the function returns true or false at the end, it's still going to perform direct changes to this variable, and not to any kind of copy it would be creating inside of its working area. So if we're getting the result of something, and in particular our raycast, then we will instantiate our objects on the surface. Of course, because we're making use of the raycast, it's coming from the physics static class, therefore we don't have to have an object to call raycast. We can call it directly from physics. And 12 overloaded methods, plenty of room for you to improvise. I'm gonna go with 4 options. This one in particular. Ray, which has an origin and the direction, as opposed to a segment or a line, which would require you to specify 2 points in space. But here it has a ray, the variable where to pack all the information if something was hit. It of course goes in pair with the out keyword. The maximum allowed distance of our array, how far should it fire before it vanishes. and against which layers do we want to cast our array and which ones to ignore. So to create an array, we can either declare a variable of type array and specify the origin and the direction. Instead, I'm gonna make use of the function which converts the click on the scene view viewport into the world space, just like I promised. Such value can be produced by the result of the function, which can be retrieved from the camera class, the current camera, the function screen point to array. The result of it will be array from the screen coordinates into the world space, touching our cube somewhere when we click onto our screen. This function requires a vector, the three-dimensional vector, the third component of which will be always 0. Read the summary. It returns an array going from camera through a screen point. The coordinates, of course, will be either x, which is the horizontal screen coordinates, or y, which are vertical ones. It requires a vector, so we'll create a new one right on the fly. For the first argument of the vector, which is to be plugged into this screen point to array function, we're going to supply the current mouse position. And how do we get it? We can retrieve it from our event variable here, e.mousePosition, and mouse position is a vector too, as you can see here. So we can retrieve x and y variables, as well as set them, but we want to retrieve them. So for the x component of our vector, we're going to retrieve the x variable, and of course we're creating a vector 3. For the y component of this vector, e.mousePosition.y. For z, as promised, 0. Now we've fulfilled the requirements of screen point array function because we've provided it the vector as an argument. It's sitting right here, and it's based also on the coordinates of our mouse. For my more advanced audience, yes, there's a slight misconception here. We will return back to the statement because at the moment the coordinates are inverted, but don't bother your head with it. We will return to it in a second. Right now, the coordinates that we supplied here are correct, and we're gonna get a vector sent from the camera from our point on the screen. Coming back to the raycast, we've supplied the ray, but we also have to supply the variable where to pack the information into here, so it will be out hit. The distance, I'll put it to be math_f.infinity. This class is provided by Unity with those namespaces, so infinite ray. And the layer mask is which layers do you want to ignore when you're raycasting an array into your world. Let's say that we pick our cube and we assign a layer of with the index 8. I will create a layer called cube, the layer 8 one. We'll pick my physical cube object and assign it a layer of cube, the 8th layer. Back in here, for the layer argument, the layer mask one, which is an integer, it has some tricky notation, so I doubt that you can put just 8 here. To be correct, we will go into layer mask class, then we'll make use of the static function nameToLayer. Notice that there is also layer to name, which returns string. Here we want to supply a string of cube, because that's what we've called our layer. It will be converted into the integer form and fed into this last 4th argument of our raycast. This is the layer which our raycast will ignore. However, we want to do something opposite. In fact, we want to cast our array only against this cube and nothing else. So to invert this selection, we can put a tilde character, which is to the left of your 1 key on the keyboard, above your tab key. Press shift and drop it into there. This symbol inverts the instruction, and now you're no longer ignoring the cube layer, but the cube layer is the only thing you're casting your array against. All the other ones are ignored. If you want to cast against multiple layers, do a research about bit mask shifting and bitwise operations, because this is what layers are tied about. Since it's tied around those bit operations, there is a clear reason why you can't create more than 32 layers in here. But that's another story. Now we've sent an array directly from our screen into the world, that is the raycast function returned true. We can create an object. And which one do we want to instantiate? Well, it's gonna be the object which we've plugged into our slot right here in our onGUI function. We can plug whatever we want to. Spheres, capsules, our custom objects, trees, rocks, you name it. So as we are creating it, let's grab reference, the game object type variable, which will be assigned to the newly declared variable of type game object called placed object. Of course, it will exist until this if statement is not over, and then it will be erased. I've covered this many times. If you didn't understand what I talked about, you can check out the previous lesson, part 8. So we are creating an object and we'll be referencing it until this if statement is not over with this variable later on. To create an object, we can in fact instantiate whatever was plugged into here, for example a sphere or whatever you want. But because we're working in editor and creating an extension from it, it would be wise to check out where sphere is originating from, grab the prefab and instantiate an object from the prefab, so that later on, if you click your mouse on the screen, all the objects that you are instantiating are going to be created from the prefab and will have the direct blue connection to their prefab. They're not going to have the orphan behavior. All of them will have a prefab standing behind them. So for that, I'm going to make use of the prefab utility class and will instantiate a prefab. I cannot plug the object to instantiate, our variable of type game object, which corresponds to the game object plugged into the designated area on our window. I mean this one. Instead, the instantiate prefab function says that it requires an object type variable. What it means is it wants a reference to a prefab. Prefabs are sitting in the project panel, not in the hierarchy. So just dragging an object from the hierarchy or from the panel into here is not enough. We grab the reference to the object, to the game object, but not to the prefab. We have to retrieve such prefab from the reference of our game object. Hence, I'm going to click on the object to instantiate variable and we'll extract the prefab out of it. The result of that operation will be the link to the prefab, which can immediately be used by this instantiate prefab function. I will once again make use of the prefab utility class and we'll get the prefab parent based on our object to instantiate variable. Because object is standing higher in the hierarchy than the game object, we don't have to make a specific direct cast from game object into object, because object is higher in the hierarchy once again than the game object, so it's implied. The result of the prefab utility getParent, as you can see here, is object. That is the link to the prefab of that game object. And this result, the object, can be immediately used by instantiate prefab function, which also requires an object. The result of this function, you guessed it, is also object that has to be cast down into game object, since there is a variable on the left of type game object. Game object is sitting lower in the hierarchy of and in the structure of C#, hence we have to cast down object into game object, which we do here. I hope I didn't complicate it too much. But now we got the reference to the game object finally, we've created one in the world, and it has the link to the prefab. But we still haven't positioned it properly, didn't provide it rotations or scale if we wanted to. Where are we gonna position it? Well, it's exactly gonna be intersection of our ray produced by the raycast with the layer cube. And this intersection point and all of the required information, such as the normal of that point of the surface, or the game object, the collider, they are all stored in the hit variable here. So I will reposition our newly created game object by accessing its transform and just roughly teleporting it to hit.point. That's exactly the coordinate of intersection of the ray with the surface. If you would be going into hit.transform, for example, that is the transform of the game object with which the ray collided, .position, you will be referencing the pivot point of that game object and not the point of intersection. To get the latter one, use hit.point. That's exactly where we want to stick the pivot point of our placed object. Let's also maybe fiddle around with the scale. Transform dot and there is no scale, but there is local scale variable, which should be altered. If you inspect it, it's of type vector3. So we will create a new vector into the arguments of which we will supply 1, 1, 1, or actually we can make use of the Unity's provided vector in this case, vector 3 dot forward or upwards, whatever. They're all unit length vectors of length 1. And after it, we can multiply it by the coefficient so that the scale will be equal in all directions. And I'm gonna multiply it by the random factor. So random.range, explained it many times, so I'm not gonna bother now. From, let's say, 0.5 up to 2.0. And of course, since we're working with decimals, we have to specify that it's a float by placing the f character at the end. In fact, I was a little bit silly when I specified vector 3.forward, because in this case, forward is what? It's 0 in x, 0 in y, and 1 in z. So our local scale will be 0 in x, 0 in y, and maybe 1 in z multiplied by some coefficient. It is a uniform vector, but for our case, it has to be 1 in all directions. So really, sorry about this, we're gonna scrap this call and really create a new vector with 1 in each component. We can perform this multiplication, and even though this is not a vector, it's gonna perform a component-wise multiplication. It will come up with a value, which is between 0.5 and 2, and we'll be multiplying it consecutively to all of the components, the x, y, and z of this vector, and then the whole thing will be assigned as a local scale of our created spheres. We can finally test our window in Unity by opening the window. In fact, even if we close the window, because we've registered our function to the delegate, which belongs to scene view, even with a closed window, this function will be running. So it will require a couple of additional checks for you to see if the window is opened or not, or maybe you can do it just in the update function if you desire. Having gone into GameObject 3D Sphere, I've created one for ourselves in the hierarchy. We have to create a prefab for it. We can achieve it by simply dragging it into the project panel. I will rename it to something more fancy like Igor Sphere. Now those two things are tied together. We can, of course, drag our prefab from the project panel into the slot here, or maybe do it from the hierarchy because of the way we've specified it in here. This line has the argument true, which means we can assign game objects directly from the hierarchy. Notice the interesting thing. If we drag and assign the reference to the object in the hierarchy, if we get rid of this object by pressing delete, we'll get rid of the reference to that game object in our window because we were referencing this object, and only when we're raycasting do we grab the prefab. So when we're left clicking, creating the ray and intersecting the surface of our cube, we're going to be looking back to this particular instance, the Igor sphere, grabbing the reference to the prefab and instantiating a new copy of this prefab on the surface of our cube where the intersection occurred. I was talking about this and saying it to my more advanced viewers just a moment ago. Here's going to be an anomaly. Notice what's going to happen if I left click on the surface of the cube. The controls will be inverted. Clicking at the bottom of our cube, notice the sphere has been placed over there. In fact, I'm going to change the color of the sphere and need to create a new material and stick it on top of the current one by going to materials, plugging our A instead of the default one. Now I can change the color to, let's say, a bright red and set the emission to be white or bright red. Now I can see it clearly. Because we can't dispose of this particular physical object once again from the scene view, because of this I'll move it aside by just dragging it by the slider here. Since as soon as I left click on one of the arrows, I'm gonna begin to raycast instead. Moving it aside, clicking on the bottom, we're creating spheres here, but clicking on the top, we're creating spheres closer to us. To avoid this, we have to invert the controls. When we're starting to cast our ray, we're converting the screen coordinates into the world ones, and the X is okay. As you could see, moving left and right was okay, but up and down motion has to be changed. If you try to debug the values, those ones, you would see that they're quite big. They're not from 0 to 1 range, like if we'd be working with a viewport point to ray. Here we're working with a screen point to ray, hence we have to subtract the current coordinate from the following one. Camera The current one, it's pixel height. I will place everything else on the new line. This Y argument is now inverted and can be comprehended by the screen point to array function in a correct manner. Now when we're clicking on our cube, we can see that the spheres are placed exactly under my cursor, exactly where I want them to be. But our drag doesn't work, and didn't we provide an option like this? Shouldn't we be able to drag our cursor and stick spheres in a trail? Well, if I left click, you can see that Unity takes over this event and starts to draw a rectangle. To avoid this, all we have to do is after we've processed the event with our custom update function here, after our if statements or whatever, right before we finish our raycast, when it's successfully intersected with the cube, we have to just put one line of code, which is e.use. E is our event, and we're using it so that it's not propagating through the internal functionality of Unity. We made use of it, we consumed and ate this mouse click. In addition to this, we have to make sure that whenever we draw, the user is in the view mode. If I pick this hand button, I can finally draw a trail on the cube, of course populating our hierarchy with a huge number of objects. So you might want to add the functionality where you can select the range and then group it by pressing the button on the window of your editor script. But that's a different story. If you are a dedicated viewer and already tried to build this system, you will notice that putting the argument like so, the one concerning of layers, produces a strange anomaly. When you are left clicking into the scene view, you can see that we are populating it with the spheres, and if one of your spheres happens to have a collider with it, doesn't matter which layer it is, even if it's not a cube, the ray will collide with it and will create a trail like this, since every time we're gonna hit a new sphere, the point of intersection will be on that sphere and not on the cube. This is not really the proper way to specify the argument of layer. Once again, research into it, but the correct way to do it would actually be to specify an integer, let's call it layer, and perform a bit shift operation like this. We can now plug the layer into this argument and see how it's working. Now we're casting just against this layer. If you want to experiment with it further, you can add extra sliders to modify the scale of your spheres based on those values. Set random rotations based on maybe ticks, and also check for the distance between the previously placed object, you'll have to store a reference to it in your script, and the potential new one. And if the distance is greater than the set one, then you can place an object. That way you can set the scatter distance for your game objects to hold. If you want to make use of event class and event type variables, you have to make use of the function which receives this argument and plug it into the delegate. This means that even if you close the window, this function will be ran. So it's your responsibility to make sure that you inbound the entire code inside of here into the if statement to see if the tick is pressed or not, and restrict any further computations, because the function will be running at least 100 times a second. As well as that, final word is if you declare a variable of type list or generic dictionary and try to initialize it somewhere here, it's gonna throw an error at you, especially when you start Unity. That's why all of the initialization has to either happen inside of onEnable, or your variables have to be static and be initialized here, being shared by all the windows. Actually, if you check this out, when we're creating spheres here, you cannot roll back this action, because we didn't register the creation of them, even though we instantiated them. This is one of the pitfalls of working in Unity Editor, but of course there is an easy way to do it. There is just one line of code which you have to do. Since we want to roll back the creation of the sphere, we have to register it after we've finished working on it into the undo class, which Unity neatly prepared for us, which is register created object undo, plugging our placed object, and since the function requires the argument of type object, once again object sits higher in the entire structure of language than the game object. We don't have to perform a cast here. And the second argument is the name of the operation. I'll call it undo sphere. Now, when I'm creating spheres into here, if I go into edit, I can undo the last sphere. Or actually, Unity is very clever. It groups objects based on the input that you're providing to it. Let's say I'm clicking on the mouse button and I'm creating them. As long as I'm not releasing my mouse button, this is all considered an entire group. I can press Ctrl Z and all of them will be removed, since it was a single dab, a single stroke across the surface of the cube. I'm very happy for this. Otherwise, how many have we created here? About 20. We would have to press Ctrl Z 20 times. So it's very smart, and definitely look into the undo class, because you can do much more than that. You can actually assign transforms to objects, since you can't actually register the changes performed on this component. Instead, if you want to record it, you would have to assign a transform via the function provided by undo. So anyways, look into it. You can record objects, record created objects in order to undo them later on. It's a great fun. Check it out. As a continuation of the previous example, it's very important to learn about recursion, since I will be using it in my future explanations as we begin to work with data structures. You can see recursion in many manifestations of nature, in the patterns on the sunflowers, in the mirrors when you position them one in front of another. You can easily find it in maths when you calculate factorials. And it's nothing more than a self-recurring pattern when an entity falls into itself and produces something. It is very important that you ensure that your recursion is not infinite and that you terminate it at some stage. Otherwise, it will take up as much of resources as it can in order to complete its never-ending task. However, really quickly, before we do that, I want to show you a little improvement in my previous work on our script, where I've changed the appearance of the tick, and even though it's still regarded as a toggle, it's now seen as a button in our window. This is a very simple change. All I did was I omitted editor GUI layout class and derived our toggle directly from GUI layout static class. As a third argument for this function, I have to type in the way it should look in the editor. If I omit it, it will be just a simple tick. But here I specify that I want a button. There we go, we had a button there right in front of us. Also previously, because our object to instantiate was of type GameObject, even though our function allows to take the objects from hierarchy and plug it into this slot, because the object is of type GameObject, if we attempt to plug in the prefab into that slot, we wouldn't be able to instantiate it, unlike if we would drag in the object from the hierarchy. That's solemnly because when we try to instantiate such object, prefab utility would grab this reference, the object to instantiate, and would attempt to grab the prefab out of it. That would totally work if the object would be in the hierarchy, but if it would be the prefab placed from the project panel into this slot, it would be already a prefab, and it wouldn't make sense for Unity to grab a prefab for that prefab. So I made a slight change, and now our object to instantiate is of type object, no longer the game object. The editor GUI layout object field returns an object, and instead of the cast to game object, I shortened it down to object, or I can just even omit it because the function returns object. Object to instantiate is of type object, and down here, when we've hit something successfully with our raycast and we'll instantiate an object, I first of all make a little line here and try to grab the prefab from the object to instantiate, casting it down into game object. So if it would be the prefab, it would be cast down into game object, and we would try to attempt to get the prefab parent from that thing, but since it's already a prefab, we would get a result of null in here. The parent that is anticipating this result is of type object, and assuming that here we got a null, because this slot received the prefab from here, assuming this, it will be null, and as we are instantiating the prefab, we are checking, is our parent null, meaning that we plugged into the slot the prefab, and if it is, then we should use the object to instantiate, since it's already a prefab. Otherwise, if the prefab would exist for our object to instantiate, the one that was plugged into here, If the prefab would exist, then we should use this prefab. So either way, here we are creating a prefab and storing it into the placed object, the newly introduced variable. After that, it's just simple instructions that you've seen already. So in short words, plug an object into the slot, doesn't matter now from where, from the hierarchy or directly from the project panel, and treat it as an object, the vague thing. Later on, when we attempt to create something out of it, we first of all check if it's a prefab itself, then we instantiate spheres directly in the viewport based on this prefab. Otherwise, if the prefab was found, that would imply that here was plugged the game object that would be already present in the hierarchy somewhere. Using that game object, we would extract a prefab and then instantiate the prefab in the scene. Now let's talk about recursive stuff. I want to create a tool to expand our window to let it have a second button, which will be instantiating prefab copies of whatever is plugged into this slot, but recursively. As we'll stick a sphere on the surface of this cube, I want this sphere to immediately place two smaller spheres right in front of it, where those smaller spheres, in their turn, will also create two even smaller spheres in front of them. And you guessed it, even smaller ones will also create even smaller ones, and so on. That's a recursive behavior. I suspect it will only require us to write one additional function, which will be quite simple. But first of all, let's stick another button into our window. For that, we'll introduce a new toggle, which will be of type boolean, and I will call it place objects recursively. It will be false by default, since the button shouldn't be pressed. Our first button should also be false by default. I will correct that mistake. And in our custom update, I've made a little guard that we will only create our single sphere, the object from the slot, into the world on the surface of the cube. So even if we got the input, nothing will happen unless the button was pressed. Let's instantiate this first big sphere on the surface of the cube no matter what, even if we pressed the first button or the place objects recursively one. We will still send the raycast, and if it hits something, we will instantiate spheres on its surface, on the surface of the cube. And even though I've introduced the place objects recursively toggle, I should of course introduce the button to flip it from true to false. I will duplicate this line in onGUI function, and after the slot for inserting objects, I want to work with the place objects recursively now instead, and inside of our toggle function, we'll be working with the same variable, place objects recursively. It will be called with the same name, as well as will have an appearance of a button. Here it is, and it stays pressed because we have a toggle variable prepared. So even if this is pressed, or the place objects button is pressed, we'll be instantiating spheres because of this improvement introduced here. After we've created a sphere and registered it with a group of other spheres, because remember that Unity groups objects with undos based on the input. When you've been holding the mouse button, all of them will be grouped in one group, and you can Ctrl-Z all of them at once. After we've modified the position and the scale of this sphere to be on top of the intersection of the ray with the cube, we want to add its copies in front of it in the recursive manner like I've explained to you before. Let's introduce another function after our custom update. It will be void because it won't return anything and will be called createSmallerDuplicate. As an argument, it will take a reference to any game object in our world, parent, and also position relative to parent. That is, it will be of type vector3 and will be amount by which we would like to shift and position this new duplicate aside from its parent. As well as that, let's do the scale. So vector3 duplicate scale, how big it should be. After we've placed the sphere where we want it to be on the surface of our cube and changed its scale to the appropriate size, we will invoke this function, plugging our newly placed object, or we know that it's going to be a sphere, as an argument. In this function, it will be regarded as a parent. The second argument will be how far away from the parent should the duplicate be. I want it to be to the left of parent, but if the parent itself is very small, then this change in distance should be small as well. So it will be the placed objects dot transform dot forward plus the placed objects transform dot left, or maybe negative placed objects transform right. But that's more confusing, so we're going to be using left instead. It in itself is going to be 1 unit forward and 1 unit to the left. It's not considering the size of this parent sphere yet. To do it, let's multiply it by the placed object. It's transform.localscale.z. Of course, the same thing should happen to the vector signifying its leftwards direction. And this line is getting out of hand. It's pretty big. So I'll just bring it to another line somewhere before here. And we'll assign it to a vector 3 displacement. Still quite big, so we'll bring its second half to the other line as well. That's our displacement, slightly forward from the placed object and slightly to the left of it. In fact, we see that left highlights with red here, and yeah, placed objects.transform.left doesn't exist because there is forward, up, and right variable for us to use. There is no left one. So we just put minus in front of here, and the problem is solved. Placed objects.transform.forward is the unit length vector, so it has the length of 1. And so is this one, the place object.transform.right, is also of length 1. When we're looking from the perspective of this placed object, its right vector is exactly 1, 0 for y and 0 for z as well. But we cannot use this vector on its own, just plugging it here, because that would be relative to the world. But our sphere might be rotated, and we want the displacement relative to the sphere's rotation and position. So instead we're using the right variable. Looking from the perspective of the world, this right vector is most likely not going to be the right vector for the world itself. But for the sphere it is, and it's also dependent on the sphere's scale. The smaller the sphere is, let's say half of its size, the rightwards vector, its x, y, and z components will be all scaled down by half as well. That's exactly what we want. However, imagine that there is a sphere and its scale is going to be 1, 1, 1. I'm not too sure, but I'm afraid that the duplicates, when displaced by this variable, the displacement, are going to be hiding inside of the sphere, inside of its surface. So I'm tempted to put a coefficient here somewhere, or another term on top of which we can add this value, but I will not do it right now. We will see in a second. We got our displacement, and we can plug it into the create smaller duplicate recursive function as a second argument, and the duplicate's scale is going to be, let's say, half of the parent. So placed object.transform.localScale, it has 3 components, x, y, and z. Let's divide this vector component-wise by 2. So each of those components is going to be scaled down exactly by half. We've declared the body of this function. It now accepts the parent, the position of the duplicate relative to this parent, and the duplicate scale, but it doesn't even create them yet. So we should introduce this functionality. Inside of here, because we want to create a game object, instantiate it, I will declare a variable of type gameObject. We'll call it duplicate, and we'll use the class gameObject.instantiate based on the original, which is our parent, supplied to us. Here's the trick. If in here we would not be sure if we plugged a prefab or the game object from the hierarchy directly in the slot, if we wouldn't be sure of that in here, as we come into those 2 lines, we are accessing the prefab either directly, if it was plugged in the slot, or get one, if the slot contains a game object. And then it's materialized in the form of game object. So when it's passed into the recursive function as an argument, it is the game object. We know it. So we instantiate it like this. And now we have to reposition it, the position relative to parent, as well as set its scale directly like this, because it was pre-computed as it was supplied into the argument of the function. It's still not recursive. The function itself is just ordinary. When we instantiate a sphere by clicking on the cube, this sphere will invoke the function as well, creating a little copy in here. If we call it now twice, create smaller duplicate once again afterwards, and of course if for this call the displacement was correct, here we have to modify it before we call the function a second time, because now the second duplicate has to be positioned to the right of the parent. It all just comes down to removing this minus. Notice that once again you might be tempted to say that displacement x variable becomes equal to displacement's negative x variable, thinking that you would be just altering the x value. But remember, vectors are relative to the world, all the information that we supply here is relative to the world. From the world's perspective point of view, the vector might not be to its right, but it is to the right of the object for which we are working. So scrap that, it's incorrect. We should really come into here and alter the insides of the command which creates this final displacement vector. And then it can be supplied into here, as well as we can supply the same scale of the parent. Now we will have two spheres, one to the left and one to the right of the sphere. We can introduce the recursive nature of the function in just one line of code, but it's going to break Unity if you run it. Add it, but don't try it out yet. After we've created the duplicate, reposition it where we want it to be, and change its scale, from the same function before it finishes, we'll call it again. This time, the parent will be this duplicate. The second argument will be the position relative to this duplicate. So I will just do the same thing over again. Vector displacement, duplicates transform.forward, based on the duplicates transform local scale. Duplicates transform.right, based on the duplicates transform.local scale. Well, if we're not scaling it uniformly, we can leave it as z, but since it's right, I want it to be affected by the scale in the local rightwards axis of the duplicate object. So I'm going to change it to x. And the same thing actually has to be the case for the placed object, the big first sphere as well. So forward based on the z, and the right based on the x. For the second call, the rightwards direction is also based on the x-axis. So really, after we've created this duplicate, we're invoking this function over again, supplying the duplicate as the parent, this newly introduced displacement vector as the position of its own little child to the left from it, and the scale will be the duplicate's local scale, of course divided by 2. And since the duplicate has to have two children also, just like the big sphere, we'll alter the displacement vector once again to have the rightwards direction relative to this duplicate. This code will break Unity, so don't try it. The pattern will be such that this big sphere creates the left object with this call. This function begins, creates the duplicate happily, and then calls itself once again. Now this duplicate will start this function, create its smaller representative, and then start this function once again. This new function will also create a duplicate, also to the left of that duplicate, and it will continue forever. Of course, we keep getting this huge luggage behind of us, where we have not processed yet this line for all the previous parents of duplicates. But it will never get there. It's sort of falling into infinity. And even if after some time it would be able to get out of it, then here it will also fall into infinity. There has to be a counter after which we should stop actually falling into this recursion and fall out of the function, coming back from the previous calls of the parents, starting to work on the second branch. So in here, in the window, we should actually introduce a slider or maybe the integer field of how many iterations do we want to go through as we are creating objects. It's very simple. It will be concerning the variable of type integer. We'll call it iterations, and we'll set it to 1 by default. As soon as this function is called, we want to subtract from the iterations the global variable declared on the top, 1. So I'll just do minus minus. And then we'll check if we're allowed to call other instances of this function by seeing if iterations is greater than 0. If it's greater than 0, then we advance further, creating a duplicate to the left of any given duplicate, and it also subtracts the iterations. Now, it keeps going to the left, to the left, to the left. Eventually, iterations become 0, and that particular instance of function, somewhere very deep, we'll see that it shouldn't execute its copy of this code, will fall out, giving a chance for the previous calls of this function to resume working. This means that the previous function will see that, oh, this copy of me is finished, now I can proceed with working with those guys. But suddenly, when we start to work on the right branch of the function which is right before that dead end one, that function will begin, but it will see that there are no iterations left since we've wasted them on the left branches. So really, after this function is over, as we begin to work on the right one, we should bump up the iterations by 1. And if you think about it, it will give the chance for the recursion to work on its right branches. Now it's perfectly valid and we are done. Let's just see that it works. And of course it doesn't work because we didn't introduce the integer field, which is very simple. Inside of onGUI, right after our button, we want to be setting our iterations variable to whatever is the result of the editor GUI layout dot int field. We will be displaying the iterations, and additional parameters we don't want any. In fact, we might use the second overload of this function, which requires the label to be specified as the first argument. There we go. Now we've got the iterations to be able to get picked. Let's put 3. And if we click and create spheres, we do get this recursive behavior. But if you see that, first of all, it creates the left branch, comes back, bumps up the iterations by 1, comes to the right one, bumps up the iterations by 1, and then when it comes back, the iterations is at 1 at the moment. It has the chance to make the right branch, but then this right branch has no iterations resource to work, and that's because even if we add the 1 here right after our first call to this function, after the second one, the right branch is over, we don't bump it up, and we should be. Don't forget that you should adjust the iterations to the appropriate amount. So let's put it back to 3 or maybe 5 now. And now it does create this amazing pattern. Look at this, oh my god. It does have this problem where it doesn't reproduce the last row. That is because inside of our very big parent, the first sphere which initiates all of this recursive process, we do call create smaller duplicate recursive function twice, here and here. But after the first time it's ran, we don't bump up the iterations after it's being ran. But the function itself does something similar, and it does bump up the iterations after the second call to it has been over. So we should reproduce this action here and bump up the iterations before and maybe just afterwards as well. This is just a formality, but if we bump it up here as well, after the second call, when the big parent initiated this whole thing, the iterations won't be falling downwards by 1 as we are creating objects. So 5, 5 again, and just for the sake of it, let's try 15. Unity was freaking out for a little bit, and it created a very big number of objects. Look at it, so many that my Unity just freezes almost. And they're so small that I can't even see them. It's really cool. I'll try to focus on one of them. And check it out. So many small children that I can't even see the end. Do try to make a copy of this script if you want to. Work with me, of course. And you'll be surprised. It looks quite cool. Prior to us understanding what data structures are and how can we make use of certain algorithms in our projects, we first of all have to understand the time complexity concept. How long does it take something to execute a given task, and in which terms? Time complexity is a measure which evaluates the speed of algorithms, but not in seconds or minutes. Instead, we evaluate the algorithm in terms of numbers of actions that have to be performed to achieve a certain task, based on the number of input elements, or maybe other input things, such as actions, etc. So what is it exactly? Well, for instance, imagine we have several numbers in an array, like 9, 8, 7, and so on. And that's an array. We got 9 elements, which are sitting on the corresponding cells within an array. 9 is sitting at the cell number 0, 8 is sitting at the cell number 1, 7 on the cell number 2, and so on. Let's say that we have to sort this array such that the first cells of an array contain smaller values, whereas the further we advance to the right across the array, the greater the values are. Basically, we have to reverse the order. It might be simple just looking at this. Simply change the order from where we count in an array, and that's it. Which is done in just a snap of fingers. It's like one action. When we simplify it down and exaggerate a little bit, we can ultimately achieve it in just one action, which means an order of a constant time. And we put order, this is the big O notation, and in the brackets we put 1, constant time. Just pretend for now that we don't know that we got a perfectly descending array of elements. And we still have to make sure that we start with the smallest element and end up with the biggest one, with all the intermediate elements being placed at the correct position. In that case, we would look at the first element and compare it with its right neighbor. If it would be greater than its right neighbor, we would put 9 instead of 8 and 8 instead of 9 where it is at the moment. Then we would take this 9 at the new position and compare it with 7. And if it's greater than 7, we would bring it to the right and perform the same procedure over and over again until 9 ends up at the last spot of an array. Let's say we got our number of elements is 9. And in the worst case scenario, when we have to literally reverse the array, with this algorithm, just simply comparing with the right neighbor and bringing the element, pushing it to the right until it reaches its spot, this would mean that for every single element that we're pushing, we would have to inspect in the worst case scenario all the ones to its right, which would amount roughly to 81 checks. And then we would end up with something like 1, 2, 3, basically the correct sorted array. 81 is the number of checks that we had to perform to achieve this result, and the input number of elements was 9. So this algorithm can be evaluated with the big O notation as of order n squared. This is a very, very slow algorithm. There might be something even slower than that, but that would be absolutely terrible and nobody would use it. Something like big O notation, maybe n factorial. Factorial is just a mathematical representation, and if we're saying, for example, 3 factorial, we're literally meaning 1 times 2 times 3, which is 6. And it's growing exponentially or even quicker than that. So 4 factorial would be 6 times 4, or 3 factorial times 4, which is already 24, as opposed to 6, which was 3 factorial. You can see for yourself. Obviously, this is the best performance, however, it's not always achievable. Like, it's a very rare case when you can do something at a constant time. The second, more realistic choice, ultimately the best one, is the order log n notation. We will talk about this guy later on, but this is usually the best performance ever achievable in such sorting algorithms, and other ones as well. The third best option is order n. So if you have a n number of elements, you will have to perform n number of instructions. Here we got 9 elements for our array, meaning that we would only have to do 9 checks, and then miraculously we would have those elements right in front of us in a correct order. It is actually possible, and I'll show you how you can sort this array, or how people figured out how could this array be sorted at such quick speed. A slightly worse and a much more common speed would be the order of n times log n time. So as you can see, not really the n, but something stuck on top of it. We multiplied also by this time. Number of operations of this n log n time would make us end up at much more number of operations having to be performed with the input number of elements n. Then of course the worst possible real life scenario, which sometimes can be met in real life, is n squared. Sometimes it's a necessity and there is nothing better. But the absolute worst case, almost no algorithms have it, is this slow guy, the order n factorial. This algorithm that I mentioned a second ago, comparing 9 with all the elements and then comparing every single element with its corresponding right neighbor, is called bubble sort. We've already figured out that it's of this time complexity, since we got 9 elements and we'll have to perform roughly 81 checks to end up in this position, in the worst case scenario. Of course, if let's say 9 is already on the last spot and 1 is there, this means that we will have to do slightly less than 81 checks, maybe like 70 or so, because those 2 elements are already in the correct position. But once again, the big O notation is expressing the worst case scenario possible. I also told you that you can sort an array at a linear time, that is order n time. How did people figure it out? Okay, for instance, imagine that we're sorting integers. This means that there are no numbers like 1.5, 2.3, 2.177, etc. Just rough integers. Since it's integers, they can be mapped to their array straight away. If there are no repetitions within this array which has to be sorted, then it's a piece of cake. Simply create an array with the 9 elements, place 1 on the first cell, that is the cell 0, and 9 on the last one, that is cell 8. Drop 8 into cell 7, 7 into cell 6, 6 into cell 5, 5 into cell 4, and you guessed it, 4 into cell 3. 3 goes here, and 2 goes here.
And actually, there was no 0, right? It should have been 1. That's what I meant. This is done in an order n time. We had 9 elements, and we just did 9 operations, having achieved this time complexity. This is the ultimate best case scenario, when you got a very narrow scope, and you are guaranteed that no integers are repeating themselves, as well as there are no floating point numbers. When you have slightly worse conditions, and your numbers are not that perfect, then different sorting algorithms come into play, such as merge sort, quick sort, or my personal favorite, also for integers, radix sort. I'll post the link into description, or you can also see it on the video right now, where you can see for yourself how different algorithms sort arrays, in which time, how many operations and comparisons they perform, and actually how they sound as well. For instance, one of the algorithms will split the query array into 2 halves, and then will keep splitting it such that this array ends up as many sub-arrays. Then those sub-arrays are quickly sorted and are joined into slightly bigger arrays, which are also sorted amongst each other. Then those 2 bigger arrays are fused into one, in our case, and the whole thing gets sorted. This is called merge sorting. As we can see from the Wikipedia, merge sort has the worst case performance as n log n number of operations, if there are n items. Typically, it ends up with the same time complexity in the best case performance as well. It is also very important to visualize and understand how those time complexities relate to each other. Let me quickly grab and position this information downwards, and we will draw a graph. The horizontal axis will represent number of input elements, how many items in an array we had, so n. The top axis will stand for number of operations which have to be performed given n input items. This is a very rough graph, but you should understand it. The constant time is always constant. It can be 1, 2, 3, 4, 5 number of operations, but it will never grow as we increase our number of input elements. So we can say, okay, let it be at 1. Log n time will grow at a rate similar to this one. It will always keep growing, but at a decreasing rate. So it becomes much more important and much more valuable the bigger n gets. Order n time is worse than log n time, and it looks something like this. So if you got 5 number of input elements, you will end up with 5 instructions having to be issued. The order n log n time grows something like this. As you can see, it grows at an increasing rate. But when we compare it to order n squared, it actually grows at the increasing rate, which is much slower than the increasing rate of order n squared. N squared would be growing something like this, you know, and then it rockets upwards. And finally, the ugly, poor n factorial. Sorry, buddy, you're not ugly, but this guy, it just goes relentlessly upwards. What is the best case scenario? As I said, ultimately we want to go for the order log n time. Since let's say we got 81 items, at order n time we would have to do 81 instructions. However, if our algorithm is working at order log n time, we would only have to do 6 instructions with 81 items. It's incredible, and it also depends on which base the logarithm is calculated upon. But once again, I will touch this thoroughly later on. Always try to avoid the green line, the order n squared time. Never ever do anything at order n factorial. Try to aim for order n if possible, or ultimately for order log n time, which would be the best one, since the constant time is usually unachievable. So this is your best bet, but you would usually end up with order n time, or in a much more likely scenario, most of the time something like n log n time. Having learned about this very important term, the time complexity, you can now understand and learn about data structures. We've already talked about dictionaries, which we used in the previous example with time remapping, and also generic lists as well as stacks. All of those are data structures, and they are all operating in different ways. Each one has its own benefits over the other one. So assume, for instance, that we're working with an array, and it will have several elements. In this case, its n would equal to 5. Any data structure has three important concepts that you should get your head around. It is the indexing time, also represented in big O notation, just like any other time. It is the insertion and also the deletion time. Any data structure will have its benefits in one of those areas, but most likely not in all of them. In an array, if we want to access a fourth element, we just point to the element number 4. So for the array, the indexing time is order of 1, the constant time. However, if we want to insert an item into the array, for instance, somewhere here, the first two boxes would remain as they are, but then we stick an item into here, and all of the following three boxes will have to be shifted by 1 unit each. In the worst case scenario, if we would insert the orange box into the beginning of the array, we would then have to shift the entire array by an index of 1 for its every single cell, and this would take us the order of n. The deletion time is exactly the same. If we want to get rid of this orange box, we delete it, and in the worst case scenario, it would be deleting the object in the beginning of the array, following by shifting the remaining row to the right of the deleted object by an index of 1. Also done in order and time, the worst case scenario when the box would be at the beginning of an array. Can we improve on that? And yes, we can, if we are using something which is a linked list. In this data structure, the elements are scattered randomly on the memory and are not neighboring with each other. Every single element knows about its child, and list will have its own benefits over the array and its own disadvantages. Assume we're looking for the fifth element in the list, and we want to establish a reference to it. Unlike in the array data structure, elements are not neighboring to each other, so we cannot say fifth element of the array and just move 5 cells on the memory to the right. We have to look at the parent-child relation of each element and travel across the children until we find the fifth element, and then establish a reference to it. Hence, the indexing time of the list is order n time. Notice the difference between the indexing time of array and the linked list. Here we are losing in time, but if we want to insert something or delete an item from the list, it's only going to take us a constant number of operations, simply changing the pointers between the parent and the child. Imagine that we want to stick an item somewhere in the middle of the list. All we'll have to do is just to reconnect the parent and the child, and there we go. Only 2 instructions which don't grow based on the number of elements in the list. It doesn't matter how many instructions there are, 1, 2, 3, 4, 5, as long as they don't grow when we increase the number of elements in the list, we can regard this as a constant time. Here we just change 2 pointers, meaning that 2 instructions have to be issued, and this is also a constant time. We don't have to shift the following elements by any amount, because they're not neighboring cells on the memory, unlike the arrays ones. But yeah, in array we are winning in the indexing time, but losing on the insertion and deletion. In list we are losing in indexing time, but winning on the insertion and deletion. Can we join those 2 data structures so that we win in all of those aspects in some way? And the answer is yes. You can come up with a third data structure, which is called the binary search tree. In it, we always have one root element, which is sitting at the top, and it's acting like the first element of the list. It always has 2 children on its right and on its left. Well, for us, it's on the right and on the left. For the computer, it just has a child 1 and child 2. The rule of any binary search tree is that all the children on its right are going to be greater than their parent, and for all the children on the left branch, they're all going to be less than their parent. This leads to several interesting consequences. So assume that we got a binary search tree, and this is just for a reference for us, that all the children on the right are bigger and all the children on the left are smaller. Assume we got just one item. Let's say we're storing numbers in our data structure, and it's number 20. Then we get a query, the request, to insert a number 6 into our structure. We are saying, okay, give us 6, and because we already have 20 as our root element, we look at 20 and we determine that is 6 greater, less than, or equal to 20, and it's less than 20. 20 doesn't have any left child, So 6 will become the left child of 20. We then get an item 40. Look at our root. 40 is greater than 20, and 20 doesn't have any right child. So let's store 40 as our right child. A wild 30 appears. We look at 20 and we're saying, okay, 30 is greater than 20, so perhaps we should travel to the right child. And the right child is 40. Because we want to insert 30, we have to travel now to the left. But because 40 has no left children, we'll store 30 as its left child. I'll keep going, and I'll add 35. Once again, look at the root. 35 is greater than 20, so we go to the right. 35 is less than 40, so we go to the left. Here we got 30, and we want to store 35. 35 is greater than 30, so we go to the right and store our 35 as the right child. 45 appears. Look at 20, should be greater than 20, so look at the right child. Should be greater than 40, so look at the right child, and there is no right child. We'll create one, and we will store 45 there. I will also chuck in, I don't know, number 1. 1 is less than 20, less than 6, so it should be here. Notice that any item in the left branch is less than 20, and any number in the right branch is greater than 20. Any number in this left branch of 40 is less than 40, and any number in this right branch of 40 is greater than 40. Answer me a quick quiz. How do you find the smallest number stored in this data structure? The correct answer is keep going to the left, and the biggest one obviously would be keep going to the right. Here I'll add a couple of more items like 8 and also 28, as well as 43, 90, 0, let's say 3. Here we will have 7, and here we will get 11. Observe that this tree has 4 levels. This is level number 1, level number 2, number 3, and number 4. 4 levels. The number of items we have here, the n, is 15. I will quickly steal the information from previous data structures, just so that we can compare the benefits of it. Answer me the following questions. What is the indexing time of our binary search tree? We have the structure, each element of which has 2 children. For instance, we want to get an element 5 in this data structure. So our query will be 5. How many steps do we have to perform, and how many traveling do we have to perform in the worst case scenario? We would have to travel a maximum of 4 elements. Is 5 less than 20? Yes, it is. Go to the left. Is 5 less than 6? Yes, it is. Go to the left. Is 5 less than 1? No, it's greater than 1. So if anything happens, it should be on the right branch of 1. And here we travel to 3, and we see that 3 is the leaf node, the last element. And we compare our 5 to 3. It's not equal, so 5 is absent from this data structure. Once again, our n was 15, and we had to inspect 4 elements. Now imagine that we erase the last row of our binary search tree and are left with a tree which has 3 levels only. Now the number of elements is 7, and we receive a query, a request, to obtain the item number 8, because I'm picking the worst case scenarios. The items in this case have to be present on the last row of the binary search tree, meaning that they are leaf nodes, or should be absent completely to illustrate the worst case scenario. Of course, I could have picked 6, for instance, and we would only inspect 2 elements. But yeah, query is 8, so we look at 20, we look at 6, and then we look at 8. When we have 7 elements in our binary search tree, we only inspect 3 items maximum. By the way, we call this binary search tree because every node has 2 choices, smaller or greater. Tertiary tree would be with 3 children. But yes, if we have just 2 rows and our n will be 3, then we would only have to inspect 2 items at maximum. Notice how n grows exponentially, but the inspect grows linearly and by 1. you can safely assume that if n would be 31, we would only have to inspect 5 elements, and so on. What is this? Well, on the graph, if you recall, where we got n number of items being represented by the horizontal dimension, and number of operations, the time it takes, as the vertical dimension, as we're checking more and more elements, we have to inspect the items, but our time grows at a decreasing rate. This is the log n function. In fact, it's a log n, but it's of base 2. 2 because we're dealing with a binary search tree. The log would be of base 3 if our tree would be ternary, with 3 children. But we are dealing with binary search tree because our children can be either bigger or smaller than the parent. So, base 2. Just to learn more about logarithm, calculate the logarithm of base 2 of 32. We know that we can express 32 as 2 times 2 times 2 times 2 times 2. This is 4, this is 8, this is 16, and then this is 32. Or we can also say 2 to the power of 5. And guess what? Log base 2 of 32 is 5. It is this tiny thing. How many times do we have to multiply the 2 by itself to get to 32? And the answer is 5 times, the power of 5. I'll give you just one more example and won't bore you to death with maths, but try one more example on your own. Log base 2 of 16. The answer is 4, because 16 can be represented as 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. Or, in other words, 2 to the power of 4. To which power do we have to raise our 2 to get to 16? To get to 16, we have to multiply 2 by itself 4 times. In other words, raise it to the power of 4. In this case, n is our number of items we drop into here, and the inspect result is the number of instructions we have to perform to achieve a given task. It is quite complicated, so if you understand it, you can congratulate yourself. If not, you can quickly go over the algebra principles, which will take you about 1 hour or so, and come back here to rewatch those last 5 minutes. But based on all of that, we can deduct that our binary search tree structure, the indexing time of it, is of order log n time. The insertion and deletion is just as inside of the list. Just modify the pointers of the appropriate parent and you're good to go. Here we're dealing with a constant time. Notice that log n is faster than order n time, because log n grows but at a decreasing rate, whereas the order n time grows linearly without any change. Binary search tree is an ultimate structure, but it has several implications about which I'll touch in a second. Given that you are dealing with a binary search tree, you can solve the following problem. In the universe, the maximum number of atoms approximately is no more than 4 times 10 to the power of 81. Or in other words, this big number with 81 zeros. Assume that every item has a unique name, ID, which is not repeated, and is in the form of integers. So we're dealing with item number 1, item number 2, number 3, number 4, blah 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 blah, item 500 billion 41, 500 billion 42, and so on. Their names are not repeating. If so, we can quickly spread them into our binary search tree such that we end up with a hugely populated data structure, where each item has a child who has an index smaller or greater than its parent, just like a normal binary search tree. And then, because we're dealing with the indexing time of order log n time, if we have that many elements in our data structure, if we want to find an item with the name of 6,500,001, we would only have to inspect 272 atoms or elements in our data structure at maximum. Imagine such a huge number, which is the number of atoms in the entire universe, and we can find the precise one in just that many picks. It's absolutely mind-blowing. And yes, if you wondered, when we chuck an extra 10 zeros to this number, because we're dealing with a logarithmic function, we will only have to do no more than 304 inspections of our binary search tree, just looking at its children, until we find the atom or its absence in the data structure. But there is one very important part which we should consider, and it is how we balance our tree. Assume that we have our root element as 20, and now we chuck in, let's say, 40. So obviously it will go to the right. Now we drop in 50, and then we drop in 52. We also drop 62. We got also binary search tree, which doesn't violate any rules. Every element has potentially 2 children, but because of the order we've inserted our elements at, our binary search tree is not balanced. Ultimately, it should have looked like this. So we literally grab this 50 like with a hook. But this binary search tree, the old one, violated the rules of the binary search tree, because in this case, if 20 is the root, the indexing time will be, in the worst case scenario, 5 inspections. Here our n equals 5, and if we want to find out if 72 is present within this data structure or is absent, we will have to inspect 5 elements. So the indexing time will be order n, which is not right. If I type in logarithm of base 2 calculator, then type in, well, calculate log base 2 of 5, the answer is 2.3. We always round it up to the following number. So if a log base 2 of 5 is roughly 2.3, we assume that it should be 3. Here, in the new version of the tree, this rule is conserved, but right here in the old one, we are violating it. This tree is incorrect, and this one is the correct balanced tree. There are several implications and operations which are dependent and tied with this concept of being balanced, maintaining the balanced binary search tree. Every time we insert an element, we should ensure that the elements in the tree are at the correct spots, and perform required transformations upon this tree if necessary, just like we grabbed this 50 and made it a root. This is all just a matter of reconnecting and repointing elements between each other. I will go over several rotations and transformations which can be performed upon the binary search tree when necessary. Assume that we got a root with the element 50. If we are inserting an item, let's say 62, it's clearly gonna go to the right of 50. We are yet not violating the rule of binary search tree, because log base 2 of 2 elements is 1. But for our case, it's an exception, so we are assuming that it's roughly 2. Whichever item we insert into the tree, we're gonna trigger a transition, a transformation of the tree, unless we insert something that is less than 50. For example, if we insert 27, the tree is in the correct state, because log base 2 of 3 is approximately 2 instructions. We can now add any item without triggering the transition of the tree. Doesn't matter where we will insert the item, the transition will not occur, and I'm experienced in that, so I know why it won't occur, but just bear with me. Let's say that we are inserting 76. And for example, let's insert 16 into here. We are not violating the rules because log base 2 of 5 is roughly 3. Because once again, even if we get the answer like 2.2, we're gonna make it a 3. If we now insert the item, which will be 82, the tree will no longer be valid, since log base 2 of 6 is still approximately 3. We have to perform a transformation. And how do we do this? I'll quickly make a duplicate of our tree, just to illustrate the transformation that we have to perform here. We will have to grab 62 and bring it to the left, making it the left child of 76. This is the right rotation, because we grabbed the right branch and brought it upwards. So whichever things we bring upwards, be it the right one or the left one, that sort of rotation will occur. Here we bring the right branch upwards and bring the parent downwards. So this is the right rotation. With this tree, let's see another case, the one where we insert something to the left. Let's insert 0, for instance. 0 would be less than 50, less than 27, less than 16, so it will be the left child of 16, because 16 has no left child. But clearly this tree is now unbalanced. We'll have to bring 27 downwards and ascend its previously left branch above it, making 27 the right child of 16. Once again, this was how our tree looked like before we had to perform the left rotation. And there is our right rotation. But if we're being naughty and are doing something different, let's say that we got this tree sitting here, and we want to insert not 0, but something like 25. 25 will go here. But notice that this branch is no longer straight. It's actually bent. How do we fix this? We cannot perform the right rotation or the left rotation here, since the elements will be in their wrong places. The right child will no longer be containing the greater element relative to its parent, etc. We first of all have to straighten this chain to make it straight. We're going to do this in the following way. Place 25 instead of 16 and make 16 the left child of 25. So we bring 16 downwards and raise 25 upwards. Now the rules are not violated and we got a straight branch which we can proceed and follow up with the leftwards rotation. And here we go, our tree is balanced as we inserted 25. Because of this, as we are inserting items, we are cleaning up our tree, and we are guaranteed that the indexing time will always be log n time. But because of this hustle that we have to go through every time we insert something or delete an item, the insertion time is no longer constant. It is as high as order log n. As you can see, with this approach we've managed to fuse together the benefits of an array and the list as well. Now when we have something like that number of atoms in the universe, the 4 and 81 zeros, if we want to find a particular atom, we only have to look at something like 273 elements. Whereas in the list, we would have to look through the entire huge number. But on the contrary, the insertion time would only take a constant time. In the array, if we would be dealing with this huge number, we would be able to quickly find an item just in a constant time, in a flip of fingers. However, it would take forever to populate this data structure, because every time we would insert something, presumably in the beginning for the worst case scenario, it would take the order n time to clean up the structure and shift all of the elements by 1 to the right, as well as for deletion. Here, we are somewhere in the middle. We are doing much better than order n time, since we don't have to look through the entire number, but we are worse than the constant time. Binary search tree is an excellent and a very fascinating subject to study, and I built a red-black balanced binary search tree, which I encourage you to look through. It's nothing more than just the way of keeping track of the shape of your tree. You keep track of it with red and black color. The sequence at which those nodes are being colored tells you about the problems in the tree and if it should be rebalanced at some stage. You can click on this link and it will point you to an excellent website which explains it in great detail, telling you which kind of rotations are being performed step by step. Binary search tree has many applications. However, here in this tutorial, later on we're going to focus on creating a data structure for handling three-dimensional space. Before we finish off with the binary search trees and the theory about them, let's also glance at their one application which was very important for my pathfinding and is tied with the planar point location problem. So yeah, you might be thinking, okay, you can use binary search trees to store numbers like integers or floats and quickly retrieve them, as well as delete them or insert into the data structure. Of course, this will incur several changes that will have to be added to the structure for it to function at a correct logarithmic time. Really, there isn't straight ahead any kind of useful application for that anywhere else. But in this case, if you are thinking this, you are a little wrong, because there is one excellent way and excellent approach to use binary search trees, to quickly speed up the process of finding if a point lies inside of any kind of shape on the screen or any two-dimensional surface. For instance, all of those buttons that are listed here in the Photoshop, including the close, open, and widen the window, all of the drop-down lists are there to be clicked upon. As I'm clicking on them, the program has to somehow identify if we clicked on some button as we clicked on the mouse. And that has to be done relatively quickly. If there is a button with a very weird shape, like a hexagon or maybe octagon with many sides or something like this, you still have to be able to click on it, and the check to see if it was clicked or not, or your click missed the button, should occur very quickly. So for instance, here we got a Cartesian system of coordinates. Let the x be the horizontal axis, y will be the vertical one, just like in normal maths. So assume that this is our screen space, and in the middle of it we got a weird shaped button, like that sort of shape. It has 5 points, one right here, another one here, and when we connect those 5 points we get 5 segments. Of course, computer doesn't see this picture or representation. In its memory it only has the coordinates of points, which can be linked mathematically in order to calculate any kind of intersections required, or something like this. So what I mean is that in memory, computer will see very disjoint data. So this is roughly what it looks like to computer, and well, once again, it sees it as coordinates, so it doesn't know even that those are lines or segments. But just to understand it slightly better, assume that this is what it looks like in the computer memory. Now with this data, given that I click somewhere here, and the coordinate, the point P, happens to fall onto coordinates 15 in X and 10 in Y. Given this information, and obviously we know coordinates of each point, 9, 13, 9, 13 here, and same for every single point. While we are seeing a shape here, a pentagon or sort of like a disjoint pentagon or distorted pentagon, computer doesn't perceive it that way. For us it's clear that P is outside of the pentagon, but what computer has is this data surrounded by a circle, no more and no less, and it also knows about this coordinate. The brute force approach, as we receive a query point like P, to see if it lies inside of the shape, would be to draw a line, let's say the one pointing to the left, and then to test the line that we get, which looks something like this, for the collisions with all of those lines. Computer will grab first of all this segment, that is this one, and test if it intersects with the ray that we drawn here. It will then do the same thing for that segment, and in reality it's going to be this one, and test for the collision with the line. And yes, it does in fact intersect with the ray. Then we check for this line, which in reality is this one. There is no intersection. Then this line, there is one. Finally, this one, which doesn't have any kind of intersections. In the end, computer sees that having drawn a ray, the leftwards pointing ray, from P, and having tested for intersections with this list of segments, in the end there are 2 intersections. And if you think about it, when we know that those segments, when combined, form a closed shape with no holes, if there are 2 intersections like those ones, then the point must lie on the outside of the figure. To be fair, it's going to be on the outside if it has an even number of intersections. Here we got number 2 of intersections. Therefore it's even, and hence we are outside of the shape. Yes, it might seem quite trivial for the human, but assume that the shape isn't as simple. Let me drop a point into here, and can you quickly tell me if it's on the inside or the outside of the figure? This time it will be easier for the computer to do its own routine, and it might be actually quicker than you predicting where the point fell into, inside or the outside of the figure. But that approach was a brute force approach, because for every single segment we had to test for the intersection with our point and our ray coming off the point, which would lead us to n checks if we have n segments. Can we get better than that? We have a very complex shape, which I'm obviously exaggerating too much, but assume that we got like, I don't know, 1,000 of segments making up our button. Maybe it's super round or something like this, with all weird wobbly shape. And we need to quickly check against all of those segments that make up this button, but we cannot fire off rays because there might be multiple touches if this is like a touch screen or something of that sort. We want to do it in a logarithmic time. For that, clever people have already invented a method called slab decomposition. To use it, we simply have to draw vertical lines through every single vertex of our figure to subdivide our figure into slabs. Notice that every single slab gets cut by the figure into several regions with the diagonal blue lines. So if I make a duplicate of what we got here, of our slabs, bring them to the right and scale them down slightly, you can really see that they are being spaced out horizontally along the x-axis. So every single one is a straight line with its own unique x-coordinate. This one has an x-coordinate of 5, the next one of 7, 10, 11, 12, 13, 15, 16, 17, and 18. When we got our point P, which has coordinates of 15.5 for x, and for y it's sitting somewhere at 9. With this point, we can really quickly find out if we are inside the figure or outside of it. As we're building those slabs and subdividing our figure by drawing the lines through all the vertices, we get a total of 9 slabs. I mean this one, that one, that one, that one, and so on. 9 slabs. By looking at the x-coordinate of our point P, the 15.5, we can quickly find out which slab we should be really looking at, with discarding the other slabs that we're not falling into. Because we are really focusing on this guy. You know, the one between 15 and 16. This one. If we check out, we can see that every single slab is being cut into different regions with its blue lines that are passing through it. So as we're building those slabs, we have to ensure that those entities know about the regions and about the segments which are cutting those slabs. So it sort of looks like this. Once again, as we're building those slabs, we should really mark the areas as being on the outside or the inside of the zone. When we're building such system, yes, we can use the brute force approach, because that's the only way, but only to make this quick structure, by traversing which we'll be able to find in logarithmic time later on if we are inside of the zone or outside of it. And with that, we are marking that this region represents the outside of the zone, this one the inside, and I'll put I to indicate that it's inside of the zone, this one outside, inside, and outside. We've already done half of the job when we've found out which slab we are into with our point, and now it's just a matter of identifying which region we're falling into as well. This can be done by quickly comparing the y-coordinate of our point P against the segments which are subdividing this slab, the chosen one, into regions. And as we find out that we are above this segment but below this one, we must be in this zone, and so we are inside of the figure. I said we can identify which slab we are fairly quickly. What I mean by that is that as we're building such structure of slabs, we got 9 slabs here, and because each one has a unique x-coordinate, those are nothing but numbers, and for numbers we can plug them and their related slabs into the binary search tree leaves. So we can really have a binary search tree of our slabs, and as we identify the node, our slab which we should inspect, let's say this blue one will be represented by this node of this binary search tree of slabs. But after we found this node, we can have a different link to another binary search tree, but the one which controls the vertical segments of that slab. So if we would be in a different slab, somewhere here for example, we would find ourselves somewhere in this place, and it would take us to a different binary search tree for that slab. Once again, those trees that we are identifying ourselves are controlling the areas of the slabs, or maybe segments. And because we're dealing with 2 binary search trees, we really have to do 2 queries. Each one will take logarithmic time. We first find which slab we are in, and then we identify which area we are in by comparing the vertical coordinate of our point against the equations of the segments. Since all of that takes logarithmic time, we don't really care about the coefficient of 2 in front of our time, since this is really what makes up the structure run at logarithmic time. This coefficient is just as negligible as some sort of additional component like 1 or plus 2. All of that can be discarded because this is what we really care about. Even though the problem of planar point location is very fascinating, and it's something that you might consider and must consider when making a pathfinding solution, we're gonna focus on something just as interesting, on controlling and handling space. Imagine that in a 2-dimensional world, we want to get a grasp on the point entities. And every single point is an object which has an x and y coordinate, because they are in a 2-dimensional world, that is the horizontal position and a vertical position, as well as maybe some sort of color. When we have something like 1 billion of those points, and like maybe a particle simulation has to occur, when we want to perform a collision detection for every single point to determine if we have to process it with physics, maybe move it aside because it has collided with other particle. If we have such a big number, the direct approach would be to grab the first point, and for it, grab all the other points and measure distance between this point and all the other points. That would amount to roughly 1 billion of checks for every single point, making it a billion squared number of instructions, which of course would amount to order of n squared time complexity. And it's a brute force approach. It would rocket up like this very quickly. The good news is that we can reduce it down to a linear time with something which is called a quad tree. Assume that we know that points won't leave a given region. If we know that, we can quickly cut out a square, the region, in our zone, the two-dimensional world. And we should enforce one rule, which is none of those nodes, and currently we have one big square node in front of us, none of those nodes can contain more than 2 points. So we will set our n, or maybe, I don't know, k, as 2. If we have more than 2 points in here, let's bring in a third one, then the zone has to subdivide itself into children and give its old points to the 4 new corresponding children. In this case, it had 3 points, so it had to subdivide itself in order not to violate this rule. And now every single child has 1 point and the condition is satisfied for this quad tree. If we try to graph this tree and see how it would look like visually, it would remind us of a binary search tree, because we have one big node on the very top, being the root, the biggest square, and it had 3 points, but then it had to give them up to its children because there were too many points for it to hold. And it has 4 children now: quad A, quad B, quad C, and quad D. Those are the leaf nodes, the bottom ones. Only the leaf nodes can contain points, and the intermediate nodes, such as the big or any other nodes that are lying in between, cannot have any points unless they are the leaf node. Because A, B, C, and D are leaf nodes, they can have their points, and A has 1 blue point, C has also 1 blue point, and D has 1 brown point. If I decide to drop another point somewhere in D, for example here, D is okay because it has 2 points now, but if we stick a third one, the magenta one, once again D will not be able to hold it and will have to split itself, giving the corresponding points to the new 4 children. And we'll call those children, let's say 1, 2, 3, and 4. So D had to create 4 children and pass its 3 points to the corresponding new 4 children, which are the new leaf nodes. This tree now might look unbalanced, but when we're speaking of quad trees or any other kind of k-dimensional trees, balancing them is possible, but it's of a very big hassle. And if it has to be done at real time, it's not really worth it. This way of handling space is very efficient, and really there isn't a need for any kind of balancing. It's already much more efficient, and you'll see in a second why. Also, let's say that we are adding another point, the pink one, somewhere in A, but we are doing this really close to the currently positioned blue point of A, and then we decide to stick a green point as well. Because we've positioned them so closely to each other, just one subdivision of A will not be enough. But let's not rush it, and first of all we have to subdivide this A node into 4 children, so it will have its own 4 children. But we also have to give those current 3 points to the 4th child of A. I'll call this one W, X, Y, and Z. Z is a leaf node, but it still violates this rule, so Z must be subdivided again into 4 children. It has to pass those points to the 2nd child, following our convention, because this one is the first one, this is the 2nd, 3rd, and 4th. The 2nd child, again, is not able to hold that many points, so it has to subdivide once again, and now we can see that its new 4 children are able to accommodate points and split them such that there are no more than 2 points per region. There's going to be 1 green point for child number 1 and 2 points for the 4th child. Our tree is quite deep, and you might want to restrict on how deep it can go.
how small those squares can be. But with this approach, what we've done is we've guaranteed ourselves that every point is going to be neighbored with a maximum of one another point in the region. We know that this blue point and the pink one cannot collide with the green one because they are in different regions. They still can collide between themselves, but the green one is all lonely on his own. The magenta one from region number 1 of D cannot collide with the red one since they are in different regions, and so they can't collide with the brown one. If we had 1, 2, 3, 4, 5, 6, 7 points, including the one in C, we would have to perform 7 times 7, 49 checks, because for every single point, using the brute force approach, we would have to calculate distances between this point and every other remaining point. Well, slightly less than 49, but anyways, that sort of number. However, here, we know that C is on his own in the region. There is no second point in C, so there is nothing to compare against for C. The same thing happens for this point, this region, this one as well, because they contain only single points that are guaranteed to not collide with anything, because it wouldn't make sense. The only thing we care about is this child right here. This area contains 2 points, and we can quickly check the distance between them, but that's about it. The distance checking is fairly expensive because it requires squaring the numbers and then taking a square root of it, but you could have seen for yourself. With this amount, only 8 checks instead of 49. It's so good. It's absolutely wonderful. We could have achieved the exact same effect if we would be using a 2-dimensional array with many square cells. You know, I'm trying to represent a very bad-looking array, but yeah, if we have such a 2-dimensional array, we would also have many little squares, and there is a fair chance that we would only get like a 2 or 3 points at maximum in the squares. But then we would waste all of that space with filling them with useless and empty squares. 20 by 20, which is 400 cells. And we only need to use those ones. Here is just enough to have one big cell. If we would have the 2-dimensional array, it would be full of empty cells, 5 by 5, 25 unused cells here. B would be completely wasted with cells because it wouldn't be ever filled. But with this Octree data structure, it's sort of like archiving, and this is exactly how you transmit pixels across the net and shrink down on the information. If you know that there is a big region of black pixels, why not to store this information in a quadtree? If there is a big lump right here, just keep subdividing until you get a fine resolution and transmit just this data instead of transmitting the entire array of empty pixels. If we know that this lump is completely black, shape it out with the appropriate resolution and don't bother about transmitting this useless data. It can be just in the big lumps because it's all solid white color. It's like archiving and it's very efficient. Plus, when you perform checks for collisions against points, you just saw it for yourself. Only 8 checks. Yes, with the cost of traveling down the tree, but it's such a good approach, and when you have billion points, it's an absolute necessity to use it. We're going to be doing something even more fascinating, because we're dealing with a 3-dimensional space. We're going to build an octree. Not a quadtree, but a 3-dimensional data structure which subdivides the space into cubes. Next example is going to be so hardcore that I'm afraid that half of my viewers will feel hopelessly lost somewhere in the middle of it. That's why, trust me, it's much better to do a quick revision to strengthen your knowledge a little bit more. We're going to talk about vectors right now. Vectors are the 3-dimensional entities, and a vector is the direction. It can point to some location from any specific place of your Cartesian system. Here, just like in Unity, assume that we are using a Cartesian system with the axis which is sticking forwards being called the z, the one to the right is the x, and the upwards one shall be y. It's not the case for 3ds Max, but assume that it is right now for us. Z is forwards, x is to the right, y is upwards. Where there is a cross, the black cross that you see here in 3ds Max, that is the 0th coordinate of the world. Such coordinate can be represented by the vector whose x, y, and z coordinates have a value of 0 in them. It is the center of everything, the center of the world. Here we got a pyramid with 4 vertices,
It's the simplest volume you can have in 3D. There are several ways we can define its coordinates, which is relative to the world or relative to the center of the figure. If I select it, you can see that it has a pivot right in the center, in the floor right here. This is the 0th coordinate within the figure. If I hide the grid, all the points here in this primitive are specified relative to its center. If I play my lovely animation, you can see that when I fade away this prism, there are 4 vectors from this origin of the prism, the coordinate which we count from, its pivot, origin or center. And it doesn't matter how much we displace this pyramid relative to the world's coordinate. In the local space, the 0th coordinate is its pivot. And from this pivot we can see that there are 4 vectors extending towards each of the corners of this cone. For example, the upwards pointing one has a change in x being 0, change in the forward axis being 0 as well, but with a 2 in the vertical dimension. For this coordinate, we are moving 1 unit to the right, 0 units upwards, and 1 unit forward. The same thing happens for all other points. Of course, if we would move around the pivot, then those coordinates would be changed, since the lengths of the resulting vectors would be different now, extending from a different origin. So we can pick any point relative to which we can specify our coordinates. It would be just as fine to specify it in the center of the pyramid, but then once again the vectors would be changed, since the origin has changed. This is the local space. If I make our grid come back, you can see that our cone is now being displaced away from the world's 0 coordinate. We can represent this displacement with another vector from the world's 0 coordinate towards the pivot. We can of course respecify those coordinates to be no longer relative to the local space of the figure, but to be relative to the world's origin, the world's 0 coordinate. That way we get a completely different length of vectors, and of course their coordinates values will be very different to the ones we had when we were specifying the coordinates relative to the pyramid's center. This is the world space, and the previous one was the local space. Here we're specifying coordinates relative to the world, and previously here they were specified relative to the figure's pivot point or the origin in the local space. The figure can be rotated around its center, and all the vectors are to be multiplied by the rotation matrix. When we perform rotation, those vectors get multiplied and transformed to point to a slightly different direction due to the transformation they are going through. This kind of rotation within the pyramid changed those vectors, and their coordinates are very different to what it has been before. I still haven't moved the origin relative to the world anywhere, so the vector from the world's 0 coordinate to the pivot point stayed unchanged. The same thing happens if I scale the figure, be it in all 3 axes or in some other axis. We are simply stretching the vectors describing the corners of our pyramid relative to the origin of this pyramid in the object's local space. If we would scale this pyramid relative to the world's center, let's say in the x-axis, this would have a completely different effect, since we would be scaling the vectors describing the corners of the pyramid as if they would be specified from the world's 0 coordinate. The same thing happens with rotation. This is the rotation in local space, but like this I'm rotating the pyramid around the world's 0 coordinate, relative to the world. In Unity you can always rotate an object in 2 ways. Around the world's 0 coordinate, meaning that if the object is here, then we rotate it normally, but as soon as it gets displaced, it begins to orbit the world's origin. In that case, we can pretend that the object's position is at the world's 0 coordinate, somewhere here, rotate it a little bit, and then immediately in the same frame, displace it back to the original position. Next frame, let's say the object has moved slightly more, and its pivot's position has changed. We can quickly teleport the object to the world's 0 coordinate, or pretend that it's there, rotate the object slightly more, and then displace it back to the original position. That way we create an illusion of object moving, but its rotation is actually occurring around the world's axis, and such rotation is very quick. It's referred to as Euler rotation. Another way of rotating the object is around the vector. That way we're not bound in rotating around the world's axis, but it's slightly more difficult. We can specify the vector direction, once again the vector which is relative to the world, and all that means is that the vector's origin is always at the world's 0. So we can rotate it as much as we want to, and then we can rotate our object locally around the given direction. It doesn't matter where actually the object is positioned, here, here, there or there. We are only looking at the direction the vector is looking at. We don't care that it's sitting at the 0th coordinate of the world. It's only the direction that is of our interest. If the vector is looking in a different direction, somewhere here for instance, then rotating the object around this vector will result in a different rotation. Returning back to the example with the pyramid, if we have our coordinates specified in a local space relative to the figure's origin, and we want to change those vectors, those coordinates, to be relative to the world, all we have to do is to sum up the local vectors with a vector from the world's 0 coordinate towards the pivot of the pyramid. Their sum will produce us a third vector for that point, which will represent the coordinate in world space. This information was very valuable to understand, and having learned it, you are ready to advance to the next level of this lesson.
I'm stressing this once again. This part of the lesson is really hardcore already. Make sure to watch it, but only after you are confident with other previous parts. I will ensure that it's as easy as possible, but you really need to have a backup of knowledge behind your back to go through this example with me. An octree is a data structure which allows us to separate elements in three-dimensional world such that we can perform fast calculations upon them, literally separating those items into groups. Evaluating such stuff by groups is always much quicker than doing this one by one. I've already explained why previously. So right now we will recreate such data structure from scratch. And we will end up with 3 scripts. There is going to be one script for moving and interacting with the world, such as placing the items in the world, deleting them, or moving them around. This script will be attached to the camera, and the camera will be serving us as a player, really. We will also have a mono-behavior script, which will be present on all the items that we are creating. We used an example of points. Here we're going to be using cubes. Such items will have this script on them, which will be controlling their position and relation, literally which nodes they belong to in the Octree data structure. And finally, there is going to be a third script describing the class of a Octree node. We're going to make use of recursive stuff here, and I don't really remember if I explained to you what recursion is. Don't worry, because it will be covered in this lesson. It's our goal to create an octree and to also make sure that it cleans up unused cells. For instance, once again drawing the parallel to the Quadtree implementation, all we did there was to add points to the data structure, but when they move around and leave some of the cells, we need to quickly find out which cells have to be removed, and sometimes the entire branches have to be removed from the data structure, so that the tree is not polluted with empty cells. All of that will be done with a third script. So, just as always, let's begin with creating the first script, the moving one, and I'll create a C# script with a big M up front. Immediately let's attach it to our camera by dragging it on camera. I will select the camera because I don't like this skybox here, and I'll set clear flags to solid color. I don't want to make camera see any kind of skybox. The color will be some sort of mild yellowish gray, just so that it's pleasant for the eyes. By the way, Unity changed in the version 5.0 where you can find skyboxes, and now they're sitting in Window, Lighting. In the Scene tab, you can find the skybox fold out or slot, and you can assign no skyboxes or maybe some different material with a different skybox. You can explore other settings, but they are really straightforward, granted that you've been through the introduction of the 8th tutorial. That is, no skyboxes, our camera takes solid color, and the background is this nice color. It also has now the mover script, which I've attached to it swiftly, and let's double click on it and start editing it. Once again, we'll be moving around with the script, and we'll be creating items during the gameplay. I don't think we'll need this system.collections namespace, and that's why I will comment it out. We can always add it later. But straight away in the start function, I want to lock our cursor so that it's not moving around in the scene. And this is going to be only happening during the gameplay, but in the editor, lock cursor doesn't really work. So it's still going to be useful, but only when we build our game. For that, I will go to the class cursor. We'll pick the lock state for the cursor, which is a thing of type enum. We've covered enums in the previous lesson. Make sure to check it out. Somewhere in the middle. Yes, it's in enum. We'll set it to cursor lock mode dot locked. This will stick the cursor in the middle of the screen, preventing it from moving around. We also have to confine it or hide it, so we'll set once again the variable visible inside of the cursor class. We'll set it to false. We want to make our camera fly around relative to its local position. So if we are pressing forward and the camera is turned downwards with rotation, when we press forwards, we want to move directly perpendicular to the screen, sort of downwards, according to its local position. That's why I've specified the space to be self, and I've also increased the speed at which we're going to be moving to the side and forward, because I'm multiplying this by a coefficient of 15 float. I'm ensuring that we're frame independent, and I'm supplying this amount for x. We're never going to move up and down because, yeah, we could have used spacebar, but it's not necessary. As well as that, we will also move forwards relative to ourselves, to our rotation and orientation within the world. On the second line, we're going to take care of rotating our camera, and we're going to do this in 2 steps. First of all, let's ensure that we are rotating relative to the world around the vertical axis, so that our camera is never tipped over. I've shown this in the end of the 8th tutorial, when our monk was getting screwed over because we were rotating the camera, and then the camera would get destroyed and messed up because of rotations. But here, once again, we're making use of this approach, and we are preventing the camera to rotate in any ways other than around the vertical world axis. Hence, I'm going to specify space.world for the last argument, which requires a value from the enum space. Because we're rotating around the vertical axis, obviously I'm not putting anything for the first argument, which would be the rotation around the x-axis, the rightwards one. We are rotating around the vertical axis here, and so we should be focusing on supplying the information for the second argument, the y argument. We also don't rotate around the z-axis here, because that would be clockwise and counterclockwise rotation around the forward axis. And obviously this happens relative to the world. Here it's exactly the same line, except that now we're focusing on the first argument, the rotation around our local rightwards axis, and local because we're supplying the space.self enum value for the final argument. So we can tilt our head forwards and backwards relative to ourselves and our rotation within the world around the rightwards sticking axis. Notice the minus that I've placed here, otherwise we would get an invert control. I have a feeling that we can already jump into the scene and test that our script is working. Because it's attached to the camera, let me just select it really quickly. You can see that I'm rotating with my mouse buttons, and we're gonna move forwards relative to the blue axis, the forwards pointing one from the camera, the z-axis. Due to this line of code, where we translate our character forwards, the third argument here takes care of that, relative to our own rotation. And therefore we can fly around the world just depending on how we look around the scene. Also notice that as I'm rotating my camera around the vertical axis, once again it happens around the world's vertical axis, not around the y-axis of camera, the local one. And so our camera stays in a correct position and doesn't get tipped over as the time progresses. For now, let's jump back into Unity and create an item, our cube, that will be populating our Octree with its copies. Let's drop a folder resources, which has a special meaning. Once again, I've been talking about this many times. We can create game objects on the fly out of it, and somewhere in the scene I will create a 3D object cube. We can create a sphere or whatever, but this one will be cube, and it has to be tagged with a new tag. I will add a tag called octcube. Pay attention to the casing of the letters. Here we got a new tag, but we still haven't assigned it to our cube. Let's jump back to cube, following by assigning an octcube tag to it. In the SS folder, I will create a second script now. Remember that we'll have a total of 3 scripts. We'll call it Octree item, with a big I up in the center of the word. Now, this script is the mono behavior and should be residing on all the copies of our cube. I'll drag it to the cube to fix this change and store it on the cube. Now the cube has mesh renderer, box glider, the transfer component, as well as the Octree mono behavior script of ours. We will need all of those components, so don't get rid of them. To create a prefab out of this cube, let's drag this cube over into the project panel, into the resources folder. Immediately we are brought here to this folder, and there we go. Cube prefab was created for us. We're going to be creating those guys on the fly with our camera as we are pressing several buttons. Jumping back to assets, we will take care of the new Octree item script, but for now let's return to mover script just for a little longer. Now we want to create copies of such cubes with a click of a button in front of our camera. I want to be creating them as I'm clicking my left mouse button. That's why every update I'm gonna check for an input, if there is an input, the mouse 0, 1. And if I do get it, time to create a new cube object. For that I will declare a new variable of type GameObject. We'll call it newCube. Immediately let's instantiate the cube. The instantiate static function of the GameObject class requires several arguments which can be overloaded. We're going to make use of the one which returns object and requires an object which is to be created. To supply such object argument, just as we did in the beginning of this tutorial when we were implementing time remapping, here we're going to supply an argument of resources.load, a function which returns an object, as we supply a string path to it. It is its second overloaded method that we're going to make use of. For the string path, because our cube lies right in the resources folder, not in any folded folders, we're going to just say cube. Pay attention to the capital letters. This function, the resources.load, when receiving this string information, will throw out an object which is immediately going to be consumed as an argument of the instantiate function of the GameObject class. The result of this instantiate function will be the object. Once again, if I open up the brackets, we're using the second overloaded method, it will return an object. So we should really cast it down to the GameObject type variable, because that's what we are sticking it into. The variable on the left is of type GameObject. Now this is correct. As we left click, we create a GameObject and immediately store the reference to it in this variable. This variable will be accessible for us until we've not finished going through this if statement. When this bracket comes into play, any reference stored in this variable will be erased and broken. So it only exists until this if statement is being processed. Creating a cube is not enough. We should also place it in the correct position, in the correct coordinate of the world, right in front of our camera, and maybe perform something else on it. So I'll say new cube, its transform and position. We're going to teleport it brutally to be right in front of our camera. For that I'm going to say this, implying this instance of this monobehavior script. And we can make use of the transform variable, that is the transform of the object this entire script is attached to, implying the camera or wherever we stuck it on. Dot position. This will be the countdown from where we're going to be counting out. If we just set it as it is, the cubes will be created right on top of our camera's position. But that's not what we really want. We want to stick it right in front of the camera. So with this vector, we want to displace it by a slight amount forwards from our camera. We cannot just say vector 3 dot forward, because that's relative to the world. We know that our camera is being rotated around, and its local forward direction might be actually looking downwards, because the camera is pointing downwards at the moment. Because of that, we want to make use of the local forward direction, and we're gonna once again ask the transform of the game object this script is attached to for the forward direction, the local forward relative to this camera. 1 meter in front of us will not be enough, so let's multiply it by something like 6. As I'm clicking my left mouse button, you can see that we're creating cubes in front of the camera. Even if it's looking upwards or somewhere downwards, we're still creating the cubes right in front of it, because we're making use of this variable. This is our little displacement, the forward displacement, from the current position of this camera. And we're storing this in the position of our newly created GameObject cube. Let's add some fancy effects during our update function. We want to drag around our cubes and delete them, maybe push them forwards. For that, we can already see that the cubes are already containing the box collider component on them. We don't have to attach it. But if it's absent, make sure to get it, stick it onto this cube, and apply it to the prefab, so that the changes are stored in the resources folder in the cube prefab that we are instantiating with our script right here. But we're going to be raycasting in front of our camera, trying to see if we actually have a cube right in front of us, and if we can interact with it, maybe grab it and drag it around as we press some other buttons. For that matter, we're going to create a variable of type raycastHit. And once again, we've been talking about such thing in the end of the 8th tutorial, when we were moving our monk around, casting rays and moving him with cross-product vectors. Make sure to check it if you don't remember it. I'll call it hit. This variable will be getting all the information as our ray that we're going to be creating just in a second intersects any kind of colliders on its way.
When this happens, all of this information will be dumped into this hit variable. This variable is declared every single time the update runs, right before the following instruction. We're going to make use of the physics class, just like in previous lesson, then use the static function recast, which is provided by this class. It has so many overloaded methods that you can use. You can see it's 12 here, but the one of our interest is the one with 4 arguments. The first argument is where we want to send our array from, the position, and it should be the position of the game object to which this whole script is attached to, so our camera, or whatever we stick it on. We can say this.transform, or just omit the word this, because it's implied, and just say transform.position. That's where our array will be emitted from. We want to direct it strictly to be forward from the camera, but we cannot say vector3.forward, because that would be relative to the world's axis, and our camera can be tilted upwards and downwards, with its local forward direction actually being different from the one of the world. Hence we're going to make use of the transform.forward value. With these 2 arguments we've specified the origin of the array and its direction. Now we can give it the variable where to dump all of the information about the intersections, collisions on the way of our array that's being sent. It's going to be the hit variable. However, it should be preceded with the keyword out. This keyword ensures that the function to which this variable hit is supplied will actually perform some manipulations upon it and will not make a copy. It will be working with it via the reference. So passing the variable like this will ensure that it will be changed and the changes will be applied to this variable as the function is ran. The function can still return something at its end, but supplying arguments in this way with the out keyword, or the alternative would be ref keyword, it ensures that you perform manipulations on an additional data passed into the function. And finally, the length of our array. Let's make it 100 float units. Notice how I wrapped this whole instruction in the if statement. If our array collides with something, this function will return true. Notice that if I open its first bracket, its return type is boolean. And so, yes, indeed, if something is on the way of our array, this function will return true, and this block of code, the one following this if statement, is to be executed. As soon as we know that there is some sort of collider in front of our array, through which our array pierces, we need to check if this collider is actually belonging to the correct object. I'm gonna quickly perform a check to see if the tag of the hit game object is equal to, how did we call it? Octcube. That was the tag that we assigned to our cube object. Notice that I'm making use of the hit variable. This function has already been ran and it returned true. That's why we fell into this block of code here. But because the recast function has already been executed, we are guaranteed that the hit variable has been modified with the data, and we can extract whatever information we want to from it, which we're doing here. We are getting to the collider of the hit game object, and from there we can straight away access tag or the game object itself, as you can see here. I'm interested in the tag. If that is also true, then we know that we are dealing with our octcube game object, the item, and it's right in front of our camera, because we're sending the array straight forwards from our camera. In this block of code, we'll now be executing all the relevant instructions that are to be performed upon those cubes that are in front of us. In particular, we want to highlight them just to show which cubes are in our focus, also delete such cube which is in front of us, or move it around. Let's focus on the highlighting part first of all. Since in this block of code we are definitely sure that there is an octcube game object in front of us, we can establish a reference for it for further utilization. I'm going to declare a variable of type game object and call it Quad. Then we'll establish a reference to it through the variable hit.collider. From the collider we can access the game object. Now we've established a reference to the cube which is right in front of us. And also in the beginning, somewhere in the global scope, I'm going to declare a variable of type material, and then call it a recent cube material. Right after I've established the reference to the game object, the Quad one, the cube right in front of us, I also want to establish a reference to its material. Now I'm going to say Quad and get the component of type renderer dot, then point myself to material. Now we're referencing the material of the cube which is in front of us with our variable in the global scope. Because this cube is right in front of us and is therefore in our focus, let's maybe highlight it with a color like cyan. I'm gonna go ahead and change the recent cube's material, its color, straight away to something like color.cyan. Of course, I could have created a new color. However, here I'm really making use of the Unity's prepared value of color, not wasting even a smallest portion of memory, creating unnecessary colors every time. As soon as we will get the cube in our center of screen, meaning that the ray pierces through this game object, identifies that it's an octcube. As soon as that happens, we establish a reference to it through our global variable and are referencing its material, the color of which we change straight away to a cyan color. Also notice that if I start the game once again and create other cubes in front of us, they will all be of cyan color, but the previous ones will keep their color being changed to cyan because we never change it back to their default state. Hence, let's introduce another small piece of code right after our raycast function fails to hit anything. So if previous block of code didn't run, meaning that our ray didn't intersect any colliders, we're gonna grab the recent cube's material, access its color, and set it to be the white color, the default one. However, there is a small trap for you. This might be a problem because if this code runs for the first time and we start the update for the first time, notice that the recent cube's material hasn't been assigned anywhere yet. It will only be assigned for the first time if the raycast is successful, right here. In such cases, we should make it an exception and actually surround it with a check, only allowing the following instruction if the recent cube's material does not actually equal to null. Only then should we allow to change the color of a given material in the renderer component of some Octree cube. But if it hasn't been assigned yet, then we just don't do it. So notice that if we run the game, now the cubes will be getting their white color back to them as soon as we don't highlight them anymore. But there is one interesting thing in that if I create more cubes, notice that there is a little glitch. Some of them do get highlighted with cyan, but some remain with it, and it's a problem. Notice that this code, the one which resets the color back to white, of the cube's material, the most recent one, only if the raycast fails. But what happens if we just slide our ray from one object to another one without the ray actually being cast through the vacuum? What if it just slides from one collider to another one? This piece of code will never be ran, and whatever was referenced by this variable previously, the previous cube, it will never get its color changed to white. So this block of code should also be ran inside of here just before we decide to rewrite this variable with a new reference to some other material, somewhere here. As soon as we know that there is a cube in front of us, if the recent cube's material did not actually equal to null, meaning that this is not our first cube being referenced, we change the material of whatever was referenced by us previously, its color, to white, and only then do we proceed to rewrite this variable with some new reference to the new octcube, which is actually in front of us now. The glitch is gone now, it's no longer present. Even if we're sliding our raycast ray from one object to another one, before we reassign the reference of the material variable, we are ensuring that the old game object has its color being reset back to white, before this variable gets to reference a new material of some other octcube. And with that we've achieved the highlighting part. Now we know which cube is in front of us, which one we're going to be manipulating. Now let's move it around. Let me embed this piece of code slightly more. And here, after we've performed all the manipulations with colors, we can finally do a check. Notice that I'm doing this still inside of this block while we are sure that there is an octcube in front of us. A check to see if we're pressing the right button on the mouse. We only want to perform this once when we register the mouse actually being clicked down, not held. Mouse 1 because I want the right mouse button. And if we do get key down, this means that we should hook this cube which is in front of us and parent it to our camera, because we want to drag it around. For that matter, just like we did with the recent cube's material, I'm gonna create a variable of type transform and call it recent cube's transform. Immediately here, to this variable I will assign a reference from our cube, which is in front of us, and we called it Quad, to its transform. Now, when we have a direct link to its transform, let's make this camera be a parent of this octcube, since we press the right mouse button while this cube is in front of us, and so we imply that we should be able to drag it around. That's why recent cube's transform dot parent becomes equal to this dot transform, because we want to access the transform of the game object to which this script is attached, meaning the camera. Or we can say simply transform because we can omit this keyword. we can create several objects. And when I right click on one of them, let's say this cube, I parent it to my camera and I can drag it around the scene, but there is no way to unparent it. Let's introduce this functionality to our script. Once this is over, let's see if we actually get the key up, with the key up being the mouse 1. And if that's registered, then we should unparent our cube. Recent cube transform, its parent, becomes equal to null, meaning that there is no parent of this Octcube game object anymore. In this case, we might also encounter a problem similar to the one which I explained with the material, because if this function is run for the first time, since our recent cube's transform is the variable of a global scope here, it might have not been declared yet. So let's ensure that we access it and begin to work with it only if it has been already tied to something and given a reference to some Octcube's transform. Just like this. We can grab a cube, parent it to our camera and drag it around, but as soon as we release the mouse button, this event will be caught and the old cube will be unparented from the camera. We can now pick up another one and drag it around. Our code is able now to highlight the cubes which are in front of us, as well as to parent them to our camera when needed, so we can drag them around the scene. Let's maybe introduce the functionality where we can delete such cube which is in front of us, or maybe add a force to it so that it's set flying forwards. Deleting the cube will be our first step, and it's going to be performed just like we did previously with with checking for a similar input. This time we'll be checking for a key down, and the key code will be E. In fact, maybe let's make it the key up, so that even if the user pressed E while having the cube in front of him being highlighted, he might actually change his mind and without releasing E, just rotate the camera such that the ray is no longer highlighting the cube, and the cube will be saved, will not be killed. Otherwise, through the GameObjects class, we're going to access the static function called destroy and supply the game object to be destroyed, that is our caught cube. Later on we will elaborate on this functionality and add actually extra piece of code such that if there is an additional information related to an actual Octree, it will be deleted correctly and properly in this block of code. Right now we're just focusing on visually destroying this game object. It is visible that when I press E on the highlighted object and release the mouse button, the cube will get deleted. I can then create new ones all around, drag them around, and whenever I want to, I have to highlight a cube and press E to get rid of it. Let's add some final functionality to it, such that we can push cubes away from ourselves. And for that, I'm going to select a cube and add a component, the rigid body one. The mass of the cubes will be 1, and their drag will be something like 0.3, so that they are stopping fairly quickly after there has been a force added to them. The angular drag is how quickly the object stops spinning. Let's set it to something like 0.2. It will not be using gravity in order to make cubes hanging space, and they will not be kinematic because they have to be colliding with each other. I will apply the change to the prefab, which is sitting in the resources folder, and now all the cubes which are instantiated from it with our left clicking will have this rigid body component attached on them. Just like we did before with delete, we want to add another block of code and see if there is a key down. Key code R. So when we press R, we want to add a force to the rigid body of the cube which is in front of us. For that, we have to establish a reference to its rigid body component. I will call it Quadtrees. We'll point it directly to the quad.getComponent rigid body. So now, you guessed it, we're referencing this rigid body of that particular Octcube in front of us being highlighted. We can now perform operations and carry out instructions on this particular component. We want to be adding force in the forward direction relative to our camera. So even if the camera is pointing downwards, we want to be sending the force forwards from our camera, which is going to be downwards. And because of that, we're not going to be using any kind of vector 3.forward, which would be sending a force parallel to the forward axis of the world, always in one direction. But instead, we're going to send a vector of force parallel to our transform.forward. This value is too small, the vector which is produced with this instruction. It's a length of 1 always. So let's multiply it by something like 150 float, so that the force is strong enough. Notice the following thing. If I start the game and create several cubes, When I set them flying with my R button and quickly grab one of them, it will start to fly out from my reach and will no longer become highlighted. When I release the mouse button, it will still be parented. Therefore, let's improve this by ensuring that as soon as we grab and hook our new cube, parenting it to our camera, that its rigid body becomes kinematic as long as we're holding the cube with our hands. In fact, we should bring this reference outside of this block of code so that other blocks of code can access it and share it. Just like we did here. Right after this line, I'm gonna stick this one, and now we've established the reference to the rigid body of this Quad game object. In this block of code, just like here, let's work on it. It is of our interest to set the isKinematic variable to true as soon as we grab the cube. That way it will not be pushed by the rigid bodies of other cubes flying into it, but it will be influencing the colliders and hitting the colliders of other rigid bodies, pushing them aside if needed. Also, as soon as we release the cube and there is an input of getKeyUp, the rigid body of the Quad game object isKinematic has to become false, since the rigid body should no longer be kinematic. Now, as we start the game, even if our cubes are flying around the scene and we grab one of them, as soon as we grab it, it becomes kinematic and is fully under our control. When we release it, it can be now pushed with the forces and pushed away by other cubes. Finally, let's add one small minor change to our code at the end of the update function, where we should be looking constantly for the input, the getKeyDown keycode escape. If the user presses escape, this will terminate the application, and this will only work after we've built our program. That way you don't have to panic and press Ctrl-Shift-Escape, go and terminate the process, since your game will not be able to close. Press escape and you're done. If we're getting this button pressed, just access the function quid, the static function, belonging to the application class provided by Unity. It is very important that you understand that those variables, the recent cube's material and the recent cube's transform, are declared in the global scope, outside of any functions. Therefore, we have to flush references to them and handle them in a careful way, since they are not recreated every single time the update is ran over and over again, like, for example, raycast hit would be. Even if the update is finished, the references to the game objects will still be stored, even if we're no longer highlighting them. Therefore, if we're not highlighting them, we were going over through such things like here, we were resetting the material, etc. Maybe we could also unparent such transforms, but I don't think it's necessary. You still have to understand that references stored in those variables are more persistent than any ones inside of this update call, for example. Like raycast hit will only exist until the update is not finished. The next time it's run, a new variable will be redeclared and all the previous data will be flushed, unlike for those two variables. Also, the static functions can be called directly from classes because that's how they are working, as explained in the previous lesson, in lesson number 8. You can call static functions and ask them to do anything without actually having to create an instance out of the class to which they belong. Normally, I would have to get our class, the blueprint, to be formalized in terms of some sort of physical object, and then from that object I could make use of the function. Here, we're just saying, okay, make use of this function of that class without actually creating an instance of that class. You can see that quit and the raycast functions are the static ones, and they are being called from physics class and the application class. Looking at those namespaces, I didn't make use of the system.collections, so I'm indeed gonna get rid of it. And with that done, we have finished the first script, the mover, and it's now time to advance to the second part, the Octree item script, every instance of which will be holding data of its relevant cube to which it's being attached to, such as position and later on the Octree nodes to which it belongs, as well as maybe its neighbors. We will see. And then after that, it will be the third script, the one directly related to the Octree node, which we are yet still to create. For the purpose of this project, we're gonna focus on developing an Octree, but in its virtual form, and then later on, when it's all working, perhaps we can visualize it in a three-dimensional world. Right now, it's the matter of shaping out our Octree item script that is going to be sitting on all the cubes, also known as our objects stored in our Octree data structure, the items. Our second script, the one regarding the item, is going to be directly working with the instances of the third script, which we are yet to create. The third script will be describing just a single node of an octree, and then as it's being materialized in its many copies, those copies will be linked between each other, forming in a whole this Octree data structure. I will create a C# script and we'll call it the Octree node. To rephrase this a little bit, imagine this final third script as representing one of those squares which were making up our binary search tree. It's just a description for one of such squares. We're gonna focus on it slightly later, and for now let's chuck in a few more information bits into the Octree item. This is a mono behavior because this script and its instances have to be present on our cubes, which has to have several global scope variables, the generic lists. Because of that, I'm going to include another namespace, system.collections.generic, because we want to make use of the lists, or maybe stacks even. We'll see in a moment. Because we now have the access to this namespace, we can create such a few variables. One of those variables will be the list of the Octree nodes into which this object happens to fall. Because of that, we're going to refer to them as owner nodes, the ones which contain this cube. Having called it my owner nodes, I will initialize it straight away to become a new list of type Octree node. This line of code runs before even the start function, but roughly on the same time. So as soon as the game starts, each copy of this script that is attached to all the cubes will get its own list of Octree nodes called my owner nodes. We'll be constantly adding and subtracting those Octree nodes, the entities of the Octree, to and from this list. So it will be growing and expanding as our cube is chucked into different regions of the Octree. Every single item like this one has to keep track of its position and invoke some sort of operations and perform different requests as soon as the position doesn't match the one from the previous frame. In order to keep track of such positions, we're going to create a private variable of type vector3 previous position, or prevpos. Because this variable has to be initialized, otherwise it interprets this as a vector3.0 pointing to the 0th coordinate of the world. Because we don't want this, we can initialize it straight away in the start function to give it a different value by saying that it will grab the position of whichever object the script is attached to. So the transform.position. That's literally it for the start function. Nothing else has to be performed right now. We're not going to make use of the update function, however we need the fixed update one, since we want to perform the following operations only now and then, and not every single frame, because they will be quite expensive. The fixed update will ensure that as we move the cube, that we update ourselves the information in this cube, and also the corresponding information in the Octree itself, but only if there is a mismatch between the current position and the previous position stored from the previous frame. For that, I'm going to shape out the block of code, saying that if the current transform's position doesn't equal to whatever is stored on the previous position, then execute the following bit of code. And because the position doesn't match the old one, having performed something in this bit of code, what we will be doing we will decide later, but having done this, let's update our previous position so that it stores the correct value of the position, the new modern one. In this area, it's designated to run the function which updates the entire information of the Octree, and also does some operations upon this list if needed. If, for example, this item moved to a different cell of the Octree, or some sort of division occurred. But let's drop this for now to change and develop the third script. This one will not be the mono behavior, even though it's going to be controlling so many virtual entities, the Octree nodes. So we're going to get rid of this extension. This class doesn't extend anything, and it's on its own. Straight away, I know that we're going to be using a lot the generic lists. I'm going to chuck in, because of that, the appropriate namespace. View this class as an entity of the Octree node. Remember how we were making the Quadtree? Well, this class can represent one square. It doesn't matter how big it is or what parents it has got or children. This is the representation of one cell, the node, in our Octree. So now we're going to write a description for it. Let's say that this data structure can only hold no more than 2 items. Or even for the debug purposes, no more than 1 item. If it has more than that, then it has to subdivide itself and create 8 children. Because this variable has to be shared across all the instances of this class, it has to be static and also public. It will be the integer and will be called the max object limit. Static means that no matter how many times we recreate this object and create different instances out of it, with different children, populating and growing our tree, making it deeper and deeper, Doesn't matter how many instances we got, this variable will only be in one replica and shared by all the classes. If some class would decide to change its value, then all other classes would see this change as well. If you don't want to change the value of this variable, then you can consider using the constant keyword. However, it might be in our interest to change how many items each node can contain dynamically during the runtime of our program, so I'm not going to add this keyword here. That's why I'm going to keep it as it is, without adding anything. The Octree cells can be represented as a cube-like structures. They're just division of space. Because of this, every single node will have its position relative to the world's 0th coordinate, and from the center it will have a given fixed length unit. We will call it the half-dimension length. It will be set later on, and we shouldn't set it here, because it has to be done once we are creating and instantiating this class. Imagine that there is one big root, which is also an Octree node, but it has to be splitted into smaller children. Only then will we know how wide its children have to be, and only then we will pass the value for their half-dimension lengths. Of course, every node like this, just as I said before, has a private position, the center position, relative to the world's 0th coordinate. The entire Octree data structure will have one single root about which every single node will know. That's why, similar to this variable, the shared max object limit, there is also going to be a shared variable which is going to be pointing towards the root of our Octree. That variable will be private because any other entities other than Octree nodes shouldn't get access to it. It's only the privilege of the Octree nodes to know about the root. We can omit this keyword because it's not necessary. If we don't supply it, then it's implied that the following variable is private. The root, of course, will be of this type, the Octree node, and it's going to be an internal variable. So I'll put an underscore in front of its name to signify this. Even though this is a private variable, the internal one, it will have a messenger variable, the public one, which will be the read-only one. Nobody will be able to rewrite this connection to the root, because it will only provide an opportunity for reading it, not writing. This will be the external variable, visible to all other classes, and let's say Octree items, which will encompass the getter instruction. Of course, I forgot to put a type in front of it. Now it's correct. We're going to make use of a so-called singletone pattern. Assume that the game has just started, and this class is sitting here all alone. It's not even materialized, nothing happened, and there is no Octree present in our world. Just like we did with the example on time remapping, we're going to make use of the runtime initializeOnLoad method, supplied in Unity 5.0, to invoke some sort of function. This method will ensure that we create one root in the center of our world. In fact, let's really quickly create such method here in the class. Remember that the signature of the function has to have a static keyword in front of it, so that this function can be called without having to instantiate the class. And I'll call it init for initialization. Just like promised before, I'm gonna add a mark on top of it, saying that it's a runtime initializeOnLoad method and should be called as soon as Unity starts its game. It will call this function, and that function will ensure that there is at least one instance of this class representing the root of our Octree. But it will do it in a smart way. Let's, instead of explicitly saying that, oh, create an instance of this class, blah blah blah, let's do it in a slightly tricky way and return the following statement. Because our function returns a boolean, we have to perform something that will return true or false. Let's grab our Octree root messenger variable and check if it's equal to null. The result of this statement will be true or false, and that's exactly why it's being stuck into the if statements, if you think about it. But as soon as this is called, this function will be over, and you might have thought, oh, didn't you say that we should instantiate and initialize at least one instance of this class, but we didn't do anything? Well, what we'll do is that by accessing this messenger variable, which has the getter instruction, it will check if the internal Octree root is exactly equal to null. It will create an instance of this class and will point it towards this internal variable. After this, it will return the Octree root internal variable. With this way, to whoever requested and called this variable, we're supplying the value, the reference, towards the Octree root, and in the meantime, if it hasn't been even initialized, then we'll create a new instance and then return it. So at the end of this block of code, we will always have a reference to some Octree root, either the newly made one or the old one, if this block of code wasn't successful. But if it was successful and our internal Octree root hasn't even been created yet, then we're going to say that it becomes equal to the new Octree node. This is a constructor function attempting to initialize and form an object out of this class. but we didn't supply any constructor function, so it will run the default constructor, and we should take care of this as soon as possible. But here we go. This function is ran as soon as Unity starts. We perform this check, which requires traveling down this variable, which turns out to be just the getter implementation. And this getter attempts to see if the actual Octree root, the internal variable, has been pointed already to a class, the instance of this one where we currently are in. And if it hasn't been, then we quickly create such instance of this class and point it directly to the Octree root internal variable, which immediately after that is being spit out. I've been talking about the static keyword and how it's important, but I forgot to include it here. The internal Octree root variable should only exist in one replica, and all the classes, even though they have an access to it, should all be pointing towards one single variable, sharing it amongst themselves. So both the getter variable, this one, and the actual internal, the real Octree root variable, which has the link to the Octree root, they should be static. So static Octree node Octree root and public static Octree node Octree root with the getter method. This is exactly what singletone pattern looks like. It is always tied with some sort of class, which has a static variable, and when this variable is called by some other object, this class sees that, oh, actually, this variable hasn't been pointed to anything, so perhaps I should create an instance of myself and link it to this static variable. Next time when some other random objects make call to this variable, the class itself will look at its own single static variable that can only exist in one replica, and will see that it has been tied already to the instance of this class. So it will return whatever is there without creating a new instance of itself. That's how singletones work. So in the end we ensure that there is always one class which can only exist in one replica. Just one instance of itself can exist at any given moment of time. Before we finish this block of code, let's also check in a few more variables. We already have the maximum object limit, which is shared with all the instances of such Octree nodes, can only exist in one replica. Also a single replica possible of the Octree root with its getter, the half-dimension length specific to each Octree node. Every instance of this class will have its own half-dimension length, and the position of this cell relative to the world's 0th coordinate. We should also create a variable of type Octree node and call it parent, because every instance of this class should know what its parent is. And haha, we can make use of this generic namespace because we want to keep track of all the items, those things, keep track of all of them which fall into this particular cell described by some given instance of this class. We've already specified the creation of such an Octree node when we were creating a root. Right here we would make this Octree node, and as it's being created, notice that we initialize immediately this list before the constructor will be ran actually. So later on we can use this list, even though it's going to be empty in the beginning. But this one will keep track of all the little cubes, the items that are falling into this cell described by this Octree node. Finally, every single Octree node has the potential to contain 8 children. When it splits, when there are too many items to contain, it will give birth to 8 children. It will split around its center, so later on this variable will come in handy. But every single node like this one can contain 8 children also of this type, and it will be private because it will be the internal variable. We'll call it children nodes. And straight away, as soon as this instance of class is created, right before the constructor function is ran, we already want to initialize an array with 8 cells. Even though this array will be empty in the beginning, it will have 8 cells for the future utilization. Later on we can place corresponding children if needed at those empty 8 cells. Once again I forgot to specify the type of this array, and of course it should be the Octree node array, since our potential children will also be of this type. But this is an internal variable, just as shown with this underscore and the private keyword. Actually I'll remove this keyword because it's unnecessary. I've been telling you this many times already. Then we'll provide the getter instruction for it. Of course it will be public, so that it can be accessed by anyone. It's going to have the exact same type as its corresponding internal variable. It will be the Octree node array. And this time it will be called without the underscore, so children nodes, since it represents the external handle or getter instruction.
and straight away we will return the corresponding internal variable. So this way we are preventing anybody from unauthorized rewriting of corresponding data in those 8 cells of this node. Only node itself will be able to change its children if needed. But for anybody else, they can go home because they can only read the information and can't change it. We will continue by introducing a constructor function into our Octree node class. That way, as we create the instance of Octree node, be it the root or some other subchildren of it, using this constructor function, we can tell it an extra information such as what length should this new node be, what children and what items might it have. Recall that constructor functions should always have the same name as the class name. So I'll grab the name, the Octree node, and we'll set it to be public. We'll have a public constructor, which will take several arguments. We will discuss them in a second. First of all, whenever we create such node, we should always tell it who is the parent of it that created it. Therefore, the first argument will be of type Octree node and will be called parent. We want to set the parent variable of this instance of the class to point exactly to the supplied parent. And so typically, when a big node subdivides itself and creates 8 new children, each one of those new children will get their constructors invoked, and it's the parent's responsibility to supply itself as an argument so that children can set it properly and they know that it's this big node who is their parent. As well as that, we should supply to this newly created node the list of items that might be given to it and might be contained in this new smaller child. Hence the second argument will be of type list, which is designed to carry the Octree items. In this constructor function we will refer to it as potential items. After we set the parent of this new Octree node, we should process such potential items to see if they indeed belong to this new node. We will iterate through each item in this list, and for every single item we will invoke a yet non-created function, which we will develop later on, which will be called process item. Once again, we still haven't created this function, and we'll do this in the near future. Process item, the item. This function will take care of inspecting this item from potential items list to see if it indeed has to be accepted as its own native item, so the item belongs to this node. But this will be done later. This is not enough, because as we are creating a node, we should supply also the position, which should mark its center, and I'll call it this child pause, as well as the half length of this newly created node. Right after we find out who's the parent of this new node, we should also set its correct half-dimension length to acquire the passed parameter of this child half-length. The same story happens to the position. The real position of this node becomes equal to the position supplied by whoever created this node and call this constructor function. Let's check for any errors in Unity. Apart from this function missing, which I told you we still haven't made, everything seems good. If I comment this method call for now, another mistake comes up, and in fact it happens when we create a root with our getter method. It makes a call to the constructor function of this class, but we've just said that anytime we want to create a node, we should supply it 4 arguments. Who is the parent? Where is its center? What are the dimensions of the cube? And are there any items to be stored in this node? Therefore, for the parent of the root, we'll supply null, because root doesn't have any parents. It's the biggest possible node. In this case, I will position the main node, the root, at the 0th coordinate of the world. I could have created a new vector and supply 0 in all 3 arguments, but I'm just gonna make use of the Unity's supplied one. Just like this. How far will the dimensions of the cube be? Like, what is the half of its length? Let's say that from the center to one of its walls, it's gonna be about 15 meters. And for the list of items, we have to supply a list, but we're gonna just supply an empty list. That's why we're gonna create an empty list, which is to be carrying Octree items. And we'll pass it as the argument. It's completely empty and it's not being assigned to any variable, so as soon as this function call is over, it's gonna be vanished into the eternity. Nobody's gonna even remember that it was ever created and passed. But it's a necessity because the function demands a list to be passed. Create a new one, completely empty, and pass it to the root, because there are no items to be stored yet. The error will go away now, and there are several warnings because we've declared some of the variables that we are not using yet. As I start the game, believe me or not, there is already a big entity, the half length of which is already 15 meters in all dimensions.
It's pretty big. It's the big root, which sits at the world coordinate 0. If we want to see it, we will have to make it visible, which will require us to add a few more functions. For such visualization, we should actually carry an information about an Octree game object. So every Octree node will have a game object that will be displaying and representing the bounds of this particular node. So here we can declare the necessary variables. One of the game object type will be called node game object, or maybe octant game object. This object should contain several components, the most important one of which is the line renderer. Octant line renderer. As you can see, with those two lines we're going to be storing references to this component and the game object. Tying of those references should happen during the constructor function. Right after we've specified all the information for the position, the length, and told the node who was its parent, before we start to go and sift through the items, we can initialize this information by creating a new game object. It doesn't matter where we position this object, so by default it will be placed always in the world's 0th coordinate, for any consecutive nodes and even their consecutive children. Their octant game objects are all going to be stacked at the world 0th coordinate, but the lines that are shaping out the boundaries of those nodes should be in their correct positions. We will take care of this. After creating it, we should also hide the flags of this new game object, such that it's not shown in the hierarchy. Hide flags is an enum, and you can pick between different available options. You can even hide and don't save, so the items won't be saved between the scenes. You can hide anything in the inspector, and as you would select such object, it would have no settings visible on this inspector panel. Our interest is hide in hierarchy. This new game object, which belongs specifically to this particular instance of an Octree node, should immediately receive a new component of type line renderer, which should be immediately assigned to the octant line renderer, the one we declared just a second ago, right here. Becomes equal to octant game object. Usually we would get a component, but it's not attached by default to this new game object. We have to attach it ourselves. So add component of type line renderer. As well as adding a component to this game object, this function ensures to return a link to this newly created line renderer component. Now having our grasp on the octant game object and its corresponding new line renderer, we need to supply an additional information for this new component. Just once, so that it knows through which coordinates to draw the lines. Because our Octree node entities are of the cube shape, and the root is pretty big, its half dimension is 15 units long, because of this it would make sense to supply such coordinates for this line renderer to be the corners of this cube. Here we're gonna make call to a new function, which we're also to declare. We'll call it fillCube visualize coordinates. Without waiting, let's declare such function and explain what it should be doing. Our line renderer component should draw a line between 8 vertices. It would make sense to create an array of 8 entries of type vector3, because we want to store 3-dimensional coordinates on its cells. Once again, since our Octree nodes are of the cube shape, I will call this cube coordinates. As well as that, we'll immediately initialize the array to provide 8 cells. I will create just one vector, which is pointing from the center of this node towards one of the corners, and then we'll be rotating it around 8 times, sticking each newly formed vector into the cells of this cube coordinates array. Let's point it to the top right corner, and for that I'm gonna make use of the half dimension length, which by now should be given to the node. Then we'll supply to all 3 arguments of this vector3. So we are pointing 15 units in a positive direction of the x-axis, 15 units upwards, and 15 units forwards. And I refer to this vertex as the top right corner. Since we're to the right, above, and when looking from above the scene, we are actually in the positive forward direction, also in the above corner. Just as promised earlier, I'm gonna rotate this vector in a for loop. We'll do it 4 times, and on each iteration, I will populate each corresponding cell of the cube coordinates array with the resulting vector coordinate, the coordinate of the rotated corner vector. Notice that even though half dimension length is 15 to the right, this one is 15 above and this one 15 forward. If we're gonna supply just this piece of information, this will only work for the root, since all of its children will no longer be in the world's 0 coordinate. It's only the root who is sitting there. So we should always add the position of this node to be the countdown, which will serve us as the starting position, out of which we can stick our rotating corner. So after we've stuck it into the appropriate cell of the array, we can rotate this vector. Now the corner will become equal to the corner, which is to be pre-multiplied by the result of the function obtained from the quaternion class, the Euler, since we are rotating relative to the world. I want to rotate by 0 around the world's rightwards axis, but by 90 degrees around the world's vertical axis, and obviously 0 around the forwards z-axis. This coefficient, when multiplied by our vector, will rotate it by 90 degrees around the vertical axis. And then on the next iteration of the for loop, the cube's coordinates next cell will get another different corner. So in those 4 iterations, we're populating the top 4 vertices, and then there should be another for each loop to populate the bottom vertices, the remaining half of the cube coordinates. I will reinitialize and re-specify the information of our corner vector, which we are rotating around, such that it starts to point to the top right corner, but of the bottom part of the cube. So bottom, top, right. This one will be our first of 4 coordinates to be supplied into the remaining half of the cube coordinates. Here it will be just the same for loop. This time x will be not from 0, but starting from 4, all the way up to 8. This line remains unchanged because we are rotating our corner around the position of this node. And the actual rotation should also stay the same, because all we did was to reinitialize the corner vector so that it points to the one of the bottom corners. And then we can rotate it the same way, counterclockwise around the y-axis. So really what happens in reality is we rotate and orbit our vector, pretending that it sticks out from the world's 0 coordinate, and then we displace it towards our position. When we finally have this array with 8 coordinates, the cube coordinates array, this in itself is not enough. The entire purpose of this function was to supply coordinates to the line renderer component. Even though we have 8 coordinates in our array, we still haven't made use of them, and so after it's being populated, we can correct this mistake. Previously in the constructor function, right before this fill cube visualize coordinate function would be called, we've established the reference to this new line renderer component. So we can make use of it here, because it won't be equal to null anymore. First of all, we should be using the world space, not relative to the octant game object, since all of them will be always present at the world's 0th coordinate. So we will use the world space because all of our coordinates in here were stored with the position taken into the consideration. We will set it equal to true. Number of vertices altogether will be 16. This is because you can't draw a cube with just one line going through all the vertices. You have to come back and forth between them so that you have 2 squares joined with the 4 lines. We'll set the vertex count to 16. And the width of the line passing through those coordinates should be about 0.03 float, both for the start of the line and for the ending as well. Otherwise it would be shrinking towards one of the ends. We should now proceed with supplying 16 instructions and pieces of information telling the line renderer the sequence of points through which it should draw itself. And if you look at the signature of this function, it requires an index of the vertex. Of course it will be 1, 2, 3, 4, 5 all the way to 16, and the position of this vertex. They are being supplied in a sequence. To be fair with this line renderer, you can draw any lines, be it the Bezier curve, the straight ones, or the jagged lines, whatever you desire. And it also accepts a custom texture, which is quite nice. The line renderer is much quicker than debug.drawLine or handles.drawLine. Plus it works during the gameplay, which is very nice. This one will be with index 0, this one with 1, 2, and so on. This is a quite repetitive and tedious work, but it has to be done. We could have shoved it into the for loop, but the sequence of the vertex coordinates, which we're about to supply, is too intricate, and it's hard to figure out. So I'm better off supplying it just like this, hard coding it. For the second argument of those functions, we want to reference the corresponding cells of the cube coordinates array. Here, it's going to be the cell number 0, the next one, the cell number 1. And you can draw cube via different paths, but this is the one I've taken, so my sequence will look like this. After we've reached the 4th cell of cube coordinates, we suddenly have to jump back to the 0th one, and then jump to the 4th one. Then it's the 5th one, and then back to 1, and back to the 5th one. The final position with the index 15 will be the coordinate sitting at the 5th cell of the cube coordinates. That is, it will have an index of 4. Just before I forget, for the first for each loop, we did specify that there is an integer x, but it should be starting at 0. When we test our game, we can see that there is a big octree with several lines being drawn,
but when I inspect it closely, you can see that I made a slight mistake, and our corner is not really respecified. Here, it should be pointed to the bottom top right corner, but it's exactly the same as here. To point it to the bottom one, we should just place a minus in front of the y coordinate, since we want to point to the bottom vertices of the cube. There we go. Big, beautiful cube. Later on, it will be subdividing itself with the children, but right now, it's quite good looking already on its own. So having done this and having obtained the clear representation of our Octree node, the root one, we can finally implement the splitting of the nodes so that they can give birth to their children. We've already prepared everything with the constructor function and all the passing of information. The children are already ready to jump on and initialize their view lines such that they can be shown and visualized in the viewport of Unity, similarly to the root that we saw a second ago, the purple one. But really, yes, we need to create a function which is able to split a node and also process the items so that the items can be stored within a node if the number of such items does not exceed the maximum allowed number of items per node. So really several functions. The splitting of the node, giving birth to its children, which will also include passing down the items to the children stored here in this list belonging to this node which is to be splitted. So this is number one. Number two is to process the item. This function will determine if this item is eligible to be added to this list or does not fall in the boundaries of this node and should be ignored. As well as that, this process item function will be actually able to trigger this split function, the first one, in case if there are too many items contained. Really, two functions to make. And actually, let's start with creating the process item function. With its help, we'll be able to store the items in our nodes, be it the root or any of its children nodes. Somewhere after the constructor and before the fill cube visualize coordinates function, which is just for debugging so that we can see the cubes. Right before it, I'll add another function, public, and let's make it a Boolean type function. Process item, obviously. And in there we can supply as an argument the item that we want to check, if it should be stored in this node or not. So Octree item, called, item. Even though our items are attached to cubes, meaning that they have also width and height as well as length, we're going to regard them as points. So in more complicated projects, you would have to consider this extra dimension, but we're going to regard those items as points, because it's the easiest one for this example. It's only the position that we are interested of this cube. So let's see if the position of this cube falls into the octant, and if not, then we should discard it straight away. For such comparison, I'm going to introduce another function, which will be called contains item position, but it's yet to be declared and introduced. It's still not existing. Into this function, as an argument, we will supply the current transform dot position of the item, since the item inherits from mono behavior. Obviously, it's going to be stuck on top of some game object, which will have transform dot position. And only if it's contained within this octant for which we've written this script, the instance of this class, if it contains this position, then we should proceed. Before we forget, let's quickly describe this function, the one that will be figuring out if a given item falls into the region of this node, or doesn't. This function will be very simple. It will be of return type Boolean, meaning that if all the checks are passed, then we return true, and the item is indeed contained in this node. Otherwise, if at some stage it fails, then we immediately will return false, terminating the function right there. See how here we are passing the item transform.position, which is a vector 3, into the function. By that we assume that the function should accept the vector 3 argument. Let's refer to it as item pos in the body of this method. There will be a total of 3 checks. Let's see if we are falling in the x range of our node. If our x coordinate is greater than the x coordinate of the center plus the length, or if it's smaller than the x position minus the half dimension length, so we are subtracting to get to the other side of our cube. If that happens, then the x coordinate falls out from the x range of our cube, meaning that we should return false. Such checks will happen twice more, and in there we're going to be comparing the y coordinates as well as the z coordinates and the z range. If all of those checks fail, and we don't return by now false, we can then safely return true. This item is in fact inside of this node. But coming back to our process item function, the one which checks
if a given item should be stored in the contained item list for this particular node, or if there is an actual overload of items and there are too much of them, meaning that there should be a split occurring for this node. This function does require an item to check, and we're checking if this item's position is inside of this octant, or in other words, the node. And if it is, we can first of all see if this node doesn't contain any other subchildren and subnodes. In this case, let's check if there are already children present within this particular node. And for the first time, I'm going to make use of the reference equals function, which compares the object addresses. And if they are the same, then the objects are literally considered the same entity, the same thing. We're going to check if our children nodes, the first cell, is actually the same as null, meaning that there are no children. Notice that there can be either no children of a node or 8 children at once. If there are no children, then all the children nodes cells will be empty, so we can pick any one. In this case, I'm just picking the first one and comparing if it's null or not. If it's null, that means that there are no other children as well, so we can proceed working with this node and consider if we should store the item here and check if it doesn't cause the split of this node. This is very important to understand. Pay attention to the fact of how I'm using this function. You might have asked yourself, why not you just say children nodes 0 exactly equals to null and stick it into the if statement. Using this operator confuses Unity a little bit. So when you're comparing objects and want to see if two objects are actually one same thing, meaning that not their entries and parameters are the same, but they are literally coming from the same address. They are the same thing. For that matter, we're using reference equals. It's a different way of comparing objects. For instance, let's say I have a twin brother and, I don't know, cloned Igor. If we put double equal sign between me and my clone brother, usually we will get a result as a true, because all of our parameters are absolutely identical. However, we're not the same thing, and reference equals would return false in this case. There is a fine difference, and you should understand it. We will do something here, but for now we should also describe a case when there are children already present in this particular node. Just like I told you before, it's only the leaf nodes, the ones that don't have children, which can contain items and store references to them. In this case, if there are children in this node, we should really pass this item in a sequence to each one of them until one of our children picks it up. We can rely on that because this particular node already accompanies by now the position of this item. So we definitely know that one of its children must have this item, must accept it. It's just a matter of which one and how soon. There are a total of 8 children, so we should iterate through each one, passing the item to those children. To iterate through them, we need to grab the children variable. We don't want to modify our children node's internal variable. That's why let's make use of the getter method. For each Octree node, child node, in our children nodes, for this particular node, and remember that there are 8 children, for each one, let's process an item. So, child node, process the item, and supply an item. The one which fitted into our region of this particular node, but since we have children, we are passing this item further on to this child. And it's quite important to understand. This is exactly why I've placed this Boolean return type of the process item. Imagine that we are pushing an item into the root, which already has 8 children. And the item indeed is falling into the range of the root, but the root already has children. So we are falling into here, and for every child, we're going to attempt to process the item. In 7 of them, the item will not be contained, but in the 8th one it will be. So we should really check if the process item was successful. If it's true, then this block of code will run, and we should really return true. And I'll explain in a second, don't panic. And at the very end of this process item function, we should return false. After we do something here, meaning that this particular node doesn't have children, we also return true. So we are pushing an item into the root has children, and we are in this piece of code. Iterate through every child. Let's look maybe at the top right one, the 0th child. The item doesn't fall into it, because as we call the function process item for that child, that is this function, if the item is not contained, this block of code will not execute and will return false. Because we returned false, this block of code will not be executed within the root, and we will continue to iterate to the next child. If it doesn't contain the item, that is its process item function failed, because it would be finding its way here for the child. Then this block of code will not be ran once again, and will continue iterating through the third child. The third child will get its function invoked, the process item, and it will say, oh, okay, so it's contained within myself, and if that child doesn't have any children, then this block of code will be ran. It might either grab the item and store it, or perform a split, because there would be too many items to contain for it. But if it also has children, then we go through this routine once again, iterating through its own children, until we find a child which is able to accept this item and contain it. In this case, it will return true, and because we return true, we stopped iterating, the whole function returns true, and it's over. Coming back to the place where this function was called from, to the parent will see that, oh, some of the child's function returned true, so we should really return true ourselves, because our child are happy, they have accepted the item, and it's all good. Because we're returning true, we are falling out and finishing this function once again, coming back to the previous parent if needed, and so on. This is exactly what recursion is about. We are really making a call to the function from a function. But it's a very strange kind of recursion. It's not really normal, because we're calling a function from a child. Quite ordinary recursive functions would be something like this, making a call to our function inside of this class. But we are invoking the function from the child. I hope that this doesn't blow your head off, because it's quite complicated. But we are really passing the information, the item, to all the children until we find the child that can accept it. And as soon as it's found, then all the parents are notified and they stop passing this item to other children because it's done. The same happens to their own parents. Such parents no longer pass this item, trying to stick it into some other children. The most important bit is now here. When the item doesn't contain any other children, and we also know that the item falls into its range, there is one important part which it has to perform. The item belongs to it, so it must be accepted by this node, and if there are too many items, then a splitting has to occur, and the new children have to be born. We are almost done. It's just about writing a few more functions and that's it. When the item has to be accepted by this node, we have to process it. I will make a call to the new function, which is to be declared, called pushItem. We really want to store this item in this node. Hopefully it doesn't cause a split, but if it does, then some other actions will occur. The push item will have the following description. It will be of type void and will be private, because there shouldn't be any nodes telling any other nodes to push an item. It has to figure out for itself with the process item function if the item is eligible to be pushed or it should be ignored. So the function is private, it's void, and it awaits for the Octree item. I will also call it item for this function, just so that it's easier to understand. The result of this function will be the item added into the contained items list for this particular node. There might be a split of the node occurring, but it's a different story. And we should only add items if our list of contained items doesn't already mention it. So if contained items dot contains the item argument, and observe that I've placed the exclamation mark up in front of it. Only if it's not contained within this list will we execute the following bit of code, which is all about adding the item to this list. If that's not the case, we will simply add the item to this list. And after this has been performed, let's check if there are too many items in this node to contain, and if it should split, giving birth to 8 new children. We'll be comparing the count of the refreshed contained items list, to which we added the item, with the max object limit, which is the static variable declared at the very beginning of this example, and it is shared between all the instances of Octree node, similar to how the Octree root is shared. So max object limit is 1, and if our list is greater than max object limit, let's say it has 2 items now, then a split should occur within this node, and all the contained items will be passed down into children for potential adding. But this will be the job of the split function, which is yet to be declared. The split function will be the final method we're going to write in this Octree node class, until we decide to do something more advanced, such as the cleanup of cells. But for now, it's going to be the final function. And it's going to take care of splitting this node into its children. adding 8 new children to it, and passing the items for further potential acquiring by its children. Of course, it will be private, its return type will be void. To split a node into children, we have to supply the coordinates, the center coordinates of the future 8 children. For that, I'm going to declare a position vector, which will be initialized with the following arguments. If you're not yet lost, try to figure out why I've placed such coordinates in here. We will iterate through all the children later on, but here, with this vector, I've marked out the position of the first top right child's center. If we slice this particular node with 3 perpendicular planes, we're gonna get 8 cubes, each one sitting in its own corner. And its corner will be exactly the half of dimension length from the center of this particular parent node. So, just as promised earlier, let's iterate for the first top 4 children, create them, and supply the appropriate information to them. Because we're creating a new node, the child node, we should store such nodes in the appropriate children node array of this parent, which can propose to us to use its 8 cells. So in each of those cells, the first 4, the first half of the child nodes, we're going to drop a reference towards the newly created node, the Octree node, because we're creating a child. For the parent, we're going to supply a reference to this, meaning that we're supplying a reference to this particular parent node. This child's position will be the position vector that we've neatly prepared a second ago. It will be the center of this child. And the half length of the child should be exactly the half of our half length. Let's say if from our center towards one of our walls it's 15 meters, then the child's half dimension should be 7.5 from its center towards its walls. And notice that constructor also takes care of the potential items that might be acquired with this child upon its creation. We should supply it the contained items list, to which we've added our new item, which actually caused this split. So we're passing all the items down to this child, hoping that some of them will be acquired by this child. Notice that I've supplied position vector here, but if you try to run this code, it's still not finished, but if it would be finished, you would see that position vector is really supplied as a half dimension length over 2. All is proper, so we're pointing sort of like to the top right corner, but it only works when we count from the world's coordinate 0. And let's say if this new small child at some stage will also have to create its own children, then its actual position, the position of this struggling child, will no longer be the world's 0 coordinate, like let's say the root's position is. And its children with this notation will still be placed to the side from the world's 0 coordinate. So the position vector should be left as it is, but here, as we supply it into the child, it should be relative to our current position of this particular parent node. Similar to how we were specifying the coordinates, we have to rotate this position vector by 90 degrees, so that the next iteration of this for loop will be pointing to the different child in a different corner. Notice the order. Once again, similar to the first example when we did time remapping, this coefficient of quaternion.Euler has to be supplied before the vector, otherwise it's going to be incorrect. We're going to rotate this vector around the world's vertical axis, since the Euler function is relative to the world, not around some specific vector. Therefore, this function is quite quick. I will rotate it by negative 90 degrees in float, but it doesn't really matter. This will just result in how your children are ordered in the data structure. Finally, let's indeed multiply all of this coefficient by the position vector and reassign it to itself so that it's rotated. This will be done 4 times, and we will populate the first half of our children array for this particular parent node, creating the first 4 children and passing the items for potential acquiring by those children. After this half is done, let's reinitialize the position vector to be pointing to the different corner, the bottom one. So I will place simply minus here for the second argument. And of course we will rotate it a couple of times, but this time the I will be from 4 to 8 so that we can index the array correctly and populate the next 4 cells with the newly created Octree node children. Those children will also be passed this item list, and it's all good. After the split has been finished and we've came to its end, created new children and initialized them with all the correct settings, because this parent is no longer able to hold any items and it really has passed them down the children, we should get rid of any contained items here. So contained items will be cleared. It is very important to understand that you cannot simply set it to null. because then you would destroy your list. And if you ever need to add items to it, you'll have to reinitialize it. That's why it's better to just simply clear it, remove all the entries from the parent's contained items list. Two important parts to pay attention to. First of all, I'm going to return once again to this kind of vector that I've specified here. Here, I'm saying that its half dimension length should be divided by 2, but if we would be to debug such vector, we would see that it's sticking from the world's 0 coordinate, and it has exactly half of the length of this half dimension length of this node, but it will be positioned at the world's 0 coordinate. It is very good for us, because we're making use of the Quaternion.Euler rotation, which rotates it around the world's origin, the 0th coordinate of the world. And we're doing this with this vector, which is really sticking from the world's origin, rotating it properly, but then when we need it, we quickly displace it temporarily towards the position of this particular node. Let's say it's not sitting at the world's 0 position anymore. It's some smaller child other than the root. So we displace this vector, which was rotated correctly due to the way where it was positioned, and stick it on top of this position to mark out the center of the new child. I'm doing really my best to explain it, and I hope this is the best explanation possible. I sincerely hope that it's clear enough. When you feel comfortable with this explanation, there is a second point to consider. Because this is a constructor function of the child, when we pass a contained items of this particular node, the constructor function of this child will look at it, and it's going to look something like this, but it's to process the item as well. Notice how the child acquires the parent, it records the dimension that it should be having, and sets its position. It also creates a game object and quickly sets up the line renderer so that we can see it in the viewport. It visualizes the coordinates of such line renderer, but then for every item in potential items passed to it, and this is the contained items coming from the parent, we should process each such item by this newly created child and its process item function. The process item function just checks if the item actually falls into this child, and if no, it returns false. Nothing happens. But if it is contained by this child, then we either push it, maybe actually causing yet another split, or pass it down any other further children, expecting a response from them right here. And if there is response, then the whole entire function is terminated, and we finish. Let me drop this comment so that you understand what's happening slightly better. We can try to run the game, but nothing will happen when we drag our cube around. The cells will not be subdividing themselves, and I will explain why in a second. Basically, there is no way to push an item because the process item function is not ran for the root. In the beginning, when the root is created with this getter method, after our runtime initialize and load method is ran for the first time, when the root is created, the list is completely empty that we pass to it. There should be a way to trigger this root's process item function, and that has to be done every time the Octree item is moved. That's exactly why we stored this previous position in the Octree item class, and every fixed update we are checking if it doesn't correspond to the current transform position of the item it's attached to the cube in our case. But if there is a mismatch, then we do something and we update our previous position so that next frame, if the object is stationary, nothing will happen here. But this is where the interesting part happens. When the position doesn't match, it means that the object has been moved, and we should push it down through the root of the Octree to see if it has to be acquired by the root itself or any other children. This is literally the easiest part. It's just one line of code. We're gonna make a call to the Octree node class and make use of the static function, the Octree root. From the root we're gonna access it. We're gonna ask it to process, well, this item. We can do this by asking just the class, since the Octree root is static. If by the time we're calling it, the Octree root hasn't been yet initialized, the getter method will take care of it. However, I doubt it, because there is going to be already runtime initialize and load method being ran before that. But either way, we're safe, and the root will be initialized, so we can make use of the function process the item, which will check if this item is actually to be added to the system, and if there are too many items like that, then maybe the root has to split itself. There is a very interesting way of how it's going to be handling itself. You can see for yourself. When I create another item in the structure, first of all, nothing happens, and this is because none of the items moved previously. by now the Octree would already have been dividing itself, but since the items haven't moved, there is no mismatch in their positions, so the process item function of the root is not called. But here you go, I moved one, and its position is already set for comparison, and I also moved another one, and as soon as there is a mismatch occurring between their positions, we're able to call the root and see if this item actually falls into this big square, and since it did, there were too many items, meaning that the push function called by the root caused the split after the new item had been added to its list. So if we add another item, or maybe actually drag this one closer, you can see that the octant, the top left one or top right one, couldn't accommodate those two elements, so it splitted itself, and its new child also couldn't accommodate it, so it also splitted itself, and then again. Notice that if I'm inside of here, the scene view viewport, when I start to drag those objects around, changing their position, we are creating dead cells, which are not being cleaned up, and the tree is slowly getting polluted. This is something to worry about, but cleaning up of the tree is a very important subject, since all of this is empty, useless objects, the nodes, which shouldn't even exist. However, with this approach, we can create some beautiful, very interesting structures. And I remember I actually placed those cubes so close together that they would be causing so many subdivisions. And then as I drag them around through this data structure, I could have drawn a three-dimensional cube inside of this octcube structure with the trail that is left behind it. I really love this structure, it's so beautiful. It's absolutely amazing to create something which looks like some sort of Matrix film, you know, science fiction. Very beautiful, and it's all pure recursion. You're creating cells inside of other cells, which is absolutely astonishing. This is the first part of this example, and in it we managed to achieve the first part of the task, where we subdivide the cells and store the items in them. However, when the items leave the cells, such empty nodes still keep track of those items and still think that those items that actually left them are still inside of them. So it's run in several assumptions. All of those cells keep track of those cubes because they think that they are inside of them, which is wrong. And also those cells are polluting the tree and should get removed as soon as possible, as soon as the objects are leaving their domain. In order not to waste any kind of memory, it is absolutely essential that we clean up our tree and don't waste any cells. Yes, we can be traversing the tree at runtime, trying to find out which cells have been abandoned, and that way we will be constantly looking through the tree, and if it's growing bigger, we will have hard time finding the right cells to be removed. Yes, we will be able to locate them, but it will take immense time until we will be able to traverse through the entire tree. Instead, let's take a different strategy. When an item leaves its cell, it has to attempt to reduce the subdivisions, cleaning up this node with its other remaining 7 siblings. There are several checks to be performed in that case, because the siblings of the abandoned node might have their own children with children and so on, which in the end might also have their own elements. So there are several conditions to watch out for, and we will explore all of them in order to complete this deletion task. Because of this approach, every single Octree item has to know about the Octree node which it's being present in, so that later on, if needed, if it's abandoning this node, it can then notify it so that it cleans up itself. Because of this, let's open the Octree item and modify it slightly. As you can see here, in the very beginning of our lesson, we've prepared this variable, my owner nodes, and we called it not my owner node, but we have an S in the end here, because if you're working in a more complex project, not with items that are represented just with points, like in our example, but let's say you're also considering their width and height, maybe working with some sort of colliders and bounding boxes. In that case, parts of the volume of your items might be present in several nodes at once, in the neighboring ones. Hence we put plural version of this word in here. But yes, it keeps track of all the nodes inside of which this item resides. Of course, as we are entering some sort of node, this node has to add itself into this list, and we also have to subtract the old node from this list. First of all, we need to jump to Octree node script and make sure that any Octree has the functionality to add itself, add this particular node, as the owner to any item that's inside of this node. This is very simple. Such functionality can be added into the push item function, which only occurs when we know that this is the leaf node, it has no child nodes, hence it has to accept the item and then maybe perform a split if it has too many items. As well as adding this item to the list of this node, we should also notify this item that this particular node is now containing it. We need to access the owner nodes of the item which we are adding as being contained within this node, and add to this item's owner nodes this particular node. Of course, if the item is already contained within this node, maybe it was moved and then passed down the route, which brought it back here into this place, which didn't bring any change into the Octree data structure. In that case, this code won't be run because the item is already contained inside of the contained items list for this node. So this instruction will be amended as well. But now items will figure out which kind of nodes are containing them, and each particular item can then call required functions and manually deconnect itself from the node which contains it. Of course, now, let's say this item has been added to the root, passed down the children, and somewhere in the end it found out a leaf node. It exchanged information with it and established links. Now this leaf node knows about this item and knows that it contains this item, as well as this functionality that we've introduced just a second ago ensured that the item knows that it's contained within this particular node. But assume then that a split has to occur. Yes, we exchanged information here, but then immediately after that recall that the push item function doesn't end there. There's also a split function which might occur if there are now too many items within this node. So as the split happens, the items are passed down to the newly created children, but then the items have to forget about this parent node, since it's no longer the leaf node, not the ending one, and the items need to forget about it. That's why in the split function we have to introduce such opportunity. In the very beginning, before we start to build any kind of nodes and pass down the items for potential acquiring by new children, we have to ensure that those items forget about this node, which is no longer the leaf node, because it splits. That's why I'm gonna sift through all of the contained items for this particular node, which is no longer the leaf node, and we'll make sure that every single item, OI in my case, no longer contains the reference to this particular node inside of its myOwnersNodes list. It now comes down to several functions, about 3 or 4, which will take care of deleting any kind of references if possible, and removing any kind of obsolete nodes from the data structure. We need to jump back to the Octree item to enhance it slightly more. First of all, let's bring out some of the important functionality into a separate function, which we will call refresh owners. I will make it private in the meantime, because I think it's only the items that should be in charge of such functionality. It will be about cleaning up the nodes that are containing this particular item within the data structure. The fixed update will be looking at the position of this object, and if it moved, it will call refresh owners, which will take care of the rest. As you might have guessed, this line will be moved into the refresh owners function, and we will also introduce some of the other lines. First of all, because the item has moved, there is a chance that the links have changed, and the item is no longer within the bounds of certain nodes. Hence, we need to look through all of the owner nodes which potentially contain this item, and verify that it falls into their ranges. All of the nodes that pass this check and indeed contain the position of this item are going to be stored in the temporary list. We can be creating a new list every single time this function is run, right on the fly. It will be designed to hold the Octree nodes, the ones that have passed the check and do indeed contain this item. Immediately we will initialize it straight away so that we can use it. If you're not familiar with lists, make sure that you check out part 8 of my series, or maybe somewhere in the beginning of this lesson we go through them as well. Just as promised, for every single Octree node, let's call it ON, standing for Octree node, in the owner nodes of this particular item, for which the whole hassle happens because it has moved. For every node like that, let's test if this item is not contained within this node. And apparently our function, which checks if the position is contained within this node, is not public. There we go. Now we can access it. So for every single node that has been marked as my owner nodes for this item, let's see if this item is not contained inside of it. Function requires the position, and of course it's going to be the position of this item. We can make use of the transform.position to get the current position at the current instance of time of this item, because the script inherits from mono behavior. Hence, it's going to be dropped on different game objects. Notice that I've placed the exclamation mark here. The whole thing is going to be true if this function returns false, because the exclamation mark inverts it, making it a true. So if the position of this item is not contained within this particular node, then we have to store such node in another list, which will be called the obsolete nodes. Such list is also initialized every single time as we're running this function. Once again, we're going to be adding this node into this list because it's obsolete. Later on, all of such nodes can be processed and perhaps removed from the entire data structure, in case if they don't contain any other items. But that's another story. Otherwise, if the node has passed a check and it contains the item's position, that means it shouldn't be removed neither from the owner nodes of this item, and the item should remain in this node. The node is valid because it contains an item. It will be added to the first list, the survived nodes. After the entire for each loop has finished, and we've iterated through all of the owner nodes for this item, we now have two lists. One have the nodes that keep containing the position of this item, and also the list of the nodes which no longer contain the position of this item. Yes, they did contain it some time ago, but that's no longer the case, and they have to be processed through some special way. Give me some time and we'll do it. First of all, we need to make sure that the owner nodes of this particular item now reference whatever is made by this list. Don't worry, as the function finishes and the survived nodes gets destroyed, it's just a pointer, literally. It was pointing to the list, to some sort of data structure, and even though the function is over, survived nodes gets destroyed, my owner nodes doesn't point to null or anything. That's a common misconception. Survived nodes is going to be destroyed as the function refresh owners is finished, but the data to which it was pointing is now being referenced by this guy. So the data is not going to be cleaned up and it's all good. Now the owner nodes of this item are just the ones that have survived the check. Right before this function will be over, we have to perform some operations upon the obsolete nodes. Primarily this is going to be about potentially removing such nodes from our Octree data structure. Hence we're going to iterate through all of the obsolete nodes and attempt to reduce the subdivisions, attempt to remove such node with its siblings. I'm going to make a call to the non-existing function which we are about to create. Of course, this method has to be added as the function of the Octree node class. I prefer to chuck it right after the split function. Because we were accessing it from the item, this function of course will be public, and it will be void because it won't be changing or returning any variables. Its name was copied and pasted to avoid any errors. We're gonna do it the following way. Assume the following thing. The item moved and refresh owners function was ran. It quickly sorted out the owners of this item, packing some of them into the survived ones, but some of them into the obsolete nodes, meaning that such nodes no longer contain this item and are subject to potential removing from the data structure. One of such obsolete nodes is being this particular guy, and other ones of course will have exactly the same structure and functionality, so the instructions for them will be exactly the same if they're obsolete nodes. But we're gonna focus on just one particular obsolete node. Its attempt reduce subdivision function will be ran, and at the end of it there are two possible outcomes. Either this entire node gets deleted or survives. This particular node can be removed if its siblings have no children and the total sum of the items contained in this node and the siblings doesn't exceed the maximum allowed number of the items depicted in the max object limit here. That is so that the parent can accept those items without having to split. So first of all, this node has to have siblings with no children, and the total number of items of this node and its siblings should not exceed the maximum object limit. Oh yes, this node shouldn't be a root, because we can't get rid of the root, plus it doesn't have any parent. So first of all, let's check if this node is not a root. We're going to make use of the reference equals once again to compare the addresses of the objects and see if they're actually one single thing. We need to test if this particular Octree node is not actually the Octree root. Octree root is the variable, the static one, which has the getter variable declared here. It is static so that every single node can point to one particular same root. It is shared between all of the nodes. So if this particular node, which is obsolete, is not actually the root, and here we're gonna put the functionality to see if our siblings don't contain children and their items don't exceed the maximum allowed limit. It's gonna be a function which is not yet existing. We'll call it siblings children nodes present underscore too many items. Notice that I'm gonna put an exclamation mark here. Only if the function returns false, and granted that we're not the root, we're gonna perform the following instruction. In the beginning, let's describe it, because it's not yet existing. Private void, and just from its name, it's gonna be clear that we're gonna be checking that it's children, if the children nodes are present within the siblings, and if the number of items, the total number of items, is way too big for the parent of those siblings to accommodate as they get removed. The function will be Boolean, of course. I made a mistake, because it's used in the if statement here. If all of the checks and pitfalls have been dodged by this node, we're going to return false. That's a good sign, because then, as long as the node is not the root, we can proceed to do this code here. But now we're going to be adding tricky parts that are going to be trying to catch and prevent the siblings from getting destroyed along with this obsolete node. Let's create a list of items, such that we can collect all the items from the siblings, then we will drop them into here. Of course, later on we will look at the count of this list to determine if the parent of those siblings can actually acquire such big number of items. Once again, this is going to be one of the valid conditions of actually not getting rid of this node and its siblings. I'll call it legacy items. Here is one catch that will prevent this node from getting deleted. It is the situation where the siblings have their child nodes. As soon as we see that any of the siblings contains the child nodes, that's a sign for us that there is something happening in there. And probably, most likely, there are items in those children. So we're not going to be actually checking recursively if those children contain items or not. Instead, we're going to prohibit straight away the deletion of this obsolete node along with its siblings. For that, I'm going to iterate through all of the siblings of this particular obsolete node, and this for each loop, of course, contains this particular obsolete node. So we're going to be iterating not through the 7 nodes, but through 8. However, it doesn't matter. So if such a sibling node doesn't contain any children, that is, any cell of its children, be it 0, 1, 2, I just picked 0, is actually null, that means that such sibling node doesn't contain any children. This instruction will return true if the particular sibling node has the children unassigned. That is, it doesn't have any children. But we're putting an exclamation mark here. We're gonna execute the following code only if it contains children. If such sibling node contains children, then we're gonna return true. Notice that we are iterating through all of the siblings, and as soon as some of them contain child nodes, we're gonna return true immediately. As follows, the entire function is gonna be ended with the result true. Of course, this is gonna be bad news for us here, because even though this is not a root, this function returns true, which gets inverted by this exclamation mark, prohibiting us from deleting this obsolete node and its siblings. But of course, this is very important, because we don't want to be deleting random nodes. We need to ensure that the siblings don't contain child nodes, so that we don't accidentally delete some important nodes which actually contain items. However, if this particular currently inspected sibling doesn't contain any child nodes, then we should chuck all of its items into the legacy items list. However, make sure that you understand one thing. I mentioned this a couple of times that the Octree items in your later projects might not be represented as points. This is too simple, and we're imagining them as points so that it's easy enough for this example. But if you would be at some stage working with bounding boxes, then your items might actually be in several nodes at once. That's why if at the end of this function we just chuck all of the contained items into the legacy items list, there might be repetitions. To avoid this, we only have to add such items that are not already present in our legacy items list. Please refer to the comments and read them if I'm making you feel lost, because it's very important to understand. Only add the items from the siblings that are not already mentioned in the legacy items list. Because if your items are bounding boxes, you might have actually added them from the previous sibling. You don't want to have any repetitions. It's still very important, so make sure to include this functionality, even though we're not working with bounding boxes, but just assume that our items are simple points. In order to do this, we have to make use of the library called link. And I love it because it allows us to simplify the immense for each loops into very elegant lines of code, which are most of the time just one single line of code actually. Consequently, we're going to be using the link namespace originating from system. Please pay attention to the comment that I've written here. Because we're making use of link, we can now write a very short line of code, which will require some understanding, but I'll make my best to explain it. Currently, we are looking at the sibling, some sort of node in the Octree. It has items which were marked as contained because they are inside of its contained items list. From such list of the sibling node, we want to extract such items that are not yet mentioned in our legacy items list for this entire obsolete node whose siblings we are inspecting. Because of this, we're going to be adding to the legacy items another list from this particular sibling, not just the contained items of this Octree node. Actually, I'm going to rename it to sibling. Should have done it in the first place anyways. So sibling, sibling here, just to avoid any kind of confusion. So not simply the contained items of that sibling, but a slightly modified version of it. Here is where the power of link comes in. Looking at that list of the contained items, we're going to extract another list from it, such that, and we're going to be using the function where an item of that list, let's call it I, has a form of, and we put n equals and then greater than sign, has a form of not being contained in the legacy item list, this one. So the legacy item doesn't contain this I. And the link is so powerful, it knows what I is, because it can see where this where function came from. Because it came from the contained items, immediately link sees that contained items is actually a list for storing the Octree items. So I is immediately being cast and interpreted as an Octree item. Hence, we can check if it's being contained within legacy items list. By the end of this function, where is going to make sure that it extracts the modified list of all the items that are not contained already in the legacy items list. Then we're chucking in the resulting collection as a range to our legacy items, extending it slightly further. If you're interested to know what a collection is, I'm not going to complicate you with that, but it's like an organized pile. Similar to list, array, it's a collection through which we can iterate from an element to an element, but it's different to list. You can see that if I make a call to any random list, I'll remove it later on anyways, don't worry. Then make a call to add range, it requires an IEnumerable, which is a collection. IEnumerable is exactly what's being returned by the where function, which is the culmination of this line. For instance, let's make the call to the where function just for the sake of the example. Here you can see that it returns a collection. Once again, I'll not bother you with that. All you have to know is that addRange requires a collection, the IEnumerable, and where is able to provide such collection. Hence we can add those extra items to our legacy items list. The add function, on the contrary, would only accept one item at a time. In that case, we would have to do a for loop, and it would take an immense time. Link is very powerful. Just extract the needed portion, the needed pile of items, and stick it on top of our legacy items, all at once. Of course, there is something going on behind the curtains, and most of the time, if you hardcode the for loop, it will be actually quicker than link. But it's much more user-friendly to use link instead of any loops. I was silly when I placed this line outside of our for each loop, but it should be inside of it, of course. As soon as we find out that a given sibling node doesn't have any children, we can then proceed to steal its contained items, that is, draw references to them. Then we can add them to the legacy items with the addRange function. Then, later on, we will look through another sibling of this particular obsolete node for which we are working. If any sibling at any time would contain child nodes, then we would return true and the whole function would end. We then wouldn't be able to delete this particular obsolete node as well as those siblings, because one of them had child nodes. Another catchy part, where in the end it might return true, prohibiting the deletion, is the simple check. Let's see if the total number of collected items from the siblings is way too big for the parent to accept when it deletes those sibling nodes. Then we simply will not delete them. How did we call our static variable? It's max objects limit. If our legacy items.count exceeds the maximum number of objects limit, then the parent won't be able to hold such a big number of items from its assassinated children. Finally, if all of the checks have been passed successfully, all of the siblings didn't contain any child nodes, and the number of items within the siblings doesn't exceed the maximum item limit, then the parent will be able to accept those items, and the whole function is able to return false. This result will of course be inverted, and as long as this particular obsolete node is not a root, then we will be able to delete this node as well as its siblings. The items from the siblings will be of course extracted and will be passed into parent, which now would become the leaf node. Notice that if the object would be the root, that is, the first part of this if statement would come out as false because of the exclamation mark, then the second check wouldn't even be required to be ran, and we wouldn't actually start to work with the siblings, which would be a definite mistake since root doesn't have any siblings because it doesn't have parent. But we wouldn't get there. The if check would immediately stop as soon as the first part of its condition would be false. Please pay attention to the comments that I've placed here. Look what we have in the end now. The moved Octree item identified which kind of nodes were obsolete, and now for every single one of them it called this function. We're just looking at such one poor Octree node that is potentially to be removed. Its only chance to survive is to fail this instruction. This instruction makes a call to the siblings, children, blah blah blah, present or not, or too many items function. If it returns false, then its fate is done. It will be removed, as long as it's not root. But in the case if it survives, then we only have to say goodbye to the item that left this node, since otherwise this node wouldn't even be in the obsolete nodes. We're gonna remove this item from the contained items of this node. But this node, as well as its siblings, won't be removed. And, we need to know which item we're removing, right? So the item which actually formed all of the obsolete nodes and called this function within this node actually should identify itself. As it's calling this function for every single one of those obsolete nodes, it should pass itself as an argument. And the function of such node should be able to receive such argument. So the Octree item, and we'll be calling it escaped item. And that's the end of the function. The only thing left to do is to specify how we're deleting the nodes and the siblings if they were too unfortunate and this function returned true. Now it's just a matter of specifying what we do here for any nodes which weren't so lucky, who didn't have children, and there were not too many items within their siblings. Such node along with its siblings will be removed. Let's iterate through all the children of the parent of this node. Such children of course will include this node. For every single node like that, we will invoke a kill function, kill node. This method doesn't exist yet and we'll add it in a second. After this is done, we need to make sure that the parent's children get erased because they were killed and the reference to them should be dropped. We're gonna call the erase children function, which is also to be created. Don't worry, it's gonna be very short. As we're making call to the parent, of course it's gonna be just the same Octree node, so we might as well add such function to this class. I'm gonna add it right after I'm declaring our children nodes variable. It will be public because it's gonna be called from other nodes, and will be void. It won't be returning any result or any value. Won't be taking any arguments, and the single thing it will do will be about reinitializing its internal variable of children nodes, not the exposed one, which has the getter method, but the actual internal one, the private one. It will be initializing it to be pointing towards a new array with new empty 8 cells. Of course, this function can be called now from here, from this poor obsolete node, which is to be killed. So the parent should erase its children nodes, and notice that this call is done after the for each loop. This instruction only has to happen once. It doesn't have to occur every single time we're killing a node. The parent would be very sad in this case. Just do it once after. Putting it like this might be very confusing, and I'm not too sure Unity will be able to handle it, since we will try to kill this particular node before this thing gets called. Otherwise, if the node shouldn't be deleted and its siblings should also remain, then we're just removing the escaped item. Well, let's just put an else in this case, so that we're safe. Don't worry, it's just a matter of writing the kill node function, and we will be done. How do we dispose of the nodes? It is very simple. The method will be private for now, will be void, and it will take an array of the sibling nodes, as well as the escaped item. Recall that the escaped item is the actual item that was moved, identified all the obsolete nodes in which it's no longer contained, causing this entire hassle of potentially deleting nodes. Because we're killing this node, we have to drop the reference to all the remaining items that we were holding, because those items will be anyway accepted by the parent, as this node dies with its siblings. So for each Octree item, OI, in the contained items of this Octree node that is obsolete and is to be removed, we're going to make sure that such item modifies its owner nodes. And here is where the power of link comes again. Instead of sifting through the items with a for loop, we're just going to extract the list of such owner nodes from this item, such that none of the siblings of this poor obsolete node are included. Because my owner nodes of such items are actually generic lists, remember that the result of any culmination, such as except, where, or whatever provided by link, is always a collection. You have to cast it down to list with this line of code if you want to assign the result to a list. Alternatively, you can do it to array, but we got a list on the left side, so it should be list here. I'm gonna drop a comment so that it clarifies things a bit. Because where we're working with the sibling nodes, we should also not forget the Octree node on behalf of which we are getting reference to those siblings should also be removed from the owner nodes of such item. Finally, after all this hassle, when we removed the reference to this obsolete node, throwing them back as being contained by the parent, we now have to actually notify them about being contained by this parent, as well as tell the parent that it now has to contain those items. Because we're iterating through every single item of this obsolete node, which is about to be removed, we can operate with the currently inspected item. By the way, if the item escaped this node, by the time this function would be called, the attempt to reduce subdivisions, the item would already register itself to the siblings, if it would be moving into their direction. Make sure that into the owner nodes of such item, we add the parent of this poor, about to be killed, obsolete node. We can amend this keyword, because it's implied. And also notify the parent about this item by adding such item into the contained items of this parent. Of course, after we've deleted the virtual spirit, the soul of the Octree node, we should also get rid of the octant game objects, the entities which are holding our line renderers and the purple outlines, making the cubes visible to us. They don't have anything behind them now, since their soul and spirit has been killed. Let's just destroy them. Once again, we can get rid of this keyword, since it's implied. We were building this function as if we would be passing the obsolete sibling nodes of this node which is about to be killed, as well as the escaped item, but we didn't pass anything here when we were making call to this function. In fact, escaped item, from what I see here, is not actually necessary, so I'm gonna get rid of it. We only need one argument, which is the siblings of this node which is to be removed. As the argument of this function, I want to pass an array. It has to have 7 cells. If we're just making use of the parent.children nodes, we're gonna get 8. And we don't really know where this particular node is sitting at. Maybe place 0, maybe place 2, 3, 4, 5, we don't know. Let's give link an opportunity to expand its power with its where command. We want to extract from the parent's children nodes only the nodes that don't actually equal to this particular node. And then we're casting it down to an array, since the result of the where culmination is going to be a collection, and collection is not accepted by our argument. It requires an array of octree nodes. Just as you can see here, by rewriting this bracket, we do require octree nodes, but the where function would return a collection and IEnumerable. So we're killing all the children nodes of parent, and every such about to be executed child does something with its siblings. Oh, and yes, if the node actually survived along with its siblings, we're just gonna remove the item from its contained items. But the item should also forget about this node. Therefore, we're gonna make sure that the escaped items owner nodes, my owner nodes, removes the reference towards this particular node which managed to survive, since the item no longer falls into the domain of this node. Debugging is a very essential part of building any kind of data structures, and it can be very time-consuming. When I was building this data structure for the very first time, I actually had to improvise and not only use the debug console here, providing the errors and correct messages, but actually when I was creating the game objects that were holding those purple cube outlines, to such prefabs I also added child game object with a text mesh that would be debugging to me how many items are contained in those nodes, what children, etc. Here, thank God, any kind of errors are very clear. If I start the game, place my cube into the root, move it slightly so that it's registered within itself, because there would be a mismatch in position, and also this guy, we subdivide the root into several cells. But if I take this item and bring it outside of the root, this root doesn't clean up its children, even though we've written so many functions. And if I grab this item and bring it out, only then will our root clean its children. What's happening here? I've placed two commands into our sibling children nodes present too many items function, which is, as you recall, the last chance of the node, the one that has been marked as obsolete, to survive along with its siblings. Two cases when it can survive is when function returns true, here and here. And in this case I'm saying, okay, too many children, debug this information, and also in the case when there are too many items, also debug this information onto the console. That way I can see that as I'm starting the game and populating the scene with the items, when I move them and register them in the root, creating other children, pushing down those items into the children, when I move away this item from the root, you can see that we couldn't delete because there would be too many items. But why is it so? Didn't this item just escaped this quadrant or octant? There should have been just one item in all the siblings and this octant together, or not. If you look at the function and how it's ordered, it's a very tricky logical error. Notice that this function, the last chance, is getting called by the potential attempt reduce subdivision function. First of all, we check if this potentially to be removed node is not a root, and if its siblings have children or have too many items, then we proceed to kill it and erase children. But notice what happens here. This last chance function gets called and it begins to count the items contained in the siblings. As long as the siblings don't contain any children, we're gathering all the legacy items one by one with big piles from all the siblings until we've built the legacy items list. However, this legacy item will contain the item that has escaped and caused this whole hassle, because the item, if you check here, as soon as it moves, it does build the obsolete nodes and survived nodes, and for every single obsolete node, it attempts to reduce subdivisions, but nowhere does it remove itself. We don't remove the item from such obsolete node until we actually kill this node. And if you see that the last chance function, which is here, is actually called before the kill node. So in this current state, the node which is potentially to be removed still holds the reference to the escaped item. And as we are packing up and counting those items from siblings, this particular node around which the whole hustle happens will also include this escaping item as well. So just to solve this problem, we can add a +1 to our max object limit, because our legacy items will always have the escaping item, which after that gets removed anyways. Just expand our border by a slightly bigger amount, by 1. Another alternative would be to add the argument escaped item and only add the items to our legacy item list, such that those items don't equal to the escaped item, which of course once again would have to be passed as an argument into this function. This is a very intricate flow of thoughts, and I really do respect you if you manage to listen to this part and attempt to understand it, because this data structure is absolutely mind-blowing. Finding friends that actually share my passion is so valuable to me. Hopefully you are able to understand it and comprehend its beauty. Let's jump into here and see how we fix this problem. So as soon as I take away this element, our data structure gets cleaned up and it's all good. Finally, I don't like how I have to place the item creating it and then move it slightly to register it in the data structure. As soon as I create it, it should be already registered within it and pushed into the root. Previous position is going to be immediately initialized to 0 as soon as this Octree item gets created. If we remove this line, the vector 0, 0, 0 is actually going to be mismatching with the current position of wherever this cube is placed at. But there is always a chance that it's going to be placed exactly at 0 and the refresh owners won't occur. So let's maybe just in the mover script, when we're left clicking and creating an item, let's just call the refresh owners function to push the item into the Octree root. Right here, as we're creating the new cube game object, we can get component, which is guaranteed to be stuck on this prefab, because if you see in our resources, the cube prefab contains the Octree item monobehavior. So we get the component, the Octree item, and then from there we call the refresh owners. And I can't see it. I thought it would be private, but let's make it public. Now, as soon as we create this item, it's going to be pushed down into the root. And that is how the final Octree looks like. It cleans itself up, and perhaps maybe you want to set up the depth limit of how deep it can go, because sometimes recursion might go so hard and so deep, Unity will actually terminate it, and you will have forever dead nodes with so many children that the recursion would be actually stopped, and those children wouldn't manage to register any kind of items. They would forever remain there, uncleaned. You might want to set up the depth limit of how many children every single node can have. That will go into the split function. Beautiful, it's so good. This data structure is absolutely amazing and just as astonishing as red-black balanced binary search tree, the self-balancing BST. Absolutely amazing. Wow. Recursion is an essential part of anyone's code, especially if you have to calculate many branches of information that belong to your code, if it has data structures, artificial intelligence systems, such that its parts depend on each other, and you have to recursively traverse all of them and their connections. But recursion is an excellent way to update many items and their neighbors, maybe create objects one after another recursively, like I've shown you before, with just one command. This command triggers a function, and we know that as long as we don't go above our allowed iterations, the function will be calling itself, falling into recursion via different rules. Similarly to how we were creating objects, we created the big main object, which called the function for the left branch. This whole function started to invoke left branches until it hit the allowed limit. Then after that, we would be returning to previous instances of those functions, traveling to the right of the objects, returning back once again, inspecting the other remaining branches. The way the whole recursion works is it populates the so-called memory stack, about which I'll talk in a second, but it takes this space on RAM and populates it with the function calls. The memory stack itself is a location on RAM with a fixed size, to be precise about 10 megabytes as of 2015.
When you're calling functions without first terminating those other functions, you're leaving a trail behind yourself, because you're calling function A, it goes on the stack to be executed, but before it manages to finish, you also issue another command to call another instance of this function, which goes on top of that function in the memory stack. Before that other function manages to finish and get removed from this memory stack, there is another function which comes in, also going on top of those functions, and so on. That way you can see that quickly this 10 megabyte limit can be breached, resulting in the stack overflow error. To avoid this, you have to access the functionality of such functions in a different way. There is a need to keep track of which stage you're on currently, but we have to move ourselves from using the memory stack and relying on it to keep track of what functions are to be called and when. We have to move ourselves from that and begin using the data structure, which is also called stack, but which is allocated on the heap. Heap is another region of your physical memory on the RAM, and it's much bigger than your program's memory stack. Heap is almost as big as your entire size of RAM. Right now I have 13 gigabytes of RAM, so my heap is about that size, maybe slightly less, because some of it is reserved by the operating system. But anyway, if we're keeping track of our functions via the stack data structure, which is sort of like linked list, but are placing it on the heap, then we will not experience this stack overflow, since we're going to abandon using the memory stack and we'll be using our own custom stack data structure, placing it on the heap. To do this, we have to refactor this whole function, our recursive one, such that it no longer calls itself from within itself, but there is some sort of while loop. The main body of this function will depend on it, which will keep on running, executing some bit of code, but we will not be populating the memory stack with those calls. You'll see in a second. It's quite complicated when you hear it for the first time, but trust me, it's not going to be that difficult. To achieve this, I'm going to comment out any iterations, modifications from here, and the function create smaller duplicate has to be only called once. I'm going to comment out the redefinition of displacement vector so that it's never changed, and we'll, just as promised, comment out the second call of that function. So really what we have right now, and actually I'm going to get rid of this whole code because it's just sitting there. Really we are having one vector displacement, which is pointing to the left of our big main parent sphere, which was just created, followed by calling our function, which is currently recursive, but is soon to be altered into a stack form. And presumably this whole function will create all other spheres, the duplicates, on itself, but without actually calling instances of itself, of this function, over and over again. That's the trick that we have to do right now. So with that said, the function will be called once, and we have to ensure that it creates all the objects, all the duplicates, as needed. And at the beginning, it will always have the position relative to parent, which is slightly to the left from it. I'm gonna get rid of the iterations, and we'll remove all of this code as well. This function is no longer recursive, and if we try it in Unity, I'm gonna stick my sphere into the slot. Doesn't matter what iterations we put, if we press place object recursively, it will just place one sphere because we've just cut out all of the code. So it's literally just as if we would be starting from the new empty canvas. Because we want to avoid the recursive nature of the function, we have to keep track of which stage we are currently on and how far we've been into this virtual, not really recursion, but this virtual pattern of ours, traveling to the left, and then we would have to come back traveling to the right. We have to keep track of how deep we went. And for that, we're going to be using the stack data structure, which is going to be used for holding integers. I will call it branches, and we'll initialize it to be a new stack used to hold integers. Of course, it highlights with red because we didn't include the namespace called system.collections.generic. Now you have to understand the importance of this thing. Why did I place it here? Well, as we're traveling to the left of the main parent and create objects, we have to keep track of which branch we are looking at. Did we go to the left or to the right from whichever object was the parent? And therefore, the stack, even though it's used for holding integers, will only be holding two values. It will be holding 0, which will mean that we went to the left, and 1, meaning that we went to the right. As soon as we see that there is a 2 or 3 or whatever, anything that's not 0 or 1, this means that we've inspected both the left sides and the right one, so we should come back. as soon as this data structure is created, we want to push at least one item, the integer. I'm gonna place 0 into here. Whatever happens, we will always search from left to right. This means that we went to the left. And now the most important part is when I introduce the while loop. While something happens here, we'll be running it over and over and over again. And I'm interested to run this code inside of here as long as branches contains at least one item. So count is greater than 0. Because there is always going to be at least one item here, this code will run at least once. Immediately I want to see where did we go, to the left or to the right. So I'm going to extract whatever is sitting on the top of this branches stack by using the pop command. If you don't remember or don't know how to use the stack data structure or any other data structures, you can roll back in time of this particular tutorial, checking out the part where I explain how it works. It's somewhere in the middle of the lesson, I think. But we are extracting the top element, the top number, and we will be using it in the newly declared variable called explored branch. Because we are calling this function only once from the big parent, it will start, we'll create a stack, we will push a 0, meaning that we want to go to the left. We will start this code, it will run for one iteration, because as soon as we pop an element out of it, we are removing this single item that we placed previously, and now branches will have count of 0. Therefore, the while loop will fall out and we will end the function. But that's not everything I wanted to do here. It's slightly more complicated than that. Let's see if explored branch says that we went to the left or to the right. So if explored branch is exactly equals to 0, then we will do something. Otherwise, if explored branch is exactly equal to 1, we went to the right, hence we should do something here. Let's consider the case where the thing that we've removed from the top of the stack signified that we went to the left. We should get hold of the current position of parent, and based from it, maybe add a leftwards direction to that position of parent. So instead of actually receiving the vector 3 position relative to parent, I will substitute it with the transform type variable, transform of parent. Of course, here we won't require the displacement vector, so forget about it. It's no longer existent. When we are calling this function, we want to supply the transform of the placed object, the big initial sphere, because we'll be working with it. So the function is called, into which we initially supply the big object, which is created, as long as it's transform and the scale that the first duplicate must have. In fact, let's remove the scale as well. So only the big object and its transform. That's the entire thing that this function receives. So now it has only two arguments, the parent and the transform of parent. If after we've popped the top item from our branches stack, if it's 0, then we went to the left from the parent, so we should create a duplicate there. Otherwise we went to the right and we should create a duplicate to the right of the parent. We'll declare a variable of type GameObject, we'll call it duplicate, and we'll instantiate a GameObject, similarly to what you've seen previously. Of course it will be based on the parent that was supplied into the function, since we're replicating it as we're creating more duplicates. And the same thing will happen if we went to the right. The real story happens when we decide where we want to place them. Since we went to the left here, we want to place it to the left of the parent. I'll quickly teleport it to the appropriate leftwards position, which will be based on the transform's parent forward direction, to which we add the transform of parent, which is of type transform, dot forward direction, to which we add direction to the left. So right, and it has to be with a negative sign in front of it. And also this newly created duplicate has to have its local scale to be altered by 2. The same thing will happen if we went to the right branch, with one exception, that we are indeed going slightly to the right from the parent. However, the while loop will only go once, just as previously, because we are creating branches, the stack, we are pushing 0 on it, and then we are immediately pushing it out, and we'll execute this bit of code. But then, since we've pushed out the only single thing it had, by the time the while loop is ran again, it will see that the count is 0, so it won't repeat itself. However, we want to continue, and as long as we didn't breach and went past the allowed limit, the iterations variable that we made use of previously, we should continue running our while loop. That's why, after we've created this duplicate, let's see if the branches.count is actually greater than the allowed iterations. And if it is, then we're going to do something. Of course, we'll do the same thing on our right branch. There is a problem with us popping the items like this immediately at the start of the while loop. Instead, let's change it to peak and see what happens. Peak allows us to see and copy the value of whatever is on the top of the branches stack without actually removing it from the stack. So at the moment, we are not removing anything, and because of this, this while loop will run indefinitely if we dare to test it in Unity. However, we can now continue working here and here because we are able to accumulate the count of explored branch by adding extra numbers into it if required. So this bit of code means that we will come back, and also this one. However, if we still haven't breached the allowed iterations with the count of our branches stack, this means that we can continue to go forward. We will do exactly what was done here. We will push 0 into our stack. So we're going deeper, and we're pushing the indication that we're going to the left. The same thing, also going to the left, will happen in this part of code. I'll actually add the further word to indicate that we're going further. But what happens when we exceed the value of iterations with the count of our branches stack? Obviously, there are too many items inside of it, too many numbers. We should stop creating any objects, removing whatever is on top of this stack, and coming back with the next iteration of while loop. We will do branches.pop. Since it's a function which returns a value, as you can see it returns integer, we have to assign it to something, but we'll not be ever using it. Because we've removed something from the top, after this code is finished, the else statement will not be ran and the while loop will end. Since we removed something from the top of the stack, as long as there is something inside of it, we're going to copy the value of whatever was sitting under this element, because we're looking at the new top element of the stack. However, right before we do it, we should iterate whatever element sits underneath of it by 1. So we'll declare a variable called the one that was under the previous element that we just disposed of a second ago. It will be whatever is on top of the branches. I will pop out whatever sits right now on the top of the stack at this current state of time, and will immediately increase it by 1. Then after that, I'll place this value back into the stack because I wanted only to increment it. So I'm pushing back our was under previous element number. This is exactly the same thing that's going to happen in this part of code when we were investigating traveling to the right branches. Don't freak out, we're almost done. Let's see what happens when this function gets called. So initially we're creating the big sphere, and then immediately we're calling our function create smaller duplicate. And actually I'll place create smaller duplicates because it takes care of everything in just one function call. So we're calling create smaller duplicates, and we're supplying this big gigantic sphere as the first argument to be referred to as the parent, and we're supplying its transform. Here it's referred to as parent and the transform of parent. We are creating a stack of branches to indicate which branches do we investigate. And initially we're saying, let's do branch number 0, the left one. As long as there is at least anything in our branches stack, at the moment we have one element, we're going to continue executing this while loop. We want to see what's currently at the top of this stack without actually removing the top element. We're just glancing at it. At the moment, explored branch will be 0 because that's what we've pushed before we called this while loop for the first time. So it's going to be 0. And we're seeing that here it's 0, so we'll execute this bit of code, and we'll not do this one right now. We're doing this bit of code, and we're creating a duplicate. We are teleporting it where it should be, as well as change its scale. Now, as long as we didn't exceed the value of iterations with the number of items stored in our branches stack, currently we have only one item because we picked at it, but didn't yet remove it. It's the count of it is 1. There is only one item in branches. So this thing is false because we didn't exceed the iterations. So we're executing this bit of code. Since we push 0 on top of it, the count of branches will now have 2 elements. This block of code finishes, we finish the iteration of the while loop, and we attempt to do it a second time. Is branches.count greater than 0? Yes, in fact now the branches contains 2 elements. So it's greater than 0, we continue executing it. We look at the top element, which is now 0 once again because that's what we've placed previously, and we'll be going to the left even further. If explored branch is exactly 0, we're going to create a duplicate
transform it where it has to be, change its local scale appropriately, and see, did we exceed the iterations, the value of iterations with the count of our branches? Assume that we did. Let's say that our iterations was something like 1. As soon as we exceed it, we will no longer be pushing the numbers into the stack, but we will instead remove whatever is sitting on the top of it, and we will increment the item that was sitting under it by 1. So since we started with 0, pushed 0 on top, here we saw that actually 2 would be too much, so we removed this 0 from the top, and because the first element that we placed into the stack was 0, we are increasing it with 1. So now our stack contains just 1. We are finishing this instruction, didn't do this else statement. Our while finishes and attempts to do it once again. Branches.count contains 1 element, which is greater than 0. We are looking at whatever is stored on the top of the stack, and since it's exactly the integer 1, explored branch is 1. This bit of code will not be ran, since it's only executed when the explored branch saw that there is a 0, but we instead do this one. Explored branch knows that currently at the top of the stack there is an integer 1, so we should be doing everything, positioning the objects, creating them on the right direction. Because the iterations are not exceeded, since there is only 1 element in the stack, 1 is not greater than 1, so we're pushing 0. And currently our stack will have 1 and 0. Of course you can see that we're going to do now the left branch, then the right one, then come back, and so on, until eventually when the element will be 1 and we increment it by 1, either here or here, at some stage this element to which we are about to return is going to be 2 in the end. And when it's 2, this means that we also should come back, since we've inspected all of the branches. We looked at the left one, changing the value to 1, meaning that now we should inspect the right branch if we ever come back to this element. But when this number would be incremented to 2, this means that both left and right branch have been inspected. So there is nothing else to do on this element, and we should come back even further. This is the case, the third case, which is going to be specified here. So if this is not true, nor this is true, then we looked at the both branches. And to come back, we are just doing this. We are removing whatever is on top of the stack, and we are incrementing whatever element is going to be before the one that we are abandoning. Notice that here I do this 3 instructions, but here I just did the 2 ones. I forgot about this line. So I should also include it when we're coming back from the right branch. Since this block of code is only ran when we've inspected both left and right branch, it's very important to surround this code in guards, checking that there is actually something to come back. Otherwise, if we've extracted the last element, there will be nothing to come back and nothing to pop out. This line of code would produce an error. So we should check if the branches.count is still greater than 0 and there is something to come back to. Otherwise, we would be satisfied by just this line of code. With this, I think the code will be working properly, but there is still one thing that I was trying to avoid all the time, which is talking about how we are creating duplicates and are adjusting their local scales. The thing is, as we are calling this function, after we've created the big sphere, supplied it as a first parent and a transform, the first creation of a duplicate will be okay, but after that, they're gonna get messed up. That's because we are never changing the parent from which we are creating objects. However, as soon as we're traveling deeper, we should actually reassign the parent to be whatever duplicate we've created a second ago. We should be really basing the displacement vectors on the transform of the current duplicates that we've just created, since they themselves become parents after they've been created. In that case, since we will have to come back to them at some stage, we cannot be really reassigning their transforms to the transform of parent variable here. Instead, we should create a stack so that we can come back to certain elements after we've popped out other transforms from this stack. The stack will be of type transform and will be called parents transforms. Just during the initialization stage, when we've just started this function and didn't even begin our while loop, we are creating the stack of branches, pushing 0 into it, so I'll move it closer to this line of code so that it's clearer. We are declaring the stack of transforms, where we'll be stacking the transforms of the duplicates, since they will be serving as parents at some stage.
But we should also push the first transform, which is the supplied transform of parent, the first time this function is called, we receive it. We should push it onto the first spot of the transforms. Now we will be basing the creation of our duplicates not based on the transform of parent, but based on whatever is on top currently of our parent's transforms stack. So parent's transforms dot peak. The result of this command will be a transform at which we've peaked. So we're receiving reference for this transform without actually removing it from the stack. And since it's transform, we can access the forward direction. The same thing will happen when we want to access the rightwards direction. So we're displacing it to the left of the transform which sits at the top of this stack. I'll do the exact same thing for the part where we're traveling to the right branch, right here. However, now it's very important to make sure that as we're creating the duplicate, we're gonna stick its transform on top of that parent's transform stack with a push command. And the exact same thing is gonna happen for the right branch as well. When we are coming back in this part of code, from the parent's transforms we should remove an element. So we're gonna do pop. And the same thing will happen here as well for when we inspected the right branch. And finally, when we're coming back after we've inspected both left and right branch, we should remove the top transform from the parent's transforms stack in here as well. We know that it's going to be okay because otherwise branches.count would be actually 0, since the counts of parents' transforms and branches grow synchronically. Finally, the local scales of objects, when we're creating them, should be halved of whatever parent's scale they have. So the same thing will happen here. They will become equal to whatever their current local scale of the transform of their parent is, so local scale, but halved. And I'll do exactly the same thing for the right branch too. This was a very complicated example, and I did my best to explain it properly. I hope you understood it. It's quite hard to find any explanation right now on the internet about transforming recursions into stack forms. I hope you understood it, but don't worry, it's quite difficult to grasp. And if you got it, you're on the way to become an advanced programmer. Just to check the errors in Unity, let's go into console and I'll double click on this error. Let's see what it says. Of course, there's an error here because I should actually push into the parent's transforms the transform of the duplicate that we just created a second ago. Sorry about that. Let's do this here as well. Also this error. This error is slightly more subtle because as we are popping out a value, we cannot really increment it because it's just a value. There is no variable behind it. The action of popping anything from the stack means stopping to reference it as the top element of the stack. In this case, since our stack was used to hold integers, we're just splitting out the value. But we cannot use this operand on this value because there is nothing to increment, it's just a value. Instead, we want to use +1. We want to get this value and store the value which is greater by 1 into this one, was under previous element. The same thing should be done here too. And here. Finally, the last error. And of course I was silly. Branches.push is a function. It should not become equal to anything. We are pushing this value inside. I think I did the same mistake here. Yes. So we're pushing this value into the branches when we went too far. This is just a warning. This error actually comes up because, yeah, push is a function and also should be called here like this. That's because the way we are popping out values, killing them, we are assigning them to a variable which we never use afterwards. I think it's not going to be a problem if we get rid of this call and just use pop, removing whatever sits on the top of the stack, just like this, killing it. Branches.pop here and here as well. We can check out how it's working, but since I was doing it on the fly, explaining everything from scratch, there is probably going to be an error somewhere, the logical one. I'm going to try to debug it, and you can see the process of how it's happening. So let's do 4 iterations. I'm going to click on the cube and place several objects, invoking this function, starting the while loop, invoking our pseudo-recursive stack form functionality. Let's hide the cube and see what happened to the spheres. I'm going to select this sphere and focus on it. I will unclick the button because it has to be unclicked so that I can operate with the objects. We'll press W or click here and we'll move it to the side. You can see that the sphere is actually here. So this one is the first one, that one is the second one. Now this one sits inside of it, and I suspect the further one, this one, yeah, it's also inside, right here. That one is probably even more inside, and I suspect the iterations would be already breached by our count of this stack. So yeah, I'm gonna select this one, and it is to the right of the transform. There is definitely a problem with the transform and our stacking of them in the stack of transforms. So let's inspect it closely. There are several things that I found out. The first one of which is that as we're creating a duplicate here, we're immediately putting it on the transform list. However, here, notice that we're only pushing the branches and deciding to traverse further only if we didn't exceed the iterations. Otherwise, we actually remove something from the stacks. So pushing the transform into the parent's transform stack should only happen when we've decided to go further. Otherwise, we are removing this synchronous nature of growing our stacks, both the branches and the parent's transforms, meaning that they wouldn't be growing synchronically. From there, I'm going to remove it from here and put it in here. We'll remove it from when we are inspecting the right branch too, and we'll put it where it should be when we decide to go further, deeper. And down here, when we've looked at both left branch and the right one, when we're deciding to roll back, I think everything is okay. Also, we are positioning the duplicates, teleporting them after they've been created, both here and here, based on the transform.forward direction. Even though this is a vector which is relative to the transform of that parent, it's just a vector with a magnitude of 1. Whatever happens here has to be supplied in the world space. For the simplicity, assume that all the parents' transform are aligned with the world. So this will return a vector of forward, which is 0, 0, 1, and this is going to be the vector of minus 1, 0, 0. Since there is a minus, we want to go to the left. That's okay and fine. But later on, if we decide to go even further to the left, we should create those further duplicates based on the position of the current duplicate that is to be their parent. It's not enough to supply this information because that further duplicate will also have the exact same coordinate, 0, 0, 1 minus the right vector, so 1, 0, 0. And it's going to be sitting at exactly the same position as its parent. Yes, the scale is going to be smaller. This is why you saw this matryoshka situation in Unity, when they were sitting one inside of another. We should base their new position on the position of their parent, adding this vector to that position, since whatever we place here has to be relative to the world. So parent transform.peak, which is the link to the parent's transform, dot position, which is in the world space. And to it, we're adding the forwards direction as well as the rightwards one. This is the left branch, and for the case with the right one, it also has to be changed with this addition. I'll change it here as well. Let's try it out. I'll do 2 iterations just for the sake of simplicity. We'll click on the cube, and you can see that everything is proper. It's done correctly, with one exception that there is one sphere missing here. To fix this, we could have actually populated the entire code starting from here and ending where our function ends with lots of debugs, identifying which blocks of code get ran, and look at their sequence in the console to figure out the decisions the computer was taking when he was outlining those patterns. But instead, I have a feeling that the problem is occurring somewhere in this part, because that's why the right branch wasn't created. I will try to understand the problem with just one iteration. Notice this pattern. The big Igor sphere is here. We go to the left. We go to the left. We come back. and we're not able to do the right branch. Instead, we come back and we do the right branch, and then we do the left one. We come back and we still cannot do the right branch. So there is something which happens when we travel to the left, which prevents us from being able to create the right branch. Let's still put several debug messages and see what's happening. I will identify what information I'm outputting. That's going to be the explored branch. In fact, I think I know where the problem is. It's most likely because I've placed this in a wrong place. Parent transforms.pop should happen synchronously with the branches.pop. Because we're coming back, we are removing whatever is sitting at the top of the branches stack of numbers. We should also remove synchronically the transforms, since we're coming back. Explored branch is 0, we're traveling to the left. We are creating an object, our duplicate, and are traveling deeper leftwards. Here, the explored branch is 0. So after we created another duplicate, after this, we're seeing that we should return after inspecting the left branch. When we come back here, the value will be 1, signifying that we should go to the right, to this sphere. In addition, I will also add this part, where if we're going deeper leftwards, we should also say from where we're going leftwards. From the left branch here, and from the right branch here. I have finally managed to catch the error by comparing how synchronously does the branches count grow with the parent's transforms count. So as well as sticking branches.count on every single debug, I also stuck aside of it everywhere the count of the parent's transform stack to see how it grows. And turns out that if after we've inspected the left branch and have to retreat backwards, we should not be removing whatever sits currently as the top parent. Even though we created a duplicate in the left branch, we didn't store it as the parent. And currently, the parent is that particular parent of that duplicate. After we'll retreat back to that parent, we'll be traveling to the right from it. So we should not be removing this transform, because the duplicate to which we're traveling to the right will be basing his transform based on this parent to which we're currently retreating. This is very complicated, but trust me, this is how it's working. And also, the branches.pop should not be called as well. So finally, after this hardcore debugging, we can create all the spheres appropriately. It is also important to make sure that their distance diminishes as they get smaller. So perhaps we can comment out all of the debugs now, because every single debug slows up the operation time of the editor, and we can be modifying the forwards and the rightwards direction by the scale of the parent. For that, I'm going to introduce the float variables. Parent z-scale will look at the scale of the current parent of the duplicate, and we'll get the z value. Also, parent's x-scale will get the x value. All the forwards and the rightwards directions from the parent's point of view are going to be multiplied by the appropriate parent's scale. The forward one by the z-scale, the rightwards one by the x-scale. This was regarding the left branch. For the right one, the same thing will be introduced. Forwards direction from the point of view of the parent will be multiplied by the parent's z-scale, the rightwards one by the parent's x-scale. Of course, I did a mistake here. It should be big X, because that's what the variable looks like. Clearing my console, getting rid of all the spheres. When we're placing the objects recursively, their distance is shortened. Let's try 2 iterations. Insane. Super cool, and it looks amazing. I'm so glad I found this error, and even though I'm editing this tutorial in real time, so that you don't have to look at my struggles, believe me, it took me about half an hour until I figured it out. Another thing to get concerned about is that none of them are tied to prefab, and that's because of the way we're instantiating them. we are using the game object.instantiate based on the game object parent. Actually, in fact, it should be renamed to big sphere, just to make it clear, because it never changes. Here and here. We're always instantiating the big sphere as a duplicates game object. We're basing our duplicate on that game object. So it never changes, but the transforms of the duplicates get passed around. And because of this instruction, there is no connection to any prefab. So instead you might want to pass the prefab into this slot and use the prefab utility.instantiate the prefab. But since you're still looking at my tutorial, you probably understood everything that I was talking about before and didn't quit. So big congratulations to you, I'm shaking your hand. Since you didn't quit, it will be easy for you to do. Just use the prefab instead. That way your spheres will be having connection to the prefab. Also, since this is no longer working recursively, but working in a pseudo-recursion, you are able to record all the objects in a single undo, somewhere here. Just do it like I explained to you before, and that's going to be a piece of cake for you. You've currently finished the most hardcore example of all the lessons, of all the tutorials. And there was nothing like this in tutorial 8, because it was just introductory. Even the Octree wasn't as difficult. If you understand how to transform recursion into stack form, you are definitely on a very advanced level. So I congratulate you and keep working, my friend. This time we will look at mesh filter class, and we'll see how actually the objects get processed onto the screen. Previously, in part 8, we looked at the mesh filter and mesh renderer, and I explained to you that mesh filter handles information about vertex positions and the mesh itself, whereas mesh renderer takes those vertices and outputs them to GPU. So here we got a cube. You can see that mesh filter cannot be disabled as from now on, but it can be removed. If you won't have a mesh filter on your model, there won't be any information about vertices or edges, polygons that have to be processed. Mesh will not be even existing, so there will be no concept as of cube or whatever triangular polygon surface you have. However, if you turn off mesh renderer, you will have those points, but they won't be processed by the graphics card. I had one subscriber asking me what mesh is and how it's working, why is it important to have triangles of the mesh. Let's go step by step once again, just to ensure that everybody understands it. All the objects that we see in 3D, be it a beautiful house, chair, table, football, character, etc., each one of them is a volumeless shell. It's a shell consisting of vertices, the surface consisting of vertices, which are connected by segments. And they form polygons. Those polygons, when connected together, form a shell, but inside of the model there is no idea of volume or anything. Once again, it's just points in space. So when I was modeling objects in 3ds Max back in part 4, or 3, or even 2, I was explaining to you that you have to stay away from modeling with the concave polygons. That's a polygon of that shape, for example, where you've got 6 vertices on the corners. And this type of polygon is okay, but not really. Even though you still can use it in your modeling, and it's just an arbitrary representation of a bunch of triangles, you should stay away from it and attempt to use quads. If you can't get around with working with quads, it's okay if you start sticking a couple of triangles into your mesh. Here's a character I'm working at the moment on. And as you can see, it's built mostly from quads, but here and there, very rarely, you can see there are triangles. Actually, I did a pretty good job of getting rid of them, because the best thing you can do when modeling a character is to use quads. But there is one or two, I think, on the ears somewhere. Yeah, right here, you can see there is a triangle here. The problem with triangles is that when you subdivide your model tessellated, sticking more polygons inside of those ones, triangles are breaking up those loops that you can see on the surface of the character. We were talking about this, I think, in the beginning of tutorial number 6, when we were rigging the character, and we paid special attention to rings and loops that the quads can form. So the moral of the story is use quads, avoid any kind of polygons like those ones, and if you can't get around with using quads, it's not a big deal if you stick a couple of triangles. However, try to avoid them. Tessellating with them is a problem, since triangles are not really falling into the strip idea, and it's hard to understand where the strip goes. For example, if I duplicate this character and convert him to editable poly, the only way you can divide quads into triangles is either like this or like so. This might seem simple, but there is a subtlety to it, about which I'll talk in a second. However, as you can see, this stripe of polygons, if I select this one and shift-click on the neighbor, it fails to understand that there is a loop if it encounters a vertex from which it sees 5 segments extending. I mean, those ones, and the vertex is in the center. If you get rid of this 2 triangles, you'll get a quad. And it always warms my heart when I see on the model and try to get rid of the triangles, refining it after it was built, when I see 2 triangles nearby of each other, because that means that there can be a quad. But I was talking about the subtlety and how those quads are working. If you go into the polygon, edit polygon mode, in the editable poly modifier, and under the edit polygons rollout, and by the way, you can grab this border and drag it to the side so that you can see extra columns instead of having to scroll up and down. But in edit polygons rollout, you got edit triangulation. If you press it, I already have a shortcut established via customize user interface from the group editable poly. I got edit triangulation. It's somewhere here. If I press E, edit self-selection, edit triangulation mode, I pressed Shift R to be the edit triangulation mode. So yeah, if I press Shift R and enter this mode, you can see that under the hood, behind your back, 3ds Max triangulates the model, and it splits all the quads, all the pentagons, which you should avoid by the way, because try to stick to quads and triangles. It triangulates them behind your back. As you can see here, since I'm using quad, let's focus maybe, which is going to be the best idea. Maybe this quad, or even this one, that's even better. So here is a quad, and as you can see, if I enter the triangulation mode, it's being regarded of 3ds Max as of being consisting, of course, from 2 triangles. And the way 3ds Max connected it is from bottom vertex to the top one. So you got triangle on the right and triangle on the left. The purpose of edit triangulation is that you can take over this responsibility from 3ds Max and say that, no, the way I want this quad to be triangulated is actually maybe like this, from this vertex, and I click on this one. And as you can see, the polygon is now bent this way, as opposed from if we would be doing it from the top to bottom. So it's a subtlety which you should pay attention to, but it really comes down to refining a character, and it's really important when you want to rig the character, since if you want your leg to bend, it's quite reasonable to put a direction of triangles to be horizontal here, since the leg has to bend outwards when the character spreads his legs. The same thing happens on the extensors and your flexors. Those are the muscles located in this region of the character's arm. So it's really important to pay attention to triangulation in this area, because when he twists his arm, even though you're using roll bones, like explained in the end of tutorial number 6, the rigging part, even though we're using them, we still want to have a correct bending of the arm. So check out how the triangulation is flowing on the arm here with my character. The moral of the story is, if you have a quad, behind the scenes, it's going to be represented as 2 triangles, because in reality, everything, absolutely every single polygon that you see in 3ds Max, be it a pentagon, a quad, or even the irregular shaped concave polygon, all of them are consisting of triangles. What might happen in reality in 3ds Max, if you have a pentagon, it's subject to 2 types of bending. First of all, you can have a pentagon to be split into triangles like this way, that way, like so, and of course like this. So several types of bending that can occur in the polygon via this line and this one, if you have triangulation to be as such, or in the other ways. So you're subject to several modifications and bending of the polygon. It's going to be much simpler if you stick to quads, because if you think about it, pentagon is nothing but a quad and a triangle. The fun part comes in when we start to talk about the irregular shaped, the concave polygons. Concave means bent inwards, because there are several ways you can triangulate this surface. In reality, if we make this polygon convex, it has 6 sides, so ultimately it would desire to be of that shape. But we took those 3 vertices and brought them in here, literally shrinking it that way. So it might work as long as you have correct triangulation in it. But for the love of God, try to avoid it. Try avoid using those concave polygons, since even though you might see that triangulation is correct, it's gonna work, for example, if you have that type of triangulation. Even though if you have correct triangulation here and it looks okay, when you continue to model the surface represented by those polygons, distort it, maybe rearrange it, you are subject to actually screwing everything up. because in this position, like so, that triangulation is okay, but if you distort your polygon, triangulation might not work. And if you have, for example, triangle specified to be like this, you can see that this triangle actually interferes with the surface of polygon, and the polygon will have this kind of shape now, completely different from the one that you expect. That's because you're using concave polygons, and in reality, if you see such polygon, well, 6 vertices means directly that it can be split into 2 quads. Just do this, and you got 2 quads, one here and one here. That all comes down to topology, the one that we've been discussing in tutorial 3, and we touched very briefly on it when we were retopologizing the high mesh skull. And looking back at it, I was just practicing back then, but the main point was conveyed to you that you can have a high polygon mesh and have its retopologized version built on top of it. So we were using quads all the time there, and that's the rule of thumb. Always use them if you can. As the final exercise of this lesson, I want to show you how you can procedurally alter the surface of the plane of Unity to make it look a little bit like it's under some sort of waves. So make a wavy surface. The way it's working is we're going to be using some of the trigonometric functions, but don't freak out because it's quite simple. We'll be touching on them later on. Right now, let's understand what's happening just so that we have a clear picture in front of us before we start to code. We've already figured out that all the information about the vertices, about the topology of the mesh, that is how the vertices are connected into triangles, let's say vertex A to vertex B to vertex C, as opposed to vertex C to vertex B to vertex A. That would be 2 different triangles, actually facing in 2 completely different directions. But all of this is responsibility of this guy, the mesh filter of the cube. It has all the information about it. So if we ever want to change something inside of it, to maybe change the position of the vertex of the cube, maybe we want to pull it aside and apply the changes, all of that is going to be meaning that we have to deal with the mesh filter of the model. The mesh filter contains several types of information. The most important one of which is the vertex array. I think it's spelled this way, but doesn't matter. So the vertices, the array of 3D coordinates, and it also has triangles. That is an array of integers. If you look at triangles, you might see something like this: 0, 1, 2, 1, 2, 3, 3, 4, 5, etc. This is saying that when we look back into vertices, vertices is just vector 1, vector 2, vector 3, vector 4, vector 5, etc. So just 5 entries. And when we look into triangles, we see that to build a triangle, which is made out of those 3 numbers, inside of the vertices array, we go from element 0, this guy, to element 1, this one, and then to element under index 2, this dude. So perhaps in reality, when we connect those 3 vectors, those 3 coordinates, we'll have a triangle. And then here, we might see that to build a second triangle of our mesh, we want to go from the index 1 of the vertices to 2 towards 3. And we'll have a second triangle, and then the third one, and so on. As you can see, of course, the number of entries in the triangles array has to be divisible by 3, because that's the way you supply triangles. And once again, all of the meshes are made of triangles, always. Because triangles are just made from 3 points, and you cannot bend it. You can only rotate it, as opposed to quad. Quad can be bent, sort of like this, towards us. But triangles cannot. And that's very easy for GPU to shade them, because this means that the entire surface faces the one single direction. The normals, the direction into which the triangle is pointing, doesn't change and can be slided across all of the vertices, from the top one to the left one to the right one, and so on. So really, vertices and triangles. Mesh filter is the big component which holds a reference to a shared mesh. And this shared mesh, in turn, can provide us with a vertices array and triangles array. The interesting part is that when we have 2 cubes, and we create another one, or maybe create a copy of it, those 2 guys are referencing the exactly same shared mesh. So the mesh filter of cube 1, even though it's a different component to a mesh filter on cube 2, when we're saying that we want to access and compare their shared meshes, those 2 things are actually pointing to the same location in memory. So they're all going to give us the result of exactly the same component. They're just using it for their purposes. This sort of optimization is very important, because when you have a separate model, you don't have to create and explicitly provide extra information about vertices. If the shared meshes would be different, then every single cube would have to have its own vertices and triangles supplied, which would double the memory imprint, making it twice more inefficient. And if you have third cube, then it will have its own vertices and triangles, which just tripled the inefficiency. But if all of them are referencing the same shared mesh, then this thing, the shared mesh, which is referenced, can have its vertices and triangles, but we don't have to explicitly specify them inside of every single mesh filter of the object. Yes, when we will say cube 2, its mesh filter, its shared mesh dot vertices, we'll be referencing those things here. And similarly, if you say this cube, its mesh filter, its shared mesh, and vertices, it will still point us to the same location in memory, and we'll still be referencing this guy here. Let's say you got a plane, and it consists of several vertices, of quads, and even more triangles. But I'm not drawing triangles here, because it doesn't matter. Let's say that we access its mesh filter, we get a reference to the shared mesh of it, we then change the position of vertices, maybe iterate through the array of vertices, randomly subtracting the value from the vertical coordinates, maybe downwards, upwards. But we go through all of the vertices and we modify the mesh's appearance so that now it looks wavy. After this has been done, since we were working on the shared mesh of the object, now if we create any kind of plane inside of Unity by going to Game Object, 3D Object, and Plane, all of them will have this problem where they have a wavy surface here, because we've just altered the shared mesh, the mesh that is shared by all the objects created. So before we even attempt to do something like this, we should really say that, actually, you know what, we're going to be altering the vertices of this mesh. We're going to make a duplicate, copy all the coordinates of vertices and triangles from the shared mesh, so that it's separate from the mesh, the shared mesh, regarded by all other planes. We're going to be just working on our own copy and using it as our mesh. This is very important because sometimes, especially in editor scripting, just by referencing a incorrect mesh, you might alter the way it looks, the coordinates of its vertices, for all the objects, because they're all going to be looking at this guy that you're changing. But if you make a copy and alter it and then apply it to this object, this guy is going to be actually different from those two, because it's going to be having its own separate mesh with its own separate vertices and triangles. Hopefully this makes sense. So I really want to add functionality where I can add waves to the surface of any model. And all of that is going to go, of course, into our tutorial 9 window script. I'm thinking about maybe creating a slot for an object where we can plug it from the scene, and maybe a tick. Say that the vertices of this guy's mesh should be deformed by our waveform function. For that, I'm going to declare a variable of type GameObject, because I'm expecting objects to be plugged into the slot directly from the scene. I don't want to be working with their prefabs or anything. So I'm going to call it GameObject for wave. And inside of our onGUI function, let's say that the GameObject for wave receives the result, which is immediately cast down to GameObject, receives the result of the function, which returns object, and inside of this object field, we're going to be displaying whatever is held right now in the GameObject for wave, just like I explained to you earlier on when we were just starting to build this window. So we're displaying the GameObject for wave. We're going to be expecting the type of GameObject to be placed into the slot, and allow seeing objects, yes, let's make it true. So after this, we're going to have a slot in our window, if we haven't got any errors, right here. In fact, let's separate it from our functionality described above by just doing, before that, editor GUI layout dot space, and put a space a couple of times. We also can supply the label just to mark out what's happening here with the label field. And inside of there, let's say object to modify via waveform. Here you go. Space is here, and we've marked out what we want to have from this slot. Now, inside of our custom update function, let's put all of the functionality that is regarding of the previous buttons that we were describing earlier on. Let's put it slightly further and put all of the stuff that we want to do somewhere here. Let's check if our GameObject for wave does not equal to null, or actually the better alternative would be to use the if the result is false of the function which is reference equals, just like I explained to you previously. Reference equals checks of whatever is on its left side, and it's the GameObject for wave. if it does not equal to null, whatever is on the right side. The result of this function would be false if the game object for wave does not equal to null, does not reference it. And since it's false, when we put false into here, well, this code will not be running, but we want to execute it only when the result of this function is false. So we have to invert it with the exclamation mark, which in reality in human language means that if not, the result of the reference equals true, which is when game object for wave equals to null. But yeah, just gonna put a comment here to clarify things a bit. Reference equals is a much simpler function, and if you're working with threading, which Unity hates, it's very strange because you shouldn't even be using exclamation mark equals sign. This can impose several problems at you. So instead I'm trying to use reference equals wherever I can. However, sometimes you might want to test because they're not really equal to each other. Nonetheless, when we got something assigned to the game object for wave, we want to apply our waveform function to it. Let's say apply waveform. That's a function we haven't yet declared. So after everything, let's clarify what it is. It's going to be a function which doesn't return anything because we haven't assigned its result when we were calling it in here. It's just called on its own, so it should be void. Yeah, maybe it's going to be receiving a game object reference, even though it can be working with a global variable, the geo for wave. It's going to be receiving such reference as an argument, just for extra flexibility. We're also going to be referring to it as geo for wave, just to avoid any kind of complications. And here we're going to be distorting the mesh of the supplied game object. I'm going to zoom up a little bit so that you can see better. And yeah, when game object for wave, the global variable, does not equal to null, we're calling this function, which now requires a reference to the game object. Let's apply the game object for wave as its argument. Now, it's very important for this function to not directly rush and brutally grab the mesh filter component, access the shared mesh and start to modify the vertices, because that would mean changing the look of all the modals that are sharing this mesh with this object. Instead, we should create a copy of that mesh and then apply it to this game object. Let's create a variable, the temporary one, that will only exist until this function is not over, of type mesh. And of course you can use mesh, the class, because you're using those two namespaces, the Unity engine and Unity editor. So we can use the mesh class, and let's say it's going to be the copied mesh. Of course it has to be initialized to be referencing a new mesh. As you can see, it doesn't take any arguments upon its creation, but it's our responsibility to supply to this currently empty mesh, which is just a vague virtual thing. We should supply an array of vertices, the coordinates in 3D space, and also the information about topology, how those vertices are connected. That is, also supply the triangles array. Two things. Our copied mesh is going to be based on the shared mesh of the game object for wave. Let's declare a couple of variables on top because we want to steal the vertices and the triangles of the shared mesh. Just copy them over to whatever we have here. So let's declare a variable of type vector3 array because that's what vertices are going to be outputting to us. And we'll call it shared meshes stolen vertices. We will point it directly to the game object for wave dot get component mesh filter because that's the guy that's holding the reference to the shared meshes and everything. And we want to get shared mesh. From that shared mesh, we want to steal the vertices. So vertices, there you go. As you can see, vertices is an array of vector 3s, and you can get it, that is copied over, and set it. So if you set it, you'll change the representation of all the game objects that are having the same mesh. If we'll be plugging, for example, the Unity's default plane into this slot, then if we would change its vertices here, for example, let's say if we would be doing this, access the plane's component mesh filter, shared mesh.vertices, and make them equal to new vector3 array with just one vector, vector3.forward. Whatever is going to happen from there, since we've changed directly the shared mesh of the plane, all of the further planes that we're going to be creating, and even the older ones that were created before this one, since they're all using the same shared mesh, they're all going to be made just from one point, which is going to have a coordinate of 0, 0, 1, the forward one. So make sure you don't do this. Instead, what we're doing is we're copying over the vertices of the shared mesh of the supplied game object. We're just copying them over, not setting them.
And just like I've been talking to you in the previous lesson, somewhere in the middle, about passing by reference and passing by value, all the arrays of primitive data types, and vector3 is one of them, are passed by value. You simply copy them over. Later on, if we decide to say that shared mesh's stolen vertices at 0 becomes equal to vector3.forward, the change that we've done to the 0th element, the first vertex in our array, will not be replicated in here, because we've taken a snapshot from this guy and copied it over. Passing by value versus passing by reference. It's very important. Make sure you understand it. I will put a link in the video right now, just so that you can travel into the previous tutorial to check it out. But once we've got a copy of vertices on our behalf, we also need to steal the information about the topology. That information is going to be stored in the integer array, which is going to be, of course, 3 times bigger than the vertices array. And we're going to be saying shared meshes, stolen triangles. Of course, it's going to be equal to the mesh filter's shared mesh, the mesh that is used by all of the objects from the same group. If it's plane, then by all of the planes, dot triangles. And if we're really neat, we also want to steal information about the normals, that is the direction which every single triangle is facing. So it's also an array of vector3s, the directions, and we're going to say shared meshes, stolen normals. Of course, it's going to be equal to the supplied game object's mesh filter, the shared mesh that is used by all of the game objects of the same group, dot normals. If you inspect normals, it's the array of vector3s, since the normal is a direction. Now, when we have all of this, after we've created our copied mesh, we can supply to it all of the information about the vertices into its appropriate variables. So copied mesh dot vertices becomes equal to, you guessed it, the shared meshes stolen vertices that we copied. Its triangles, the topology, is going to be equal to whatever was copied over previously. The sequence of integers, the sequence of elements in the vertices which create triangles. Finally, the copied meshes dot normals are going to become equal to the shared meshes stolen normals, just like this. And after that, into our game object for wave, we want to get a component of type mesh filter and set its shared mesh to be equal to our copied mesh. Now it has its own shared mesh. But this new shared mesh, which belongs currently just to this game object, has exactly the same information as was supplied here, because after we've stolen it, copied it over, and pasted it into our copied mesh, then assigned the mesh to be the new shared mesh of the object, we still haven't changed anything in here, and that's exactly where our waveform manipulations have to go into. Here we got an array of vertices, an array of coordinates, which should represent a wavy surface. Assume that we got a plane which is consisting of 1, 2, 3, 4, 9 vertices. That's an array of 9 entries. Hopefully that's 9. V1, V1, V2, V3, and so on. That's an array of vertices of our mesh. It's an array of 3-dimensional coordinates in space. If you want to change its surface to be wavy, you have to grab several of the points and bring their coordinates upwards by a certain amount. Here I've outlined them in bold, just so that you can see which ones I'm referring to. It doesn't matter which ones you decide to grab and offset. Maybe you want to offset actually the white ones downwards, and so on. But here I'm thinking about displacing several of them according to the wave function. So as we are iterating through every single vector of the mesh, we want to really say that v1 becomes equal to v1 plus some certain coefficient k, which is going to be the result of the waveform function. How much do we want to offset it by? It's going to be plus or minus 1. Here, k is going to be a maximum of plus 1 or maybe negative 1. That's the biggest it will get, unless multiplied by some external coefficient like c, for example, which can be varying. But we want to iterate through every single vertex like this and change its height appropriately, according to the waveform function. Don't worry about triangulation right now, because even though if it's triangled like here, like this, or maybe in a different way, like so, it doesn't matter. Because if you have many vertices, you'll not see the difference in triangles. It's going to be fine. Moral of story is that we go through every single entry of an array and displace it vertically in the y coordinate according to the waveform function. The waveform, I've been saying it, it sounds like a mystery, but it's very simple. If we do a retrospective into mathematics, you should know about a Cartesian system, the 2-dimensional one, parameter x and a parameter y.
the quadratic function y equals x squared is going to look like this. It's going to be having an exponential growth, because let's say if x is at 1, y is going to have exactly the same value, 1. If x is at 2, y is going to have the value of 4, and so on. So really, by sliding along the x-axis to the right, you're immediately getting the result of y on the vertical axis. The logarithmic growth is like this. It's going upwards, but is always decelerating. So by going to the right, you can see that the y slows down its growth. It doesn't go as vigorously as in the beginning. The change in y, with regards to change in x, becomes much smaller as we keep going to the right. And actually, just because it's so simple, the change in y over change in x is nothing but a derivative. It's dy over dx, the change in y over change in x. It's a value that is explaining how the change in y over change in x decreases. But it's not of our concern. I just wanted to throw extra bit of information on you so that if you ever encounter derivatives, that's exactly what it is. Don't be scared. But that's one form of a function. Our waveform should look like this. As you can see, it's going up and down, but it's always going to have the maximum value to be at 1, and it keeps going to the left for negative x values as well. The smallest value is going to have also with a magnitude of 1, but in a negative direction. So the smallest value of y is going to be negative 1, the biggest one is going to be 1. This part of a cycle, its first half, is going to come back to 0 at the value of pi, and pi is roughly equal to 3.14 and so on. At this value, the function will become once again 0. At the value slightly bigger than pi, let's say that x equals to 4. 4 is going to be roughly somewhere here, according to our graph. At that value, the function will return us a particular value, I don't know which one, but it's going to be somewhere here. And as we keep going, we're going to come to here, and this distance, the traveled one, is going to be equal to 2 pi. Here, the function will return 0 as the result of it, because y will be 0. Really 3 points where it's 0. Here, and after every single time we add another pi, it becomes 0. This is a function of sine. I got rid of the unnecessary information on the top of our board. Let's bring this explanation higher. This function is the sine of x, because whatever you supply into it, you're going to get the value from -1 to +1. Just remember where this value came from. It was pointing to this location on the x-axis. So really, by supplying whichever value into x, even like 5 billion, etc., we're always going to get the value between 1 and -1. Because the further we go, the function just keeps going up and down, up and down. Doesn't matter how far we travel, the function's result at this point of x will be 0, for example, etc. That's the sine function. The cosine function is exactly the same, with one exception, that it doesn't grow from 0 upwards, but grows from 1 downwards. Sort of like this. As you can see, where on sine it would be 0, for cosine, the same value of x is going to return us the -1. And of course, where it was 0 here, for the sine, for cosine, is going to be +1. So it's really the sine function, but slightly offset to the left. And that's everything that you want to know. In fact, you even can forget about this graph. Just remember that whatever value is applied into x, the result of a thing that's going to be output by this function is going to vary from -1 to 1. And it's going to be in a smooth form. As you could have guessed, we want to iterate through the vertices of the copied mesh, and based on their position in space, we want to offset them by a certain amount vertically. In here, let's iterate through all of them, starting from the integer I equals to 0, from the 0th index, while I is less than shared mesh, stolen vertices, dot length, because it's an array, dot count would be for a list. But until we haven't reached the ending of this array, we want to bump up I by 1 and execute the following thing. Just to simplify things a bit, let's say that there's going to be a vector 3, current vertex. It's going to be equal to shared mesh's stolen vertices at index I, because we are iterating through the array. If you feel that you're unfamiliar with this concept, please return back to the previous tutorial, part 8. But I think if you've made yourself through this tutorial so far, My sincere congratulations, because hopefully you understand everything that I'm talking about. Basically, we're iterating through the array of our vertices, and just for this current iteration, from now on, this current vertex we're going to be referencing as current vertex. We copy it over the value. So we want to change the position, the vertical one of this vertex, by the result of the function. Let's say that current vertex dot y, because it's a vector, the three-dimensional coordinate with the x, y, and z components, to the right, upwards, and forwards component. The y component becomes equal to, and it's the one that should be displaced. It becomes equal to the current vertex dot y multiplied by our coefficient, which is going to be the result of our waveform function, the sine one, that is going to return us the result between -1 and 1. The sine function can be accessed by going into Unity's mathf static class and accessing the static function, which is sine. Now, as you can remember, this guy, once again, it's very important to understand, that's why I'm stressing it so many times, this guy outputs the value from -1 to 1. Doesn't matter how big or how small the value is in here, it's going to output the same result between -1 and 1. Perhaps 0.5 or 0.25, -0.7, etc. But as its arguments, we want to supply the current vertex dot x, that is the x position. How far is it located from the object's center? Assume that we're looking from the side of our plane. As you can see, if we're going to the right along this axis, when looking from the side of this plane, the further the vertex is to the right, the more it's going to be offset upwards and downwards. But the way we want to do it is to also supply the current system time, because it's constantly growing, and we want to create the sort of feeling of motion. So as well as supplying the x-coordinate of the current vertex, we'll also want to add the time since startup of the editor. So editor application dot time since startup. This value keeps growing constantly, and it's exactly what's going to be pushing to the right, to the right, to the right, constantly saying it and telling it by how much should it grow upwards and downwards. That's what's going to be progressing us through the function. When you look at time since startup, it's of type double, so you'll get an error. You should cast it to float. Okay, it says the variable game object for wave of tutorial 9 window hasn't been assigned. When we double click on it, it's going to point us to the function apply waveform. And the way we are calling this function, I thought that it was correctly introduced here when we are checking in the custom update, which runs several times a second in our editor. But in there we're checking that we only want to call this function if our game object for wave does not equal to null. But we're checking it by reference. And Unity sometimes doesn't like it, so you really have to experiment with it. I'm really preferring reference equals, but if it doesn't work, you can just say that if game object for wave does not equal to null. This way is really the safest one when working with the game objects or any kind of classes declared by Unity, components, etc. Just use this sign. But for your own custom objects, when you're comparing them and seeing if they are really the same thing, like back in tutorial 8 when we were working with the chests and the nested classes, there you can use reference equals. This way the error should go away. Check this out, because we've modified the y value of current vertex by a certain coefficient, displacing it upwards or downwards, we are iterating through all the vertices of our stolen mesh vertices, of our shared meshes stolen vertices, but it was just a shortcut for us here. We copy over the value into current vertex from this array, but after we've done something here, this array doesn't receive any input because we copied over by value. So shared mesh stolen vertices at the ith index should become equal to the current vertex, because all we've been doing here is passing by value. I'm gonna put a comment here so that you can see that we really copied over the value of the current vertex, so that after we changed it, you have to understand that shared meshes stolen vertices at the ith coefficient was not changed by this line. We have to really influence it like this, apply the current vertex that we've changed back into this slot, overwriting it. Because here we passed by value, we copied over the value from the right to the left. This is already enough and we can see how it's working, but in reality it's not going to be really working at all, because the height of the plane relative to the center of the object is 0 in all of the vertices. Well, 0 times whatever is going to be 0 forever. So I'm really thinking about perhaps doing plus, adding the value which is the result of this guy here. But since it's going to be running so many times a frame, adding every single frame the value which is ranging between -1 and 1 is going to distort our plane enormously. Let's multiply it by a coefficient of 0.05 maybe. Float, of course. There you go. It's growing according to the time, and it's really cool. Check this out. Absolutely amazing. Even better than I was expecting. But yeah, let's maybe change a couple of coefficients here. So first of all, this is not allowing our coefficient to grow too high and add ones every single frame, which would distort our plane enormously. Maybe to make it even lower, let's put a 0.05, so 10 times smaller influence. And there you go. Now it doesn't grow as high, but it's super cool. And because we're creating and calling get components so many times, it's not really efficient or quick, since we are reassigning mesh every single frame. Instead, we can really just get a reference to the mesh, ensure that the shared mesh for the game object is different from the other objects. But as long as it's okay, as long as we know that it's the case, we can just apply the vertices and not change the triangles of that shared mesh, because we're not really changing the topology. We're only displacing the vertices upwards and downwards. If you want your waves to travel further and quicker across the surface, this just means quicker translation to the right. That way you'll be traveling quicker along the curve. This means just a quicker coefficient here. Of course, because there is an issue of frames, since you're sliding across the curve so quickly, the way we are doing it here is very brute. We're just adding and modifying the mesh directly based on the vertices. If we would somehow grab the initial state of the mesh and store its coordinates in three-dimensional space aside, and then build additional array of modified vertices based on the first one, then we would always have the point of reference from which we could apply the change in the modified vertices position, because here, as soon as we apply this change for the next frame, after this function is run over again, what we've done here in the previous frame is going to be the point of reference for the next frame. That's really complicated subject to explain. I'm trying my best, really. But this is a very rude way of doing it. And if you understand it, you can implement it the way I've explained to you a second ago. Nothing too difficult. I'm gonna get rid of this coefficient from here because I'm okay with the way it's working right now. And I also want to change the y coefficient by adding on top of this the value of cosine function. And it's gonna be based on the forwards axis, the z1. Also, the way we're translating our waves across the surface is similar, just using the time since startup of the editor application. Cast down to float. This way you can see that we are getting those kind of waves of our surface, and yeah, it's so good I can't even believe my eyes. But if you stick parallax occlusion and if you stick normal mapping into it, maybe diffuse textures, you're gonna have pretty good looking water which works right in the editor. So if you subdivide your surface more, maybe tessellate it, bring it from 3ds Max, it's gonna look really good. And one more additional thing that I forgot to mention, even though it looks like it has several vertices here and there on the surface, even though we have a plane, which might seem like so, it might look to you that it has only 9 vertices. But in reality, most of the time, it's gonna have 3 vertices here and also 3 vertices here, just for this quad. So not 4 vertices, but 6. Those 2 ones are overlapping in here, and those 2 ones are also overlapping here. If you want to manipulate the mesh with your own hands, you can research into using handles and use, for example, free move handle, the one that you can move around. This thing puts a control onto a given position with a given size, with a given rotation, etc. And by dragging it, you can retrieve the vector 3 in the world space, which can be assigned to the vertex. So if you are positioning handles at every single vertex and then applying the position of the handle back to the vertex, if you changed at a given frame the position of this handle by dragging it or whatever, you're also going to drag the vertex after yourself. I want to comment out the waveform function because I want to show you how you can distort meshes like this and modify their look right in the editor. And I will do it starting from the for loop. In fact, inside of it, I'm gonna comment out the waveform functionality here. So we're still getting a reference to the shared mesh, copying over the parameters from it and then reassigning back our newly created mesh into it. We no longer have the functionality where we change the surface of the plane into waveform. I'm gonna get rid of it and create a 3D object, Quad, which is available in Unity since 5.0. Gonna place it here. And I really want to show you how you can position such handles at every single vertex so that you can drag them around. Handles contains different variables. You can research into it and check it out, especially in the documentation of Unity, the API. But we want to have the free move handle. We should supply to it where it should be positioned in the world. And since we want to do it for every single vertex, it should go inside of our for loop. So after we copied over the value from the currently inspected vertex, and I'm going to be referencing it as current vertex now, after that, we can position the handles into the place of the current vertex, but you have to keep in mind that all of the vertices, I've mentioned this a couple of times by now, they are positioned relative to the model's center. So if I comment this out so that we don't get any errors, in Unity, this is the model center, that's where the pivot is. From the local representation of the axis, that's where the center is, and all of the vertices are specified relative to it. From their point of view, this is the world center for them. But the handles are requiring the position relative to the world's center, which would be, if I grab this cube and put it onto the world center, the 0th coordinate, it would be down there. We want to grab and position the handles right here from the world's coordinate 0 to the center of the object, plus the vector from the center of the object towards one of its vertices. So the current vertex, its world position would be the current vertex, the direction from the center of the model, plus the game object for wave, its transform, its position. That's the world coordinate of the current vertex. Let's say this one right here. From the world 0 all the way to here, that's this vector. Because we're going from world 0 to the center of the model, which is the position, plus this current vertex vector. We can also grab it and put it somewhere here, just to say that vector 3, current vertex, just for simplicity, world position, becomes equal to this. So the position of the object, the center, plus the vector from the center of the object towards the vertex. All of the vertices of the mesh are always specified relative to the center of the object. And now the free move handle can be positioned to be in the current vertex world position with the rotation of, I don't know, quaternion dot Euler, let's say 0, 0, 0. Then the size should be, I don't know, 0.5, maybe 0.25. The snap doesn't really matter, we can put it 1. You can research into the function and its arguments on your own leisure. And of course 1 is incorrect because it's a snap, it's vector 3. So let's say vector 3 dot forward. So with length of 1. If we inspect the signature further on, the size should be float. So we should put an F in here. And after we've specified by how much we want it to snap, we also should supply it the way it should look like. I want it to look like a sphere. I'm going to do it as handles dot put cap because we can pick out from whichever ones we want. So cap, we can pick between circle cap, arrow cap, cube cap, dot, rectangle. In my case, I want to have the circle cap or even sphere cap if possible. Yeah, this one. And it's quite interesting. Sphere cap is a function, but I don't know why. You don't have to even specify the arguments or even mention its brackets. You just put it like this, handles.sphereCap, and it's going to be working. If I focus at our quad, there are going to be 6 handles, 2 of which are going to be overlapping for the reasons I've explained to you previously. Now we can drag them around, and they're going to be outputting the result of this as a vector in world space, but they're always going to be starting from the current vertex's world position. So unless we assign the current vertex's world position to the result of this, similar to the toggle and the GUI implementation of the sliders and the slots, unless we do this, we won't be actually changing the current vertex's world position at all. I'm just going to put it on the new line so that it's more visible, like this. And now after we've got our current vertex's world position, let's bring it back into the world space so that it can be assigned backwards to the model. Current vertex, which is in local space of the model, becomes equal to the current vertex in world position minus the transform of the game object for wave, its position. This coordinate in the space local to the object becomes equal to the world position, out of which we subtract the position of the object relative to the world. Because we do this, we immediately bring ourselves into the object's local space. And of course, we should be applying the change since we copied over the value of current vertex but are not referencing the cell in this array. We should really apply the change like this. We got a success in here, and we're dragging the object's vertices correctly. So create a plane. I'm gonna stick it into the slot. Every single time we process the vertex, we are creating a handle, and as you can see, we are pretty much simulating whatever 3ds Max is doing there, even though 3ds Max is so much more complicated. But we still can create our own extension for the editor like this, and if you figure out how you connect vertices, which would require you to modify the topology of the mesh, you could actually create your own small modeling package like this. If you are in that top 1% of people who have watched the entire lesson and didn't skip to the end like the other majority, you have gained something very important. After this lesson, you have a solid understanding about some of the optimizations which the physics engine takes. You are able to replicate parts of it, such as the Octree. You understand the importance and the intricate relations of the binary search, implications and benefits of different data structures. We've covered some awesome tricks and worked with the stacks in a quite inventive ways to reverse the flow of time. Recursive stack overflow is no longer a problem to you, and you're able to speed up your workflow by creating powerful extensions in the editor and paint any prefab objects directly on any given surface, instead of manually positioning them by hand. You're able to efficiently figure out the quickest way to find out if the point is inside of a given concave region or not, and manipulate any given mesh directly in Unity's editor, and you got familiar with the link and enumerables. My congratulations to you. This lesson was very long, and we still haven't covered serialization, that is how you save data between Unity's sessions, and we're yet to learn about assets database and scriptable objects. After you have mastered all of that, you'll be able to get into, in my opinion, the final stage, where you start to learn shaders. That's where the sudden realization comes that from now on you can make any game that you ever think of. It's sort of like suddenly seeing the whole picture together instead of a pile of disjoint puzzles. Now it's just about digging through Unity's API for some extra other cool functionalities that it can provide. But at that stage you'll have the entire arsenal of tools ready for you. From that moment of time, you'll only be bound by the size of your imagination. I know that this information was very important to you, and if you want to thank me, you can go to igoraherne.com and drop me any sum that you want. До встречи, and I'll be back.